rainfall leading to the disruption of lives. Apart from these, we also have the small scale weather events affecting this country, like the thunderstorms, hailstorms, squall, tornadoes. And overall, in the recent years, we will find that the number of deaths due to the lightning is ever increasing. And every year, about 2,500 to 3,000 people die in the country because of that lightning, while the number of deaths due to tropical cyclones has been reduced to only a double-digit figure, being limited to less than 100 to any landfalling cyclones. So therefore, as the time changes, the challenges also become different and more imminent. Maybe there could be some impact of the climate and its consequences. But however, the country has grown up over the period of time. There has been institutional arrangement in the country to deal with multi-hazard early warning system so that we can enable the disaster managers to take sufficient lead actions to minimize the loss of lives and properties. As I was telling that 80% of the natural hazards are hydrometeorological in nature. Therefore, Ministry of Earth Sciences plays a dominant role with respect to monitoring, forecasting, early warning services for all these disasters. So if you just took off the tropical cyclones, the local severe storms, the winter storms, there are the identified nodal agencies like India Meteorological Department. If you think of floods, we have got the Central Water Commission. And here again, we provide the support, IMD and other allied organizations in Ministry of Earth Sciences provide support for monitoring and prediction of the floods by Central Water Commission. When you talk of agriculture and disaster like drought, again, IMD plays a dominant role to provide weather monitoring and forecasting services for monitoring and forecasting the droughts. Be it snow and avalanches in the hilly regions, there also Ministry of Earth Science and IMD plays a dominant role by providing information about the occurrence of snowfall. So be it the case of climate change or the impact of climate change and extreme weather, IITM, IMD and other constituents provide the required input to Ministry of Environment, Forest and Climate Change. Similarly, sometimes whenever there is earthquake or there is some kind of landslides, there are also secondary impacts and roles by the Ministry of Earth Science and IMD. If you consider the new area where there has been threat now, that is the air quality. In air quality also we experience some kind of slow hazards, and it also causes especially the physiological problems and the health problems. So IMD plays a dominant role with respect to air pollution, haze, fog, smoke, etc. in association with Indian Institute of Tropical Meteorology and National Center for Meteorological Weather Forecasting. Similarly, there is coastal zone management because of this increased threat due to sea level rise and other coastal hazards, coastal erosions, and ecosystem monitoring and modeling. So all the different constituents of Ministry of Earth Sciences work together to provide these services. If I just go a little detail into the role of India Meteorological Department, yes, it is the nodal agency, and its vision says that no weather hazard should go undetected and unpredicted. There should be accurate warning against the hazards with a reasonable lead time so that it can trigger response from the public, from disaster managers, various stakeholders to minimize loss of lives and properties. So while doing all these things, IMD acts upon almost 5 to 6 pillars. One of the most important pillars is the observations, followed by the numerical modeling. And based on this observation numerical modeling, we go for forecasting and severe weather warning systems. And finally, we go for sectoral applications to provide sector-specific information for improving the socio-economic conditions. And to carry out all these, there is research and development by India Meteorological Department, all the constitutional Ministry of Earth Sciences, and the research and development community in the country and outside. There are many academic and R&D institutions in the country have played a dominant role in the recent past, contributing towards the applications of India Meteorological Department services. So therefore, as a result, you will find that number of sectors where the service has been provided, that is ever growing, and there is no further service perhaps left out any sector in this country where weather and climate do not play any role. So we are venturing into new and new sectors, and everywhere now we are providing impact-based forecast and early warning for sectoral applications. So if you just look at the service enhancement in recent years, what you find that there has been significant enhancement in the services. So I'll just take a few examples. Let us take one example of tropical cyclones. What you find that there has been a continuous improvement in the forecast accuracy with respect to the detection of the occurrence of these tropical cyclones in terms of its location and intensity, and also its forecast in terms of the track or path or movement and intensification of the tropical cyclone disturbances, the landfall point in time, and associated adverse weather like heavy rainfall, winds, storm surge, coastal inundations, etc. So if you just look at the forecast accuracy, you find that at present, if we say tropical cyclone is crossing the coast, then in 24 hours ahead, the error is about 30 kilometers. 48 hours ahead, error is about 60 kilometers, and 72 hours ahead, error is about 90 kilometers. So there has been such an improvement that if you compare with international warning agencies like USA, UK, Japan, or Australia, you will find that we are second to none in terms of providing the cyclone warning in terms of track, intensity, and associated weather. So this is just an example on the bottom left side, that super cyclone Amphan forecast, which was just a pinpointed forecast. And as a result, what you summarize that there has been about 45 to 50% improvement in predicting the location, intensity, and associated adverse weather in recent 5 years compared to previous 5 years. Now, if you just look at the monsoonal heavy rainfall, which causes floods and havocs in the country, there has been a significant improvement. The diagram on the left-hand side, you can find out that the probability of detection, POD, has increased significantly, and at present, it stands at about 78%. And if I compare this probability of detection previous 5 years and now, I will find that from 2014 to 2020, there has been almost improvement by 50% to 77% in 2020. And for 24-hour forecast, there is an improvement of 48% to 70% for day 2, that is 48-hour advanced forecast. And similarly, for day 3, it has an improvement from 37% to 66%. Now, if I compare what was the forecast accuracy for day 1 and now what is the forecast accuracy for day 5, what I find that the day 5 forecast at present is almost same as the day 1 forecast accuracy in 2014. So there has been therefore a lead period. Not only the forecast accuracy has improved in the recent years, but also the number of days in advance by which warnings are being made available to disaster managers in the public, that also has increased from day 1 to day 5 with similar accuracy. Now, if I just look at the nowadays the killer, that is lightning and thunderstorms, there has been significant improvement. India is the among 5 to 6 countries in the world which is providing the lightning warning to the people and the disaster managers. There also, if you find out, we provide 2 types of lightning and thunderstorm warning. One is the nowcast, valid up to next 3 hours. Another is the day 5 forecast, up to 5 days forecast with respect to occurrence of thunderstorms. So there also, if I just look at 24-hour thunderstorm forecast verification, say recent 5 years, what we find that it is just improving, and probability of detection has increased from 61% in 2014 to 88% in 2020. Similarly, if I just look at 24 hours advance, you will find that it is increased from 31% in 2016 to 80% in 2020. So therefore, there has been a significant improvement with respect to thunderstorm detection and prediction also. It has been possible because of the combined effort of the Ministry of Earth Sciences involving IMD, IITM, and NCRWF. We have come up taking it as a challenge in 2018 with the guidance of then Secretary, Minister of Earth Sciences, Dr. Rajivan Saab. We came up with a platform where we can provide a combined information of satellite, radar, and lightning detection system based information about occurrence of lightning, and also the forecast with the numerical modeling system. So similarly, if I just look at the heat wave, which is another success story, that number of deaths due to heat wave has also decreased in recent years. We find that the forecast scale of heat wave also has increased, and it is almost about 90 to 95% at present. So it has enabled the disaster managers to go for a heat action plan. With the heat action plan, it has been possible to involve a public-private partnership, all the health workers and the municipal workers, and also the early warning service providers to provide a real-time information for actions. Here also, if I find that the comparison of forecast accuracy with day 1 to day 5 in 2014 and 2020, I find that there has been a gain of 4 days with a similar accuracy level. As it was accurate in 2014, in day 1, now we find the same accuracy in day 5. That means we have gained 4 days to prepare for the heat wave. So as a result, if I just look at the outcome, what I find that number of deaths have decreased significantly. This is just an example of the number of deaths due to tropical cyclones. You will find that in recent years, there is a significant improvement. There is no cyclone in 2010 to 2020 which has crossed the coast and has caused a death more than 100. So similarly, if I just look at the other countries also, the benefit which has been accrued to the different countries in this region because of the improvement in early warning system of India Meteorological Department and Minister of Earth Sciences, we find that there is also an enabler by the country to the neighboring countries in South Asia, Southeast Asia, and the Middle East. There is also no cyclone crossing in this region, any country in this part of the world where number of deaths has increased more than 100. So therefore, if I just compare a few years back, like 1999 and now, if you see that there has been a significant gain in terms of minimizing loss of lives. And also at the same time, the accuracy has also led to minimizing the area of evacuation. Now, if I just compare area of evacuation in say 99 super cyclone, it was from Gopalpur to Digha, it is around 500 kilometers. Now, the forecast is limited only to 4 districts, about say 100 to 150 kilometers. So there is a gain of 200 to 300 kilometers minimization of area of evacuation. And in USA, there is an estimate that it is $1 million, which is the cost towards the area of evacuation for 1 kilometer area. Now, if you just consider 1 million rupees, you can just imagine how much is the cost saving towards the government exchequer because of the minimization of area of evacuation. Similarly, the ex gratia payment, the number of people dying has been minimized. As a result, the government which was paying a lot of ex gratia, that has also been reduced, apart from all the gains which cannot be measured in terms of moral gains. So as a result, it has been also appreciated internationally and nationally, the early warning systems. This is just an example of the heat action plan. You will see that in 2020, there was just only 4 deaths compared to 2015, whereas death of 2040. So it is impossible. If I remember, in 2015, when there was 2040 deaths, then Minister of Earth Sciences decided that we should go for an end-to-end early warning system for a heat wave. So we introduced in 2015 the seasonal forecast, and which is followed by the extended range forecast for next 15 days to 1 month, and it is followed again by the short to medium range forecast up to 5 days. Then, of course, we go for the nowcast. So, therefore, there is a continuity in spatial scale and temporal scale about not only the heat wave, but all types of severe weather event, which has enabled everyone to minimize the losses and lives. So, you may think that how did it happen actually? All this improvement in early warning system has been possible because of the significant intervention in terms of policy and planning. There has been significant intervention by the National Disaster Management Authority and other Minister of Home Affairs and also the Minister of Earth Sciences with respect to policy and planning. The first Vision 2020 document came in 2010 by Minister of Earth Sciences. It has been further improved by Vision 2030. So the continuous vision and strategy, which is a part of this policy and planning, enabled Minister of Earth Sciences to go for the latest tools and technology and the strategy to deal with all these things. At the same time, there was support from the disaster management agencies through their visions and strategy documents. So accordingly, what we did actually, we introduced new tools and technology, we introduced new methods, we went for enhanced research and development and capacity building. As a result, there has been a confidence building measures which taken up by Minister of Earth Sciences, India Meteorological Department, and also the outreach. If I just look at, I was just talking about this improvement in policy and planning, we just prepared Vision Document 2010. We planned that in 2020, there should be improvement by 20% by 2015 and 40% by 2020. But now you can just imagine how much improvement has been there. I've just shown you the improvement in terms of severe weather warning forecast performance. So there has been a significant improvement. And that has been possible because of various interventions, as I told a little earlier. But apart from that, there has been many soft approaches. Apart from hard approaches like procurement and observations enhancement and modeling enhancement, there are soft approaches. Soft approaches means we have gone for standardizing our operational procedure, preparing the roadmaps and checklists, etc., going for new methods like impact-based forecasting, and taking the help of the DM Act and DM plans of Government of India, National Cyclone Risk Mitigation Project, National Lightning Early Warning System. All these has been intervened with the highest level. So I'll just talk about the introduction of new technology. If we just look at, there has been significant improvement with respect to atmosphere, land, and earth system observations with high wind speed recorders, automated weather stations, automated rain gauges, ocean buoys, double weather radars, GPS-based Sundays, and also the pilot Sundays. And there has been also the decision support system for monitoring analysis, and as a result, we have upgraded from manual to a digital platform. We've also gone for enhancing global and regional modeling system. Now we have got a model which can provide a forecast for 10 days with a resolution of about 12 kilometers, which is almost at par with all the global models in the country. At the same time, we have got also the ensemble prediction system, which provides the forecast the same resolution and also up to same 10 days. So it is impossible because of the hyper computing system, which has been procured by Ministry of Earth Sciences. So like that, also we have gone for improving our early warning system with digital platform. So if I just look at the various components of early warning systems, you find that all the components, starting with observations and then modeling, then forecasting, then and forecast generation and decision making by the disaster managers, and to help them to take a decision, all these experts systems has been established with the modernization of India Meteorological Department and Ministry of Earth Sciences. As a result, we have been able to minimize the missing of the severe weather events and also providing a forecast for this. So this is in detail about the observation systems. I will not discuss in details. You can see that we have got very optimal network system in the country with the help of Doppler radars and satellite, and also the ground-based tools like departmental stations and automated stations and then gauges. Also, we have got the off-air stations like radio stations, radio winds, and pilot balloons. Specifically, I will tell about radar. If I just look at the radar, history says that we came up with radar in 1950 as expand radar in Damdam, Kolkata. And then first indigenous radar also was developed and that was stationed in 1970 in Delhi. Then first S-band radar was established in Visakhapatnam in 1970. Then first indigenous cyclone detection radar came up in 1980. And currently, if you just look at now, we have come up with 30 Doppler radars with a beginning in 2004, Chennai Doppler radar. And all these Doppler radars are very much beneficial and provides the real-time information, not only for nowcasting and short-range, various short-range forecasting, but also it provides data which are integrated into numerical models to provide the forecast. At the same time, these radar data are also superimposed in a GIS layer so that we can compare and analyze the ground truth, satellite observations, and radar observations to take a decision. The satellite, similarly, if you just look at, we have come up a long way, starting with 1960 when TIRA satellite was launched by USA, and we are donated one reception system in that is called HRPT in Mumbai Colaba office. And thereafter the story went on, and we came up with the satellite division in 1982 and 83 when India started its INSAT series. We are fully capable to utilize all informations from our satellite series. And at present, we have got 2 satellites, that is INSAT 3D and 3DR, and also the scatterometer satellites. So this has enabled to have every 15 minutes observations from the satellites for all types of severe weather events. At the same time, there has been augmentation in ocean observational network. All types of latest tools and technology has been utilized by National Institute of Ocean Technology and Indian National Center for Ocean Information Services, which are also working together with India Meteorological Department at the behest of Ministry of Earth Sciences. You can find out that North Indian Ocean region, as shown here, is adequately represented by the observation, but still there is scope. But I will say that these observations enabled us to run the ocean models and hence to provide the coupled system for ocean and atmosphere. At the same time, if you look at the data exchange, gone are those days when we started with the telegrams, and in 1974, even if you just consider it was just alphanumeric data and few kilobytes. Now in 2012, if you just look at 600 GB of data are being exchanged by various platforms. So we have come up with a multifold increase with respect to data exchange with the establishment of the latest tools and technology. Now, if you just look at present, we have got suite of prediction models and tools, starting with regional models, global models, and location specific, and also the sector specific modeling system by IMD, INCOES, IITM, and SNRWF. So this is just an example of the introduction of methodology. So earlier, these are the days, I'll take just an example, that fishermen were confined only to the coastal water. They never went beyond 75 kilometers. And therefore, all India radar was sufficient enough to provide information to coastal fishing purpose. But now you'll find that the fishermen are going far ahead and they're going far away from the coast, and so they are cut off, they're not getting any information. So we decided that instead of providing fishermen warning only for the coastal water, we should provide fishermen warning for the entire Bay of Bengal and Arabian Sea. So this type of intervention of new methodology as per the demand of the users has enabled IMD to reach out to each and every person in this country. Similar is the case with respect to the graphical and textual representation of various products, not only for heavy rainfall, thunderstorm, lightning, cyclones, but all types of weather events. So this is just an example of the tropical cyclones of what we have come. Actually, I want to say that we have gone far ahead with respect to monitoring traditional early warning services. The latest new intervention what we have done in the 2020 is that before the genesis of a low pressure systems, we have provided the cyclone watch. The pre-cyclone watch was provided to the disaster management agencies for Cyclone Tauktae and Cyclone Yas even before the genesis of low pressure system. So people say that before the birth of a child, parents just dream of what is the name of the child, but they do not name. But now the situation has come. This system has enabled, the Earth system science has enabled the forecasters now to even to dream of the cyclone disturbances 15 days ahead or 10 days ahead and provide the forecast and early warning as cyclone watch. Now, another new intervention in recent years has been the impact-based forecasting in India. As you know that we are providing now impact-based forecast for each and every severe weather. Instead of telling what the weather will do, what the weather will be tomorrow, now we are telling what we will do tomorrow. So, for example, if we say that there will be severe weather in Kochi, now we are providing that which part of Kochi will be inundated because of the heavy rainfall, and what action will be taken towards the transport or towards some other socioeconomic sectors. But however, while doing so, what we find that there are different stages of implementation of impact-based forecasting. With a humble beginning in 2013, after the Kedarnath episode, IMD started the color-coded warning. We provided only 4 color codes, green, yellow, orange, red, to indicate that some kind of severe weather is expected, action needs to be taken. So that was the guideline by WMO. Thereafter, in recent years, from 2018 onwards, what we have done actually, we are describing what type of severe weather we are expecting, what type of impact we are expecting with respect to different sectors. Then comes the third step. The third step comes the dynamical information. So we should have some kind of threshold method. We should find out what is the threshold of rainfall. The rainfall threshold may not be same for different cities and different towns. For example, we have come up with Trivandrum now, where we have identified what should be the threshold, what should be the cumulative rainfall past 2 days, past 3 days, past 4 days, past 5 days, which can cause the floods in the city of Trivandrum. So that type of third intervention we have come up in 2019 and 20. And in 2021, what we have done actually, that is the 4th stage of implementation of impact-based forecast, where we have gone for a dynamical platform. To begin with, we have gone for the tropical cyclones with the National Cyclone Risk Mitigation Project. We have a complete dynamical platform where we have got the data on socioeconomic indicators, data on geospatial, and data on the primary hazards, secondary hazards, and tertiary hazards. So all these digital data collected for all the coastal states are compared, and analyzed with a system in a dynamic platform, and as a result, we can provide what type of dynamic impacts will be. And this data has to be uploaded and updated in a regular manner, at least twice in a year, because of the improvement in socioeconomic conditions. Similarly, we have gone for the dynamic informations about the impact with respect to flash floods, with respect to the heavy rainfall. But still, the road is open, and we have to complete, as mentioned and visioned by former Secretary Dr. Rajivan Saab, we have to go for complete transformation and dynamic implementation of the impact-based forecast for each and every severe weather event, involving all public-private partnership and state governments, where we can get all types of data for socioeconomic and geospatial conditions. So this is just an example of how we have gone for implementation of heavy rainfall in different stages. Just like cyclones, we have got 4 stages of cyclone warning. Here also we introduced 4 stages of heavy rainfall warning, like heavy rainfall watch, heavy rainfall alert, and heavy rainfall warning. And we are providing this information. It is certainly helped. And I can tell you, I appreciate the forecasters and modelers for the country. We have been enabled to provide the heavy rainfall impact-based warning in such a manner in 2021 that no significant heavy rainfall event was missed during this year. This is just an example of the flash flood guidance and for flood guidance what we provide actually. So in the recent time, there was a demand to better manage the floods by the Minister of Home Affairs, even Honorable Home Minister intervened. And as a result, we try to provide seasonal forecast and extended range forecast, and also the short to medium range forecast for occurrence of heavy rainfall and flood accordingly. So quantitative precipitation forecast were provided to Central Water Commission, but finally what we found that the short to medium forecast is more appropriate and accuracy of that level should increase. And accordingly, the number of days for which quantitative precipitation forecast was being provided earlier, that was improved from 3 days to 5 days. And for 153 river catchments, we are providing the heavy rainfall warning and quantitative precipitation forecast for next 5 days. Similarly, we have gone for the flash flood guidance. About 30,000 watersheds in the country are being provided every 6 hours, the possible occurrence of the flash floods. For city-specific information, we have come up with the flood warning system for city of Mumbai and city of Chennai, and now we are providing and trying for city of Kolkata and Delhi. So here also we have the system considering all the aspects of the floods like soil moisture and soil characteristics, and also the rainfall in the past, present, and the future. And accordingly, a flood depth is calculated utilizing digital elevation model and is provided to city municipal corporations. For thunderstorm warning, as I was telling you, we have come up a long way. In 2018 April, we started this process when actually severe thunderstorm affected Northwest India and 80 people have died in one incident. Thereafter, this was taken up in 2019. We started providing lightning warning, and also with the help of Indian Air Force and in isotropical meteorology, we could provide information about the detection based on the ground truth of lightning detection system. And we also come up with the rapid system of satellite where you can have the geospatial information with respect to all. And as a result, at present, we are providing the nowcast for severe weather events, including lightning and thunderstorms, for 1,084 stations and all 739 districts. And this modeling system, what we have developed, you can see in this diagram. On the left-hand side is the forecast from the model, and the middle diagram shows the occurrence of lightning in red color. You will find that the modeling system has very well reasonably captured the lightning which occurred in eastern parts of the country. For the heat wave and cold wave, we have come up a digital platform, GIS platform. At present, you can find out the information not only about the temperature, what is occurring now, you can also find out the departure from normal, and you can find out the hot day, heat wave, cold wave informations, not only for today, but also for the past 5 days, and also the coming 5 days. So, and all these informations are available in IMD website. So with all this intervention, we also improved our early warning system. Just in the inaugural function, we have listened to Rajwan Saab about the need for end-to-end early warning system. When you consider the end-to-end early warning systems, we have the two targets. One is the community, that is community-based early warning systems. Other one is the disaster managers. So you cannot have the same approach for the community and the disaster managers. For disaster managers means for the NDMA, MHA, state emergency operations centers, etc. And for community, you need the press and electronic media and also the social media, etc. So both has been targeted in recent years, and we have been able to upgrade our early warning systems dissemination. What you find that actually there has been the conventional approaches like telephone and mobile phones, telefax, etc. And also we have got the VHF, HFRT, police wireless, and aeronautical fixed terminal network. But global telecommunication system, these are all conventional. But we have come up with the social media, mass media like AM radio, FM radio, community radio, and also the mobile apps like Damini, Megdut, and Mosam. We have also come up with the development of RSS feed or APIs. You will be happy to know that most of the states are availing our API and taking the digital data on early warning about the severe weather events. Not only that, we are a part of Global Multi-Hazard Alert System, GMAS, of the WMO. By that, we also provide all our early warning with respect to severe weather events to all the countries and all the agencies involved in humanitarian activities like UNDP, UNEP, etc. So I will conclude here that we have come up a long way in the Ministry of Earth Sciences with the help of the sister organizations. IMD is now able to provide the severe weather impact-based early warning for all types of severe weather. But still, there is a scope to further minimize the loss of lives and properties And for this purpose, we need to take some of the new initiatives, and already we have initiated all these initiatives like crowdsourcing, artificial intelligence and machine learning, digital forecasting, impact-based forecasting, and risk-based warning for all types of severe weathers in a dynamical platform. And then, of course, last mile connectivity in association with other agencies in the country. So the final goal, therefore, is that we have to convert all the data. People talk about big data. Minister for Science and India Meteorological Department has really a big data, a source of big data. We have got a lot of data with respect to satellite, with respect to radar, and the ground truth. This big data has to be converted into value. Yes, there is data science. Yes, we have to utilize the data science. We have to utilize the high performance computing systems, and we have to utilize the all tools and technology like the clouds computing and also the artificial intelligence. So the objective is that just like we convert petroleum into petrol, similarly here the data has to be converted into a value. And for this purpose, we have to adopt the two technologies, a dual engine concept. One is the enhancement of numerical weather prediction systems, that will be modeling, that is going on and that will go on. At the same time, we have to adopt the new tools like data science, artificial intelligence, the cloud computing, etc. And both should complement with each other, and both should meet at one point, and they should enable us to convert the data into the value. And finally, I just want to say that while doing all these things, human expertise cannot be neglected. There are a lot of roles of the human intelligence. You cannot go for only the artificial intelligence. For the human intelligence, what you need actually, as we are planning for impact-based forecasting, the forecaster will have a new role at present. He will have to have more interactive role with publics so that public awareness and outreach can be improved with the press and electronic media. And also we have to develop the outreach materials for this purpose. And we have to go for augmenting our information of short to medium range, extended range, and seasonal range. We have the forecast in 3 ranges. The forecaster now should understand all the 3 time scales and how to complement all these 3 time scales and provide the early warning. By that way, we can provide more specific and more lead period information for management of disasters. So therefore, what I want to say that in this changing scenario, we have to go for a meteorologist, which is a smart meteorologist. And the smart meteorologist will be characterized by its capability, credibility, and capacity. So it should be an integrated, authoritative voice. He will not speak only about the weather. He will also speak about impact of weather. He will speak about the action to be taken by the various agencies. So his role will be not only the weather forecasting, but also his role will be the advisory. The role will be the partnership with various stakeholders, customer services, production, innovation, and applications. So thank you very much.
Okay, thank you, Dr. Mahapatra. You can ask anybody having some quick questions or 1 or 2 suggestions or comments, please. Okay, then, and that if there is no comments, I think we are thanking. Any suggestions? Okay, okay, please.
I hope I'm allowed to ask the question being programmed at the Meteorological Department. This is some small question I wanted to ask Dr. Mahapatra.
Please hold your mic.
Yeah. So, as you gave a very talk and covered all the aspects, and as from your talk, like we could know that it's the models, human role, as well as the coordination that plays a lot of big role, in of a certain forecast. So my question is, how much you will attribute the successes and failures to modeling, to role of a forecaster, and the coordination? So what percentage you will attribute to each for the success and failure of the forecasts which are disseminated by IMD?
See, thank you, Dr. Kamaljeet. So all the 3 are having the major roles in improvement of the early warning services. But at the same time, all the 3 are complementary. So role of forecasters, role of modelers, and role of coordination are equally important. And all the 3 are growing. There will be limitations with respect to modeling, with respect to observations. Also, there will be limitations with respect to communication systems. But the role of forecaster is to coordinate with all agencies and to come up with a solution. And that solution will certainly depend upon all these aspects, but that is improving and will improve it further. So therefore, collaboration is key to success. Not only networking and collaboration among the scientific organizations and the R&D carried out targeting this direction will certainly help in future. And I hope with the active leadership of Minister of Earth Sciences and constituent bodies under the Minister of Earth Sciences, we have to not only coordinate and collaborate within IMD and within Minister of Earth Sciences, but also have to go for collaboration, coordination with other agencies in the country and outside. So that will help. Collaboration will be key to success.
Okay, I think because the time is very short, I think, thank you, Dr. Mahapatra, giving a very nice talk. And we will we can move on to the next talk. I think Professor Joseph, you want to make any comments, sir? Thank you, Dr. Mahapatra. Thank you very much. In that case, I think we will move to the next talk by Dr. M. Rajivan, former Secretary of MOES, on the role of oceans on the variability of Indian monsoon. Dr. Rajivan, please go ahead.
Thank you. Thank you, Professor Mohan Kumar. I am very happy to give this presentation on role of oceans and on Indian monsoon variability and new insights, especially in the session where Professor P.V. Joseph is chairing, and I have a lot of gratitude and respect for him, because I learned my basics of meteorology, alphabets of meteorology from Dr. P.V. Joseph when he was the Director of Training Division in IMD when I joined as a young IMD recruitee in 1985. So big pronouns to Professor P.V. Joseph. So I'll be talking about the role of oceans on Indian monsoon variability, and especially, of course, we all know that oceans play an important role in monsoon variability. Thousands of papers must have been written, but question is why what is new? So I'll be bringing out some gap areas and what are the new insights now which have come out from new research papers during recent years. As all of you know that we have global monsoons, we have monsoons in different parts of the globe, and the Indian monsoon is one of the major global monsoon system, and monsoon covers almost roughly half of the tropics and hosts about 65% of world population, because it covers both China as well as India. And in India, we have two monsoons. One is southwest monsoon, which is from June to September, and another is northeast monsoon, which is October to December. And and monsoon also, we all know that it varies in different time scale, starting from diurnal. Diurnal means 24 hours. Within one day itself, there's a lot of changes. And synoptic means 4 to 5 days, mainly contributed by synoptic weather systems like tropical cyclones or monsoon depressions, etc. And intra-seasonal is about 10 days to 20 days to 25 days within the monsoon season. Intra-annual means year-to-year variation, which is also very important and mostly largely influenced by global oceans. And also we have observation suggesting that there is a lot of multi-decadal variations of Indian monsoon. And in today's presentation, I'll be talking briefly about southwest monsoon on the role of ocean, and especially on Pacific influence. And but at the same time, I'll be contributing I'll be talking a little more in detail about northeast monsoon, because I thought it is very apt to give a talk on northeast monsoon, because this is the northeast monsoon season, and in South Peninsula there's a lot of plenty of rains are happening, plenty of extreme weather events are happening, and it is being hosted by KUSAT in Kochi, where northeast monsoon is very important. So, and also it's a relatively gray area when compared to southwest monsoon. And firstly, southwest monsoon, we all know this time series of all India rainfall. it has about 10% variation from year to year. And it's all internal variability is mostly influenced by tropical oceans, especially the equatorial Pacific, and also other slowly varying conditions like snow cover, soil moisture, and also sea ice. And this is the one correlation pattern between monsoon and the mean OLR, which says that Pacific Indian monsoon is largely influenced by Pacific Ocean. You can see the positive correlations over there. That means positive SSTs will give you positive OLR. There is less rain. And over the equatorial Indian Ocean also there is a good correlations, both from eastern equatorial Indian Ocean as well as western equatorial Indian Ocean. There is a kind of a dipole which is very similar to Indian Ocean dipole even. And there is a lot of papers written by Professor Sulojana Gadgil and group on ECHINO, basically equatorial winds, the relationship between Indian Ocean equatorial winds as well as Indian monsoon. And of course, ENSO monsoon relationship has been studied by many researchers for the years together starting from 1980s. The first paper I remember from India was written by Professor D.R. Sikka Saab in 1980. And so we know that both the Pacific Ocean as well as Indian Ocean influence monsoon variability. But if you really talk about ENSO relationship, Pacific Ocean and Indian monsoon relationship, there was a famous paper in 1999 by my good friend Krishna Kumar. It was a classic paper, and it is now citation is more than 1,000 citation. Now it has appeared in Science, and which revealed the weakening of the relationship between Indian monsoon and ENSO. And that was that you can see that the line goes beyond 0.42 or so. And so that means that during those years, monsoon relationship with the ENSO was very weak. Yeah, so he came out with an explanation why it was weak, etc. But after a few years, again, now if you really take the recent years, the relationship has been strengthened. The question is that so you can see that whole all the years there's a huge multi-decadal variation, kind of a epochs in which relationship is more. Relationship is strong, then relationship is weak. So again, we are going into a relationship epoch in which relationship is becoming more and more stronger. The question is why? And so there are a lot of hypotheses, and it's a relatively new area because it has been observed very recently. And also there is, so I will come to that aspect a little later, but so Indian Ocean also plays important role, as I told that for some of the papers by Professor Sulojana Gadgil on equatorial Indian Ocean winds. But there are also sea surface temperature, warm water volume, heat content in the tropical Indian Ocean also play important role. This is a paper by Srijit, which shows that composite of excess monsoon and poor monsoon, deficient monsoon. You can see that during starting from June and East equatorial Indian Ocean, you can see that it's a negative anomalies of warm water volume in the excess years, whereas in the deficient years it is positive volume. So it's a more heat content in the East equatorial Indian Ocean, which leads to poor monsoon. And also Atlantic Ocean, there have been a lot of studies now. Probably we all know that the multi-decadal relationship between Atlantic multi-decadal oscillation, AMO, and Indian monsoon. And but our internal time scale, this paper we have written with 2008, and which says that there is a relationship between Atlantic Ocean and Indian monsoon, and we have been using this kind of indices in our monsoon prediction statistical models. And recently there is a lot of interest in again Atlantic Ocean, for some Atlantic Atlantic dipole also is being linked to Indian monsoon, but we need to really study more on the role of Indian Atlantic Ocean and Indian monsoon. And also we know that there are years in which El Nino years we have droughts, it's very common. But there are El Nino years in which we don't get, and there are drought years which are not associated with the El Nino years. For example, 1974, 79. These are also two good examples. 66, for example. These are all years in which we had droughts, but it's not El Nino years. The question is why. And so there was a brilliant paper by Bora et al. In 2020 last year in Science, which says that Atlantic Ocean again plays an important role, not through SST, probably through SSTs, but basically through the Rossby wave pattern, which is emanating from Atlantic Ocean, passing through middle latitudes, and you get a standing Rossby wave pattern in the northern parts of India, which can, especially in the second half of the monsoon season, which can lead to drought. And because the trough in the upper troposphere can bring cold and dry air to Indian monsoon, and it can suppress the convection over the Indian monsoon region. So Atlantic Ocean basically plays an important role. And I'll come back to this is the important question, why the secular relationship between ENSO and Illinois is, ISMR and Illinois is stronger again. And so there was a recent paper appeared in this year, so re-examining the Indian monsoon rainfall ENSO relationship from its recovery in the 21st century, so by Chinese group. But it's, I personally feel it's very interesting paper. Of course, it's a beginning, so we need to really work on much more on this kind of this analysis. And what they used is instead of correlation, we normally do a correlation analysis for understanding the secular variation of some 21-year running mean, running correlations, etc. But here they use this a matching index, which they call, and nothing but it's a product of ISMR standard deviation and 3.4 standard deviation. You can calculate every year, and that is the time series you can calculate, and that they use it for doing the study. And if you really see the correlation pattern for different decades, you can 61 to 80, then 81 to 2020, and 2001 to 2020. You can see that in the first phase of 61 to 80, there was a lot of correlation. You can see the all blue color in the Pacific, so that means the Pacific Ocean was very much linked to Indian monsoon. And the next phase was 81 to 2000. The phase, the relationship will become very big. That's the period Dr. Krishna Kumar wrote that paper. And again, now if you really see the last 20 years or so, the relationship is again has been strengthened. The question is why? And there are a lot of changes associated with the SST. There are a lot of changes in the winds also, which is also reflected in this figure. And so what they are finding is the top figure shows basically time series of ISMR, and 3.4. First you take the first 20 years is correlation is minus 0.68, then minus 0.26 is statistically insignificant, then again minus 0.60. So there's a lot of epochal variation. And if you really see the figure B is nothing but the time series of MI, and which clearly shows the internal variation. But if we really take the 11-year running mean or 20-year running mean, there's a clear signal of it is intensifying and is strengthening. So what they have done is they analyzed a lot of EMIP model. EMIP model is atmospheric model intercomparison project that has been going on years together. But in CMIP 6 exercise, they have done again EMIP runs, which they use the observed SST to run the model. It's atmospheric model, but they use observed SST to run the climate runs. And they used many models, and they found out some models are doing extremely well. They try to analyze it. This kind of relationship is really reflected in the EMIP model, what we have seen in the observations. So the answer is yes, we have seen, and you can see the black color. You can see that the correlation is stronger in the above 90 than, and you can see that again the correlation is weakening. Again, the correlation is strengthening. So the EMIP model is really able to reflect or able to project the observed variation of the relationship. And EMIP runs are basically based on SST. So the hypothesis is that SST is playing an important role in this kind of weakening and strengthening of the relationship. And if you really first figure, you can see that this is the correlation of MI with SSTs, which clearly shows the Indian Ocean, the correlations are strongest in the Indian Ocean. So they size in the Indian Ocean may be playing an important role. And so what they did is, I will go to this straight away to go to the C and D. What they have done is, when Indian Ocean was warm and Illinois is there, and you take the years in which the Indian Ocean is warm and Indian Ocean is cold. So you plot this scatter plot of 3.4 and ISMR in two categories, where the Indian Ocean was warmer and Indian Ocean is colder. The correlation is pretty high when the Indian Ocean is warmer, is minus 0.89. Whereas when the Indian Ocean is colder, the correlation is only 0.06. So they suggest that the Indian Ocean, the warming of Indian Ocean plays an important role in strengthening the relationship between 3.4 and ISMR, and which they have found out in the model runs also, EMIP run also. This is a scatter plot between correlation of model, MI model and TOI model. That means MI index and the tropical Indian Ocean model index and in the model, and versus correlation of MI from the model and MI from the observations, which clearly shows that Indian Ocean playing an important role. And the well-known negative relationship between ISMR is actually conditional on the TOI warming. tropical Indian Ocean warming. A warm TAO may facilitate a stronger relationship, or cold TAO may lead to a weaker relationship, and which they have established further using a. So we can have 4 conditions. So and 3.4 is more and TAO is more, and 3.4 is more but TAO is less. And this is the basically these two are for basically for La Nina conditions. So I will talk about only these 2 conditions. You can see that when 3.4 is more and TAO is more warmer, you can see that the stronger SST is here. And also you can see that the equatorial Indian Ocean, the stronger easterlies are prevailing over this region. And also this is the famous the 200 hectopascal divergence fish, which clearly shows a kind of a descending motion over here, and a kind of ascending motion here. This is associated with El Nino, and which clearly shows that descending motion means it's basically it affects the Indian monsoon. So and the easterly winds over here and during monsoon season is basically it means that it is opposing the southwesterly winds. So it is basically indicating a kind of a poor monsoon. Whereas in this condition, the relationship is not this condition. This especially the Indian Ocean, the winds are not highly. It's not very adverse. Winds are not there in this Indian Ocean, and so they clearly suggest that tropical Indian Ocean warming is much more important in relating in El Nino with the Indian monsoon. So they are hinting that when you really, if you develop a prediction system for monsoon rainfall, you should see whether Indian Ocean is warm or not. So the same scheme we cannot apply it through all the years. So we have to bifurcate whether tropical Indian Ocean is warm or cold. Accordingly, the relationship should be extensively used. So both for empirical prediction as well as for GCM predictions. So this is an interesting paper. I am very sure that a lot of leading papers will come now subsequent to this. And if you really see how these relationships are reflected in the models, we all know this also is well known. This is the figure A. It's basically the SST and the ISMR correlations from the observations. Then this is from the model. You can see that from observations and from models, the models generally predict. This is MFCS, the model which IMD is using for seasonal forecast, which was developed by ATM, the seasonal prediction group. You can see that El Nino is much stronger in the model. So the El Nino relationship, and whereas in the equatorial Indian Ocean there is a strong signal here of warming, kind of a negative correlation, which is not at all reflected in the. So the models do well in the SST correlation of over the Pacific, but much a stronger relationship of ENSO. But over the Indian Ocean, the models play a very poor role, and they don't very well predict very well. And this is also by paper Prasan that also they have analyzed many climate model of. And also they tried to do a MME of all models, and they found that this kind of Indian Ocean still they produce stronger correlation with the equatorial Pacific, but while Indian Ocean relationships are not captured very well. And this is also reflected in the climate projection scenario in the CMIP-6 model. This is the latest CMIP model for climate change scenario. This is by paper by Professor Goswami's group in from Guwahati. Cotton University, and she has written a paper in which they analyze how the climate models have progressed from CMIP 3, CMIP 5, and CMIP 6. This is the GPCP rainfall, and this is the difference between the model and observed. And you can see that there's a lot of dry bias over here, or Indian Ocean, Indian region, subcontinent, which is well known, and it is available. It is there in our MFCS model also, and which is also seen in CMIP 5, and is also seen in CMIP 6, but probably the intensity of the dry bias is reduced. So the dry bias is a systematic pattern which is seen in all the climate model. If you really plot the latitude versus rainfall, you can see that this is the observed rainfall, the black line, and the remaining all models. You can see that over equatorial Indian Ocean, the models give more rain, but whereas in the monsoon trough region, the model rainfall is much less than the observation. So it's a systematic difference bias in the model lands, and they attribute to the systematic bias in the SSTs of CMIP model. You can see that here in the tropical Indian Ocean, the models perform. Models do predict much more SST than observations, where or in the Bay of Bengal and Arabian Sea, they predict much less SST. So this kind of biases can lead to the mean position of ITCZ. Monsoon is nothing but northward propagation of ITCZ. So it really affects the northward propagation as well as the mean position of ITCZ in the climate model. So what we need to really improve the dry bias could be by improving the SST bias of the Indian Ocean. So what I am highlighting is in addition to Pacific, Indian Ocean plays an important role in the Indian Ocean monsoon variability, which we need to really address. But this is a paper, this is the result Dr. Krishna has sent me recently. They also have a system model. They're trying to understand how the Indian Ocean is reflected in their model. Surprisingly, he was suggesting that their model, the Indian Ocean dipole relationship is much better. And so the paper is yet to come. So this is very interesting to see that why in this model, particularly the ATMS system model, the Indian Ocean relationship is coming very correctly. So we need to really understand why. Well, now I'll move on to Northeast monsoon, another 10 minutes or so. I'll talk about this is the Northeast monsoon is nothing but the retreating phase of Southwest monsoon. Trough comes down and stays there for a few days and goes down again. And so when the trough is there, we get a lot of rain. And this is IMD's greater rainfall data, which clearly shows the monsoon rainfall pattern over here. Along the coast, very close to the coast, the rainfall is much more than goes down slowly. And this is the same rainfall pattern, but it is for a larger region. It is from the gridded merged rainfall data. And this is the mean monsoon, and this is the internal variability. And you can see that El Nino years, La Nina years, and also Philippines. And variability here is almost 25%. When compared to Southwest monsoon, which is just 10% of standard deviation, whereas Northeast monsoon much large standard deviation, 25%. That's why we have a lot of difficulty in predicting the internal variability. So that's one case, one issue. And another issue is large variability, and also is associated with the El Nino La Nina year. There's no very systematic pattern, but if you really analyze a large scale, long time series data, we do find that relationship is when El Nino is there, we do tend to get more rainfall over Northeast monsoon, whereas the Southwest monsoon just it is reverse. When El Nino is, we do tend to get less rainfall. There's a little difference in the Northeast monsoon. The question is why? That's number one. But that relationship also is not very stable. So I will describe why it is. And if you really see the 21-year running mean of the mean rainfall, you can see large multi-decadal variation, large scale variations are there. And now we are in the lower phase, especially because 2016 to 18, they had large scale drought. And you must be remembering that Chennai had a lot of problem in even drinking water. So ground storage water and all has simply disappeared. And mainly because of that, dip has come. And so this is a lot of large scale multi-decadal variations there. And there's a paper by Kodesh Rao, it's I think an A-team group, and they say that they're trying to analyze how the extreme rainfall events are happening in Northeast monsoon. They say that this observation, which clearly shows the events are increasing, and these are from the models. They use two scenario, I think RCP 4.5 and RCP 8.5. And this is I think the green line is RCP 4.5 and blue is RCP 8.5. Both the scenario shows that in future, the extreme weather events over Northeast monsoon also will increase. Southwest monsoon is all well established. We know that during monsoon season, June to September, we tend to get more and more extreme precipitation. But that is going to happen in Northeast monsoon also. So states like Tamil Nadu, Kerala, Andhra and Karnataka should worry, because this trend will be troublesome for them. Only thing is because many students may be attending my talk, I want to caution you that we normally tend to use more RCP 8.5 scenario, which is a very extreme scenario. I suggest that you should not use, because it is not really realistic. You may get a good result and you can easily get published papers, but reviewers will be very happy because signal to ratio in RCP 8.5 will be much better. So usually you will get good results and you can easily get published papers, but it's not really a good way of doing research. So RCP 8.5, I think you should not use. And Dr. Krishna was suggesting that in the latest IPCC assessment, they not used RCP 8.5 scenario. Well, and this is the correlation of Northeast monsoon rainfall with the SSTs. We can very clearly shows that over the equatorial Pacific, it is warm. It is a positive correlation, whereas in the southwest monsoon, we got negative correlation. That means more SSTs here will give a more rainfall over northeast monsoon season, northeast monsoon season. And also very interesting to see that the positive SST correlation from the North Bay of Bengal. So Bay of Bengal is also playing an important role. And there also, of course, large scale multi-decadal variation of relationship. You can see this is from 61 to 90, and the last second one is 91 to 2. So recent years, again, this correlation has disappeared. So the relationship has become very weak now. And so I will, so if you really see this correlation pattern, this is the same time series which I shown earlier. I cannot see here the end here from here. So if you really see the last few years, these blue lines are all La Nina years. So La Nina years, we expect that the monsoon will be poor, but you get 2 years. This is 2010 and I don't know. It is a 2005. The 2005 and 2010 are the 2 years in which we had extreme heavy precipitation, but it was those years are La Nina years, and also 2016 was a La Nina year, but we had a poor monsoon. And this year is a La Nina year. It's a cold phase of La Nina year, and so now in Pacific. But this year already monsoon is especially in South Peninsula. The monsoon is very on a positive side, so we may get another 40 to 50% above normal rainfall. So question is, in La Nina years, why we should get the excess monsoon? And if you really closely follow this time series, and you see that this kind of anomalies we see only when this SST relationship with the Pacific is weaker. So this is losing last 20 years or so, it has become weaker. So you can expect even La Nina, you can expect a heavy precipitation over northeast monsoon. So it's very interesting to further study this kind of aspects. And if you really see the 21-year running correlation of northeast monsoon, 3.4, you can easily see the beautiful multi-decadal variation going up, going down, going up, going down. So there is systematically there is some physical process is happening on the relation between 3.4 northeast monsoon. I would like to suggest that it is the regional process of Bay of Bengal or Indian Ocean is playing an important role in modulating this kind of relationship. That's what I would like to present in few next slide. And we have studied one of my first student, probably he was the first student of my PhD student, and 2007 he published in Climate Dynamics, and this is a correlation between 51 to 75. There's nothing, but again correlation has come. So he wrote a paper on the recent strengthening of the relation between ENSO and northeast monsoon rainfall over South Asia, and we try to give a clarification why the strengthening should happen. And also here you can see that a lot of northeasterly winds are happening. The question is, during southwest monsoon, we are getting a negative correlation, but during northeast, we are getting a positive correlation. Why? Mainly, it's a regional process which is playing an important role. And northeast monsoon, the mean pattern is easterly winds, and during El Nino years, what really causes it gives you additional northeasterly winds add to the mean pattern. It gives you large scale moisture flux incursion to the South Peninsula and gives a lot of rain. So that's the theory we are given. And a very long time back, about 13-14 years back. And so this is a 2010. I am saying that it's a El Nino, but we had a lot of excess monsoon here. And if you really see the 850 millibar pattern wind anomaly, so this is not wind anomaly, this is a mean wind. You can see the beautiful trough here crossing across the South Peninsula, mean ITC set kind of thing, and strong jet stream in the south close to the equator. And this mean pattern has really caused the excess rain monsoon over northeast monsoon, over South Peninsula. And SST, if you really take, it was a beautiful La Nina year, whereas in Indian Ocean, you can see that it's all positive. So Bay of Bengal must have played a very important role in modulating, in spite of a La Nina year, they're playing an important role in modulating the excess monsoon during 2010. I tried to do it for 2021 also. This is 21 monsoon season. You can see there are a lot of excess monsoon. The same pattern of 2010. You can see that beautiful jet stream here, and also the beautiful ITC set here going across the peninsula. And the same thing, we have negative SSTs here, but the Bay of Bengal is much more positive. So Bay of Bengal seems to be playing an important role in modulating northeast monsoon rainfall in recent years, especially during La Nina years. And surprisingly, very surprisingly, I should admit that Indian IMD has given a northeast monsoon forecast for this year. In spite of a La Nina, they have given an excess monsoon here. And except for off of or coast of coast to Chennai, of course, they have given a kind of a below normal rainfall, but Chennai is really flooded. But of course, we in seasonal prediction, you cannot expect this kind of granular information. But overall, they are giving a kind of a positive anomalies above normal category over South Peninsula, which is very interesting. So we need to really understand why these models are. This is a MME model, MME of 7-8 models. So the question is why these models are really projecting a good monsoon. And another important study is so you can even in El Nino years, we get some years we get good monsoon, some years we get poor monsoon. The question is why? In some years only we get poor good monsoon in El Nino years, some years we don't get. So this is the again SST and wind pattern here, and clearly it shows the wind pattern is playing an important role. This is the wind pattern during El Nino years in which northeast monsoon was positive. You can see the big difference between these two panels. You can see that the Indian Ocean play an important role, especially the availability of northeasterly winds and also kind of a divergence. Of course, it can be triggered by a positive IOD. Also, positive IOD, in positive IOD, what happens is you have a cold SST anomaly here, then you get a kind of a divergence, and that also can cause this kind of anomalies. So we need to really studies. We really understand what is the relative role of IOD in this kind of situation. So my message is that Indian Ocean plays an important role. Bay of Bengal plays an important role in northeast monsoon season. And when we talk about flood season, we also know that 1960 to 18, it's a paper by Vimal Mishra. Today you are given an award to him. And he's a very brilliant young scientist working in IIT Kharagpur. He has written a paper in Environment Research Letters of 2016. 3 years consecutively, they had severe water deficient rain, and that has related to that has caused a severe water shortage over Chennai. And this is the total water storage from GRACE. GRACE is a satellite of measuring gravity. From there, you can calculate what is the water storage under the ground. Well, the question is, are these relationships are picked up by the models? That means the El Nino years, we should get good monsoon. La Nina years, you should get poor monsoon. The answer is no. We have written a paper in 2012. I think the people who want to do northeast monsoon should read this paper. It's very detailed, very interesting paper. And we wrote that the observed rainfall and the multi-model rainfall, the correlation is very poor. The model really don't simulate anything of northeast monsoon. Model is very poor. Of course, the models are really relatively good in southwest monsoon. When it comes to northeast monsoon, the models don't understand the dynamics of northeast monsoon of India. And so we need to really understand. So the problem is, if you really see the observation of the top figure, you can see the rainfall and 3.4, you get a positive correlation. Whereas in the model is just opposite. So just opposite, it is all negative. So because of that, ultimately we don't get a good model skill of projecting. And this is a paper which was written almost 10 years back. But this is a recent paper in Krishnamurthy et al. In Journal of Climate, this US group. So they also try to understand. They try to understand the 2005 Chennai floods, whether it can be related to some kind of whether it can be climate change, or it can be associated with El Nino, or it can be associated with a local phenomena. And they also found that models are pretty bad in simulating the mean relationship between El Nino and the mean monsoon rainfall from the model and observations. The relationship is very poor. The model don't really reproduce good northeast monsoon. You can see even the mean patterns are very poor. This is the model. This is observation, and this is the model. So you can see the very poor. So their conclusion is neither El Nino nor La Nina enhances the probability of extreme floods over Chennai. So basically, a warm Bay of Bengal tends to increase the odds of occurrence of extreme Chennai like floods. And this is the same thing again. Recent paper. This is also same thing. They analyze many models. APCC model. APCC model is basically from South Korea, and they have. So they also found that none of these models are reproducing even the mean pattern of northeast monsoon. So models have a lot of issues in reproducing northeast monsoon, whereas southwest monsoons in the models are doing far better job. Still, it's not optimum, but still better job. So we need to really understand why Indian Ocean is important. So we need modeling studies. We also need a lot of observations. We also need a lot of observational campaigns. And so as far as observational campaigns, we know from a long time back, we had Indian Ocean IOEE, and the second phase IOE is going on now. Then we had a so-called Indo-X, in which US and India collaborated. Then recent years we had BOMBMAX, which is of Bay of Bengal, then RMAX, which are basically Arabian Sea. But last 4 or 5 years we had an Indo-US collaboration under monsoon mission, and also into UK collaboration under monsoon mission. So this is a new proposal which Ministry of Science is pushing. When I was secretary, I have been steering this proposal. And from India, I think Dr. Srinivas, Director of INCOIS, will lead this proposal. And there's a lot of participation from University of Massachusetts, WHOI, and Scripps Institute, and also the NOAA PML. And from India, there are many organizations will be. So this observational campaign for next 4 or 5 years will be focusing more on Arabian Sea, and try to understand the model, the dynamics of Arabian Sea, how observations are really will help to improve the models. So this kind of observational campaigns are very much required, and I'm very sure this Ministry of Sciences will continue to support this kind of initiatives. So they have different common. One is a modeling component, one where they have biogeochemistry, and also of course they have beautiful observational program, both atmosphere as well as ocean. A lot of parameters they are going to observe. So this kind of studies are required. Of course, they also need to really focus more on modeling aspects of Indian Ocean. So this is a conclusion. I will come to the last slide. So a comprehensive research roadmap for better understanding of the role of Indian and Atlantic Oceans on southwest monsoon variability, and to reduce systematic errors in the coupled models. So we need a lot of systematic observation over the Indian Ocean. Focus modeling efforts are required, and also focus observational campaign, which just now I described. So this kind of observational campaigns are also required. And northeast monsoon, I should really tell you that it's a really a gray area. We have been focusing more on southwest monsoon. It's almost like a Hollywood film. But sometimes Bollywood film also play important role. So we need to really understand. But northeast monsoon also is important for all of us, and especially during the recent years, there's a lot of floods are happening in South Peninsula. We need to really understand more. But a lot of gap areas we don't understand very well. So a lot of good research should come out in northeast monsoon variability, and understanding the variability role of ocean, regional local processes, synoptic scale like tropical easterly waves. And mostly northeast monsoon we get more rain, not to kind of a tropical cyclone, but even tropical easterly waves can cause. And the question is, do we know how many tropical easterly waves occur in a northeast monsoon season? We don't have statistics. Simple. Because tropical easterly waves or Atlantic is well studied. We know easterly waves of tropical Indian Ocean, tropical Atlantic Ocean, but we don't know about Indian Ocean. But we know very well tropical easterly waves plays important role. But we don't even a statistic how many tropical easterly waves happen during a monsoon season. So it's just an example. And of course, we need to improve the prediction efforts in all time scale. So I'll stop here. Thank you.
Okay. Any questions, clarifications, or something?
Yeah, please.
From the audience.
Sir, actually, I just wanted to know that extensive period of the latter part of the month, like 2019, 2021, yes, monsoon overstayed up to October also, that it will travel very delayed all over the country, and final also northeast monsoon also at 31. And secondly, even northeast monsoon, you can see last year we have a January, very unusual. Again, overstaying and extensive of extending to January. What is the role of the Indian Ocean?
Yeah, of course. I cannot tell you the physical process, but I also personally feel that Bay of Bengal, warm Bay of Bengal may be playing an important role in extending the southwest monsoon as well as extending the northeast monsoon. So we need to really understand we need to really analyze the observations. And also we need to do a lot of model simulation, sensitivity studies on understanding the role of Bay of Bengal on both the southwest extension of southwest monsoon as well as the extension of northeast monsoon.
Any more questions?
Pardon?
Any more questions? Just I am asking. Okay, this is not audible. I think, please. Yeah.
I was further adding that for the general public, for media and others, can we say that it is a part of the climate change or something?
Well, you see, climate change is it's a easy way to use anywhere. And whenever you don't have an explanation, we normally say it could be climate change. It's a big basket. You can put anything inside. Even if India loses in a cricket match, you can say it could be due to climate change, not because of Indian players. And so climate change is really a big basket. So if you don't have an answer, well, it's a climate change. So it's easy to blame. But I am could be. I'm not saying no, but it could be, but very difficult to say.
Sir, I have a question, sir. Yeah, very excellent talk, sir. And also you have highlighted many research problems to people in it. Actually, two questions. First one, actually, when you are referring that Atlantic Roll question, because you just also mentioned that it is likely to impact more toward the latter part of the season. So that what could be the reason? That is number one. Number two is the Indian Ocean basin-wide warming is playing major role. So, but we are not distinguishing east and west. Does it indicate that?
No, the ocean. So both are different. Both are different. So what I was talking is a basin-wide warming.
Yeah. So that means whether the Indian Ocean role is also a little bit less significant.
No, it's significant. Only thing we need to understand what exactly is happening. Whether it is a really dipole kind of events or it's a large-scale basin-wide warming, which is really causing this kind of relationship. So we need to realize. So what today I talked was basically basic basin-wide warming.
And what about the
Atlantic, I'm not sure. I'm not sure. What we during those years 79 and all, the generation, the genesis of this middle altitude Rossby wave pattern, it starts only in the second half. Yeah, and you know even in monsoon books in IMD, then August is the monsoon month in which you get a lot of breaks.
Yeah.
August and September. Yeah. So there could be some reasons why. Yeah, thank you.
Okay, there is one question from the chat box message. Sir, I will read that. Sir, my question is regarding the Indian Ocean warming. All the CMIP's models show excess rainfall over equatorial Indian Ocean region. Can we say the coupled models fail to represent the upper processes over Indian Ocean?
Yeah, that's true.
That's by NCMRW from Dr. Mohan. I think he has asked the question.
Yeah, that's true. So that's why the models show a large bias over Indian Ocean and tropical Indian Ocean, and that basically it predicts more SSTs over here when compared to observations, and that forces the ITC set to stay back there. So if you really see the rainfall there, the rainfall over the equatorial Indian Ocean is much more larger when compared to the the Indian subcontinent. So the physical process probably may not be really resolved in the coupled climate models in the Indian Ocean. So we need to really understand what really why these models really fail. What physical processes are not being simulated very well.
No, I have got one question. Even when we are during the time of the May, June, early June, if you are having a depression or cyclone system in the Arabian Sea, the monsoon is get delaying. This process is seeing that last 2 to 3 years, I think 2, 3, 4 years. And so that it is shifting. The excess rainfall is now from the June, I think, shifting to July and August. You have any comments in that?
Well, so we have seen from last year, 30, 40 years observation, we have seen that monsoon is coming little late. Monsoon may be coming over Kerala on time, but the northward propagation is happening much later. So that's why we revised the monsoon onset dates very recently. Last year we revised it, and it's almost 1 week much later it is coming. And so I'm not sure what physical process. We thought that, see, I remember when I was studying, after Joseph Saab only taught me, still I remember the first monsoon depression should happen around 14th of June. First genesis of first monsoon depression the season. That now happens much later. So something happening again, Bay of Bengal, maybe it may not be continuous by 14 June. The system, the whole coupled process may not really happening. The genesis is not happening. So nowadays the first system happens much later.
Okay, I request Professor Joseph sir, you have to make any comments or suggestions, sir.
Thank you.
Otherwise, I think it is a very nice talk and very informative to the students and early research careers. It's very interesting and many things we can do now. And thank you to Dr. Rajivan for giving an excellent talk. And thank you. And also, I would like to thank both the speakers, Dr. Mahapatra and Dr. Rajivan, giving an excellent talk and also keeping time. Now I am handing over the mic to the organizers for their some announcements, please. Thank you.
Good afternoon. There is an announcement. The technical section will begin at 2:05 p.m. in all the 3 halls. All chairs and speakers are requested to log in through the Zoom link provided for the next session in respective halls by 2 p.m. Thank you.
Thank you, chair, both the chair. Thank you. Thank you. Sir, we will have to.
Morning session is over.
Thank you, Joseph sir and Mohammed sir, for the chairing.
Hello. ഇവിടെ ജസ്റ്റ് ഇങ്ങനെ സംസാരിച്ചാൽ മതി. അറ്റ് എ ടൈം തന്നെ ലൈവും പോകും.
Dr. Jaykumar, am I audible?
Yes, you are audible, sir. Am I audible?
Yeah, fine, fine.
Okay, okay. Thank you.
Thank you. So others have to join.
Excuse me, can I tell something?
Yeah, please.
With the permission of the chairs, actually, I am on organizer, local organizer also, so that I am in charge of another room, hall number
Okay.
2 area. So that my talk is last one, so that I will join by that time. But I will continue to be in the room, but I may not be in the seat. Sorry for that.
Okay, no problem.
Okay. Thank you.
Dr. Pai is seen now. Probably is there anything probably as a controller or something that you have to do, and then all the participants you will be inviting and then allowing something like that.
Okay.
So our job, myself and Dr. Pai, we will be controlling only the time as well as regulating the session. Is it okay?
Thank you. It is okay, sir. Actually, I am in charge of another room, so that people will be joining here in this room soon. From
Okay.
yeah, I think already they have joined the enrollment hall number 1 and all.
Yeah, so
I am in charge of another, but I am a speaker in this hall, so that I will join. My slot is the last one. By that time, I will come. I'm just saying that my seat will remain vacant, but in the downstairs, I am watching your.
That you told. That you already told. My question,
yes.
whomsoever is regulating from QSAT as it is.
Yes.
So whether they will be allowing the participant to control, speak, or something like that, or that also we have to do as a co-chairs. No idea.
Hi. Hello. Can you hear me?
Samsudin?
Yes. So actually I've joined from UK and I'll be sharing my screen. I haven't sent a PowerPoint presentation yet.
Oh, okay, fine. I am a co-chair for this particular session. I am just interacting with the
No, I just heard you asking him whether you will be kind of managing this presentation, and also I just wanted to clarify that I'll be sharing my screen for my presentation, which is the second one, basically.
Second one is you are presenting Semina.
Yeah, exactly.
Okay. Also at the time probably you can keep your video on, and then you can come straight away.
Yeah.
Right now, as a webinar, normally participants are expected to put off the video.
Yeah. Sure.
Hello all. Welcome to the day 1 technical session of INTROMET 2021 on changing climate observations, attribution and model projections. In this session, we have 2 lead talks by Dr. P. Sopna, Scientist E at Indian Institute of Tropical Meteorology, Pune, an expert in climate change research and Earth system modeling, and then Dr. Samina V, Land Atmospheric Scientist and ILIMS Project Manager at the Center for Ecology and Hydrology, UK, and Air Pollution Scientist working in Land Atmospheric Studies. Lead talks will be followed by 2 invited talks by Dr. Kandu Charan Patnaik, Research Fellow at the University of Leeds, UK, and Dr. Kieran Hunt, Research Scientist at University of Reading, UK. After the invited talks, we have 4 short oral presentations. This session is chaired by Dr. R. Suresh, India Meteorological Department, and Dr. D. S. Pai, India Meteorological Department. Dr. R. Suresh is a scientist F and director retired from IMD and holds immense research experience in the field of radar meteorology and aviation meteorology. Dr. D. S. Pai is the head, Climate Research and Services, India Meteorological Department, and holds immense research experiences in climate modeling and seasonal prediction of monsoon. The lead talk is for 20 minutes plus 5 minutes discussions. Invited talks are for 30 minutes presentation plus 2 minutes discussion, and short oral presentation is for 9 minutes plus 1 minute discussion. We request the speakers to stick to the time allotted. The selected questions in the chat box will be conveyed to the chairs by the rapporteurs. Now, may I request the honorable chairs to kindly take over the session. Thank you.
Thank you. So this particular session, which has the title, as already mentioned, Changing Climate, Observations, Attribution, and Model Projection. The organizers have already said the 2 lead talks of 20 minutes duration followed by 5 minutes discussion, 2 invited talks of 13 minutes presentation and 2 minutes for discussion, and 4 oral presentation of 9 minutes presentation and 1 minute discussion. I request all the speakers to adhere to the time, stick to the time. Now coming to the session theme as it is, changing climate. Normally change is dynamics in eternal life. So does the change in climate also. The climate is ever changing based on the past record of weather data, climate data as it is. Now our job is to see as to whether the change is periodic or aperiodic. The change is seasonal, cyclic, or otherwise. If any of the answer is yes, then we should know the contributory causes so that we'd be in a position to understand the change and try to acclimatize ourselves in such a way that it's a comfortable living for the human being and plant life as well. We should remember one thing, that interchanging usage of the climate change and much talked about global warming, whether it is a myth or real or true, that's again a debatable point and question. So the interchangeable use, we should have a line of separation, and then we have to stick to our talk on climate change and focusing on the focal theme. So without going further, dwelling upon the time, I invite all the speakers, viewers, participants of this particular technical session and say a very good afternoon, a contributory presentation by the speaker as well as the contribution by the listeners. I invite every one of you from my own heart as well as from my co-chair, Dr. D.S. Pai. Dr. Pai, would you like to say something, or shall we start the session?
Yeah, because of lack of time, I think we can start session. And,
So let us invite the first lead speaker, Dr. Swapna. Over to you, Swapna. 20 minutes is the time. We would be reminding you, and you have to allot some time for discussion. The 5-minute discussion, I request all the viewers to be ready with their question. Be sharp. Over to you, Dr. Swapna.
Good afternoon, everybody. I'm sharing my screen. Yeah, I have shared my screen. Is it visible?
It's visible.
Yeah. Yeah. Good afternoon, everybody. And I would like to thank the organizers of the INTROMET for inviting me to provide the lead talk. So now we will discuss about the projections of the future climate of the 21st century. And I will be presenting most of the results based on the recently published IPCC 6th assessment report. And this is a spatial map which is showing the modeling centers who have contributed for the CIMIC, that is the couple model intercomparison project that has contributed for the IPCC. And we can see that from IITM, we have contributed the CIMIC 6, we have performed the CIMIC 6 experiments, and we have contributed for the IPCC assessment first time from India. So in my talk, I will be briefly discussing about the key indicators of climate change. How are they projected to change over the 21st century? and some consequences of our region, especially how the sea level is rising with the warming in the Indian Ocean. So the IPCC report, which was published in August this year, which was clearly showing that the recent changes in the climate are caused by the human causes, and they are all widespread, rapid, and intensifying. Because what we have started experiencing the climate extremes, we are having that extremes recently many years, and we also have seen that the global temperatures have increased by more than 1 degree, roughly 1.1 degrees since 1850. So all these changes are mainly caused by the human-induced climate change. And the IPCC report clearly shows that all these events are widespread and rapid and intensifying. So this report is based on the most updated information on the climate science, physical understanding of the climate change. It is utilizing multiple evidences like paleoclimatic data, observations, and all the literatures which are available on the scientific understanding of climate change, and also the new generation models. So we can see that the CO2 concentrations, right now we have a 40 gigatons per year of emission of CO2. So that is highest in the human history. And also there's a rapid acceleration of the sea level rise. Sea level rise is accelerating, or it is rising in a fastest rate. And there's a depletion of the Arctic ice, and there's a glacial retreat. And all of this have wide-ranging global impacts. And the greenhouse gas emissions, which already we have in the presently right now, it is affecting the climate globally, and it is not only affecting the human society, but it is also affecting the human marine ecosystem, terrestrial carbon cycle. Everything is getting affected, and these changes, what we are seeing, it will be present for thousands of years or generations to come. So the report, IPCC report, again shows that the human activities are causing the changes in the climate, making extreme climate events. One of the major important findings from the IPCC report is that the global temperature is projected to increase by 1.5 degrees in the next 20 years. This is with respect to 1850 periods. So at 1.5 degrees, what will happen? So we can have more extreme heat waves, more number of heat waves will be there, and also there will be long warm seasons and there will be short cold seasons. If we go from a 1.5 degree warming to a half a degree increase to a 2 degree warming, the report says that the heat extremes is always crosses the threshold value for the tolerance level for heat and agriculture. So we have started, like we are having many of the extreme rainfall events and heat extremes. And all these extreme events are projected to increase with every additional degree of warming. So this is an observed temperature trend, observed temperature record for the past 2000 years. And what we can see from this time series is that the temperature has been fluctuating for the last 2000 years, but the fluctuation is of very small magnitude. It is fluctuating roughly between 0.2 to 0.3 degrees centigrade. But if you see the later half of the time series, we can see that there's a huge increase in the temperatures. Temperatures have increased more than 1 degree centigrade within a very short period of time. So this increase that is occurring over a very short period of time, that will have much more consequences. So that is much more worrying when we think about the climate change. And the report also shows that most of these changes are caused by the increase in the greenhouse gases, especially the increase in the carbon dioxide concentrations. Right now, we have a carbon dioxide concentration of roughly 4.12 ppm, and that has been increased since the Industrial Revolution. And these changes, the increase in the carbon dioxide concentrations, are mainly responsible for the increase in the global temperatures. And so we have seen that there is an increase in the global temperatures that is unprecedented for the last 2000 years. And we see that large increase during the past 50, 60 years. And what is there for the future? So how can we assess the changes in future? For this, the IPCC report uses 5 sets of illustrative scenarios. They start from 2050 and it going to up to 2100. And there are certain scenarios that they can even show the changes even up to 2300. So the report uses 5 sets of scenarios. They are called the SSPs. They are called socio-economic pathways. They are called so because they are not only consider the radiative forcing that will be there when we are increasing greenhouse gas concentrations, but they also consider the socio-economic pathways because that will depend on like how much greenhouse gases we are going to emit in the future. So it all depends upon our socio-economic conditions in the future also. So this is a combination of the socio-economic conditions as well as the radiative forcing. So there are scenarios like SSP5, and That is a very high-end scenario in which the carbon dioxide or greenhouse gas concentrations are expected to be increased by double from the present day up to 2050 and by 2100. Also, if we go with the present day emissions of the greenhouse gas concentrations, they are shown by the SSP 245 scenario, like they will be continuing till the end of the century. So what will be the consequences? What are the changes we can expect in the climate? And there are also two low-end scenarios. They are shown by the SSP 1 and SSP 2. They shows that when we have started drastically reducing the greenhouse gas emissions and we made a net zero, we achieve a net zero target by 2050, then followed by the negative emissions. So how the climate is going to change? So these are the main 5 projections that are used in the IPCC report to assess the future. As I told, they are called the socio-economic pathways because it depends upon the socio-economic conditions, how the world is going to develop, how much greenhouse gases we are going to emit in the future. So every scenarios vary based on depending on the emission pathways, what are the climate change mitigation controls or the air quality measures we are going to control. Depending on that, these different scenarios will vary. So these scenarios, the worldwide modeling centers uses these scenarios to run their own climate models. And they will see that how much is the projected changes in the climate. And all these data are publicly available through the ESGF servers. And through this data analysis, and also based on scientific understanding on the past literature, what are the changes they are projected, or is based on that, IPCC made the assessment on the future changes in the climate system. So this is the projected temperature of the 21st century, starting from 1950 to 2100. Again, this is a global mean picture, and it is a difference with respect to the pre-industrial period, that is starting from 1850 to 1900. So we have seen that there are different scenarios, low emission to high emission scenarios. However, if we see the global temperatures time series, we can see that whichever scenario we are following in the future, still temperatures are going to increase at least the mid of the century. This is because we already have emitted a lot of greenhouse gases, and especially CO2 and all having a long lifetime, residence time in the atmosphere. So even if we start cutting down the greenhouse gas emissions, still the temperature is going to project to increase at least till mid of the century. And afterwards, it will depend upon, again, the social economic conditions, how much we are going to emit. So future is in our hands. If we are trying to start to reduce the emissions, we will be able to control the future increases in the temperature and the more extreme weather events that we have started experiencing. So this is an estimate, like how much is the global projected temperature increase in the coming decades. So it shows that in the low emission scenario itself, in the next 20 years, the global temperature is roughly 1.6 degrees centigrade. That is the Paris goal, or Paris Agreement is set for that. So it is, even if we follow the low emission scenario, the global temperature will be 1.5 degrees in the next 20 years. If we follow the same emission as of now, and we will be having it 2 degrees, and the temperature will be as high as 2 to 3.5 by the end of the century. And if we are going with a very high emission, it is like a fossil fuel scenario, we can say, because we are not going to control the emissions, and whole lifestyle is going to depend upon the fossil fuels. In such a scenario, it's a very extreme scenario. In such a scenario, global mean temperature is projected to increase by 3.3 to 5.5, more than 5.5 degrees centigrade by the end of the century. So this will have a wider implications. So again, we have seen that the CO2 is increasing, and most of the increase in the global mean temperatures is caused by the increase in the carbon dioxide concentrations. Even if we look for the future also, under all the 5 scenarios considered, the observed increase in the temperature or the projected change in the increases in the temperature is mainly caused by the increase in the CO2. There are some offset coming from the aerosol and land use. Still, it is mainly overtaken or dominated by the increase in the CO2 concentrations. And however, when we compare the present CMIP 6 models with the past generation models, CMIP 5 or CMIP 3, we can see that the temperature warming, which is projected by the CMIP 6 models, they're roughly on a higher side. We can say 20% higher than the CMIP 5 models. Why this is happening? So what will be its consequences on the projected changes? So this is the equilibrium climate sensitivity. That means it's a hypothetical value of global warming when we have an equilibrium at a doubling of carbon dioxide. So whichever previous assessments of IPCC, it was shown that the equilibrium climate sensitivity ranges between 1.5 to 4.5. But for the CMIP-6 models, when we analyze, we can see that the ECS or the equilibrium climate sensitivity is ranging between 1.8 to 5.6. That means that the models that are having a high ECS, they tend to produce much higher warming. So how can we say that then? How can we assess the changes in the future in such a scenario? For this, for the first time, IPCC has used the assessed ranges of temperature, that is the observationally constrained projections. We have the observational records since 1980s. We have the satellite records, and we know like how much is the present day warming. We use this present day warming as an emergent constraint for understanding the future changes. So we have the CMIP-6 models, they have the historical warming. So we estimate from the historical warming, we estimate how much will be the projected warming. It is simply based on a simple equation, n is equal to F plus lambda delta T. That means that N is the net energy balance at the top of the atmosphere for a given radiative forcing F, say for the doubling of CO2, and there will be an increase in the temperature delta T. So suppose we consider an equilibrium state, like there is a proper balance of energy balance at the top of the atmosphere, then the ratio between delta T and F determines how much is the temperature increase, how much is the radiation forcing to the climate sensitivity. So like from the ratio of delta T to F, we get that is roughly proportional to the ECS and TCR. So we, from the models, CMIP-6 models, from the historical warming, if we estimate the TCS and the ECR from these models, and it is used to run the energy balance models and to see like how much will be the projected warming in the century. So this left panel is the assessed range of the global increase in the temperature based on, left panel is the unconstrained, that means the pro CMIP-6 models. And the right panel is the constrained CMIP-6 projection. That means that it is based on the observationally constrained projections. It always shows that the constrained projections are on a lower side as compared to the unconstrained CMIP-6 models. Why the models is having a very high ECS? It is because now in the recent generation of the models, the prognostic aerosol scheme has been introduced. Because of this prognostic aerosol scheme, the cloud radiative feedbacks are enhanced, negative feedbacks are enhanced. So to account for the observed warming, they have to produce a lot of radiative force. As a result, the ECS has been increasing in the many of the models. So they tend to produce much higher warming. However, to account for that, we have also assessed the constrained CMIP-6, like how much will be the projected warming based on the observations. So constrained temperature warming projections are also available with the recent IPCC report. And another issue when we are looking at the projections is that we will see like at the end of the 2050 or by the 2070 or end of the century, what is the projected change? If we are looking like we have different types of models, we have different scenarios. We have a low end scenario SSP 119 and we have an SSP 585. So warming is definitely going to be higher in the high end scenario compared to the low end scenario. And if we average over a particular time period, it will be giving a mess of results because we have a ECS, different models of ECS, and different warming levels are coming from different scenarios. So the projections are mostly affected by the uncertainty coming from the scenarios, as well as the structured uncertainty that is coming from the ECS of these models. So one of the best way to assess the projected changes is the pattern scaling technique. In the pattern scaling technique, what it has done is that we only assess the changes at different global warming levels. Suppose now the present day warming is roughly 1 degrees. If it is a 2 degree warming, what will be the change we can expect over the globe at 3 degree and 4 degree? So that these temperature patterns, we see all the models and we also assess all the scenarios. So we will be getting a consolidated result across models, across all scenarios. And for the precipitation, we can see that across the different scenarios, because it also changes with aerosol forcing or the dynamics are also changing. So we may get some changes in the pattern slightly different when we look at the precipitation pattern. Still, if we see for the different scenarios at the opposite 2 degrees warming, we can see that there is not much difference is seen across different scenarios. So this method can even apply for the precipitation to assess the projected changes in the precipitation across different levels of warming. And when we look at if we average over a globe or average over a global land regions, this is a very good technique to assess the projected changes with increasing levels of warming. We can see that high-end scenario, SSP 585, it is roughly producing a 4 degree warming. We are getting roughly 0.2 millimeter per day increase in the rainfall when we are comparing to 1 degree warming, whereas we won't get much increase in the precipitation when we are what we are seeing. So we can say that the global warming levels nexus between GSAT and the CMA. So these are the observed patterns of change, as I told, like 1 degree warming to 4 degree warming. You can clearly see the contrast, like land is warming more than the oceans, and the Arctic regions are warming much higher than the other regions. So these temperature patterns linearly scale, and any regional pattern we can clearly identify based on the global warming levels. And when we see the extreme precipitation events, also we have seen that we have started, this is the extreme heat waves, and the heat waves are also increases with warming. The event which is occurring a 10-year event, which is roughly occurring 1.2 times or 2.8 times possibly, they will increase by roughly by 9.4 times by a 4 degree warming. Similarly, the precipitation patterns, they are projected to enhance with warming. Tropics will be receiving more rainfall, and over the Indian region, rainfall is projected to increase with warming, but it will be having much higher variability. And also the extreme precipitation events are projected to increase with warming. This just because at every additional degree of warming, there will be a 7% increase in the moisture. So that is going to enhance the extreme precipitation events. Similarly, the ice and the acidity. And one more important point I would like to address is the rise in the global mean sea level. We have seen that under different scenarios, we are considering sea level again, because ocean is having a very low memory. So the whatever heat, because when heat is added to the system, the ocean, the water expands, and also the melting of the glaciers, more water is added to the oceans. So the sea level is projected to increase globally. And if you see that for ocean absorb more than 91% of the heat of the climate system, so that is going to produce much more heat connect, just because ocean is having much more higher heat capacity than the other components, and also ocean is having a higher mass. Although if you make a simple calculations, ocean is going to produce much more heat into the absorbing the heat, and one of the consequences of that is the increase in the sea level. So global mean sea level estimate shows that it is rising at a rate of 1.8 millimeter per year since 1960 to 2000. And in the recent satellite records, it shows that 3.6 millimeter per year global sea level is increasing. And Indian Ocean also, sea level is increasing of the similar rate as of that of this one. If we see the projections of the sea level, again, we see that we go from the higher to middle and low and higher scenarios, the global sea level is increasing. However, in the Arabian Sea or the Indian Ocean, sea level is again projected to increase. So it is shown that by 2050, there will be like another 15 to 20 centimeters of sea level rise. But apart from the rise in the mean sea level, extreme sea level events are also projected to increase. What are the sea level extremes? Because when a cyclone is happening, there will be storm surges, and when they are happening together with the high tide, they will produce much more higher elevation of the sea level. On the top, if we have a mean increase, and on the top of that, these events are also increasing, that can produce much more problems to our coastal regions. This is just an example from the tide gauge observations. Like we have two cyclones, Tote and Yas, that has happened 2021. And what were plotted is the extreme sea level along our west coast and east coast of India. And we can see that Tote was an extremely severe cyclonic storm, but Yas was a severe storm. Still, Yas made much higher sea level or extreme sea level than the Tote. So it all depends on the topography, and also depending on the tide and also the mean sea level increase. That is going to make much more impact. And Mumbai coast, we have a sea level data from 1870 onwards. And if we also analyze the extreme sea level, we can see that extreme sea level has clearly increased in the Mumbai coast in the recent years. These are caused by the increase in the mean and also increase in the surges. So increasing extreme tropical cyclones will have an impact on these events on our coastlines. So just to summarize, we can see that the climate change is affecting every region on the multiple ways. So whatever changes we are experiencing will be further increase with warming, but still we have a hope. Like if we can reduce the emission of GHGs, we will be able to control the increase in the temperatures, and the severe extreme events will be able to minimize. Thank you.
Thank you for finishing on time. Now there is time for a few quick questions from the viewers. Please be sharp. Any question, comment, or compliments? Okay, it takes time. So let me just congratulate you for having presented nicely. I have a small point to make. When we talk about the surface emission, going into the climate model, we always mean the CO2 alone. CO2 as ejected by the aircrafts, especially in the current day with the mushrooming of airports and then exponential increase in the number of aircraft operations, 1 kg of ATF burning releases 1.2. Now it is reduced to 1:3.15. Earlier it was 1:3.2. Now it is 1:3.15, 15 kg. Okay. That amount of CO2 is being pumped in by the aircraft operations. Whether these set of climate change models, climate model, projection models, etc., do they take into account the CO2 released by the aircraft? That is number one. Number two, the ways of means of curtailing any other factor which may be a contributing factor for change in the temperature. Whether any study has been made, please.
So basically, in the CMIP 6 models, the aircraft emissions are also considered, because for the modeling centers, they provide us the emission data. So we run the model based on the emission data. This emission data of the CO2 also contains the emissions coming from various sources, including the aircraft. So they are also considered for while assessing the scenarios.
Okay.
Yeah.
Second one, is there any other contributory factor other than CO2 for rise of temperature?
Yeah, there are other factors. CO2 is the major factor. Other than that, the methane emissions and nitrous oxide, these are all contributing. But when we compare them, compared to CO2, they are of magnitude as compared, and we have to consider the residence times.
Okay. Thank you. Any other comment or questions from the viewers? You have still time. If there is none, let me congratulate Dr. Swapna for having wonderfully presented the lead talk. So thank you, Dr. Swapna.
Thank you very much.
Now the second lead talk, Dr. Pai, you can conduct.
Dr. Simina.
Simina. Hello. Can you see my presentation in presentation mode, please?
Yes. Yes.
Okay. Okay. Yeah. Thank you very much, and good afternoon to everyone. It's a very early good morning for me here, and thanks to the organizers for inviting me for the talk. I will be discussing about the land atmospheric interactions on extreme rainfall events over Western African region. And this talk is going to be more scientific, and it will include a lot of previous studies and some of the studies that we have conducted in our group here. So I'll be showing results from our group, including Chris Taylor, Connie, and Beth and Harris. I have organized the talk with an introduction about previous studies. And then when it comes to the land surface features, I'll be talking about soil moisture and deforestation, which is basically the land surface temperature anomalies. And then we will discuss about whether we can represent these processes in climate models and what we can do to give a proper prediction about the impact of these land surface features. And then finally, if we have time, we can quickly go through whether we can do something about fix or reverse the problems. So when it comes to global warming, it's not only emissions actually, and we know that it's anthropogenic influence on global warming. And to an audience in India, I don't need to say that global warming is causing all these lot of extreme events and the hazards and the problems caused by these extreme events. But at the same time, the hydrological cycle is also expected to intensify under global warming events. And more previous studies have reported more frequent extreme rain events in many regions. So this is one such event over here. This is a storm captured in satellite picture in 2009 over Burkina Faso and in Ouagadougou region, and that caused a lot of problems over there. So if you are not so familiar about the Western African geography, this is the region that I'm talking about. And the Burkina Faso is here, the storm is shown over here. So when it comes to the extreme events and rainfall over Western African region, unlike in Indian subcontinent, most of the rainfall over the African region is contributed by convective rainfalls. So I just want to show an example about two satellite pictures of two regions over Ghana and Mopti region in Mali, which is over here, which is a wetland region. And you can clearly see the white patches over here are clouds, and the clouds are formed on top of wet regions, wet surfaces, and that's a very good example over that. And apart from that, the main rainfall over Western Africa is caused by mesoscale convective systems. And the studies have shown that 40 to 90% of rain is caused by this one. So what we were trying to see is whether these mesoscale convective systems are sensitive to soil moisture, and whether it is sensitive to land surface features like the surface temperature, and if so, is it affected by deforestation? And then finally, we will look into whether we can model these features and then give a proper estimate about or forecasting about such features. This is a study by Taylor, Chris in our group in 2017 came out, and this is based on Meteosat data of soil moisture and rainfall over there. So it shows that the rainfall trend increases over Western African region, and these two plots are shown from this red box over here. And this one shows the extreme rainfall event over that period increased rapidly over these 35 years. And these two plots, the time series that shows the trends in extreme weather events based on cloud to temperature from Meteosat 1 and Meteosat 2 satellite data. And the solid line over here shows the GridSat, the cross-calibrated GridSat versions of this one. Basically, what the study showed that the percentage change in increase of extreme events over West African region. And then we wanted to see whether how the land surface is impacting over this one. And this plot that I'm showing here is a classic study which came out in 2004 by Coster et al. That shows a GLACE, this global land atmospheric coupling experiment, included 12 modeling groups, and each model did an ensemble simulation of 16 members. And here we can see that there is a strong, significant coupling between the land surface and the precipitation over these regions. Now, based on that, Chris again did a study with this ASCAT and the AMSRE soil moisture measurements. And this plot shows that preference of afternoon precipitation over soil moisture anomalies. And this plot shows that this is a very interesting study, the first of that kind, that shows that afternoon precipitation is actually linked to the drier soil, which came out very interestingly. And then when you talk about drier soil, the mechanism is that the vegetation cover and soil moisture that influences the partitioning of radiative energy between latent heat and sensible heat flux. So when there is a drier area over there, the sensible heat flux increases and that thickens the PBL. So when there is a thick, dry PBL and there is an adjacent wet region, there is a moist advection into the drier area, and that causes intense convergence and formation of convective system, which is very classic cases in dry areas like Africa. Then he looked whether this feature that they can find out these features in climate models, and they looked at 4 climate models and 2 reanalysis models. And unfortunately, those models were not able to capture these features, which is understandable because in climate models, the mesoscale convective systems actually are in a dynamical scale, which is not able to resolve by climate models. So this study with the models were not really surprising. So then they went on with the soil moisture and anomalies and how it is impacting the land surface temperature over here. And this is again a satellite picture of soil moisture. And it is nicely shown that the rainfall is aligned very well with the soil moisture. When they looked into the land surface temperature anomaly, especially over a region in Mali, we could clearly see that precipitation or the storm events that happened a day before generated a very heterogeneous temperature pattern over that region. And we looked into that region, especially because that's the wetland region that I showed in the beginning. And that land surface features and the heterogeneity between the surface can cause actually a lot of convective events. Sorry, that was supposed to be an animation over there from a satellite rainfall event over there. But anyway, then further, when we have a land surface temperature anomaly feature generated over there, how it is going to affect a convective core or the generation of convective systems over that region. So we went on with the study, looking into the number of convective cores within a mesoscale system. We analyzed more than thousands of storms captured in satellite imagery, which is over Sahel region. And then this study found that the downstream side of the convective systems are basically aligned in the eastern part of dry patches, and it extends up to more than 200 kilometers of radius actually. So this result is a beautiful example of surface temperature anomaly aligned very nicely over soil moisture anomaly, dry soil moisture anomaly, and then that is aligned very nicely over the low level humidity and then wind shear. So basically, we went on with the frequency distribution by analyzing the cloud cores in the systems. And we could see that more drier cores here, more cloud cores are aligned with drier surface. So basically, then we came up with a schematic of what is happening physically over that region is due to the land, dry land underlying surface, a convective initiation happens in the afternoon and it generates within hours, it rapidly generates, grows into a mesoscale convective system. And when it is grown into a big system, it actually also moves westward with the African eastern region. So with a lot of analysis with the, satellite data has proven that the soil moisture has a great impact on generation of convective systems over Western African region. So when we talk about soil moisture, let's go to land surface temperature and deforestation, whether we can see that pattern in the land surface temperature data. This is basically the deforestation over Western African region. And then the interesting fact over this is that unlike in Amazon region, on Western Africa, most of the deforestation is caused by conflict in that region, cocoa production, agricultural expansion of agricultural areas due to rising population. And also this is deforestation data from USGS data. This is another deforestation data from Hansen, which is a 30 meter resolution data. So looking into those ones, we again try to analyze or try to find out the mechanism between the land surface temperature and increased convective events over there. So basically, this is a paper recently accepted in PNAS. This shows the trends in vegetation optical depth from 91 to 2015 period. And the red patches over here shows the deforestation more than 25% in Hansen data. So you can see that the vegetation optical depth data and the Hansen data agrees very well. Then we looked into the land surface temperature data. This is again, as I said, beautifully the land surface temperature anomalies aligned very well with the vegetation optical depth or the deforestation data over there. This black contours over here actually shows the trend in core frequency, and the contour values from 440 and 80% per decade are shown here. So just look in the correlation between the LST's trend and core frequency, you can clearly see that it is aligned with the positive land surface temperature. Then we checked the vegetation optical depths trend and the deforestation from Hansen data, how they agree, and you can clearly see that they agree. The shaded is VOD and the contours are Hansen data. So basically, again, the VOD is aligned very well negative VOD, which means deforestation or the lack in vegetation optical depth causes an increase in LSD, the same with the forest cover. Then we looked into the West African region, how the deforestation is impacting other features. And we found that most of the deforestation happening over the coastal region between 0 to 300 kilometers of that region. So this shows due to that one, there is a increase in land surface temperature trend. And then there is, this shows that most of the deforestation happens in coastal areas. And again, as I said, there is a population increase in coastal regions. So, and then we looked into the different classifications in the vegetation species. And that's very interesting that this deforestation is aligned with the vegetation gain in other fields, which is basically agriculture, savanna, and the settlements over there. So again, it concludes our assumption that the expansion of agricultural region, which is aligned with the settlement or increase in population, is causing a lot of deforestation over that region, and that is causing actually land surface temperature increase. And when the land surface temperature increase in a heavily populated regions like that, it can have a lot of impacts on human life. When we come into a global picture, this again, when you look into the deforestation, we can see that the most of the deforestation happens in a coastal region up to 300 kilometers. So we concluded that deforestation and the soil moisture is having a great impact on the convective core initiation in the afternoons of Western African region. So we were thinking whether we can do, because since these are not easy to model, we have to give a warning, and it affects a lot of life over there. We are thinking about whether we can model it in the, or how well these features are represented in climate models. We looked at 2 climate models from Met-Office ensemble system, and we took one event over Mali region, which is shown here. On 25th of April 2019, a very extreme event was reported over Mali, and a lot of flooding and local casualties over there. This is a land surface temperature anomaly data from Sibiri. Data, 15 minutes data, and this is what actually exactly we were looking for. This heterogeneity between the temperature, this large heterogeneity, steep heterogeneity, that can cause a lot of, lot of discontinuity and this chaos over that region, and that can initiate a convective force over there. So the models, it is a global model in 28 kilometer where convection is parameterized, and this is a convection permitting model. And in general, we can see that both those models captured that event. This is the GPM precipitation event, precipitation from the observational data. So basically, the near real-time data that we have used to analyze these precipitation event and the land surface temperature, that we went into the details because of these features. We found that these blue lines over here is the representation of water bodies in these 2 models. So when we have a very large representation or wide wetland over in a model, that is not easy to compare between these 2. So we looked into the land use representation in these 2 models, and we noticed that it is completely different because this is broadleaf in the global model, and it is in the convection permitting model. Huge difference between broadleaf C3 grass and C4 grass and the water bodies, which means there will be a lot of impact on evapotranspiration that is coming from the land. And basically, we will not be able to go for a direct comparison between these 2 models. So we went on with considering these 2 models, especially we are looking into the land surface features and how it is going to impact. So we went on analyzing these 2 models independently, and then to figure out whether these models are able to capture that afternoon events. This is a correlation map between the initial soil moisture anomaly and evaporative fraction and temperature. Evaporative fraction at 9 o'clock in the morning and temperature at the same time. Evaporative fraction is actually a measure of how much water vapor is available for energy. which is a ratio between latent heat and the total energy. We can see that with a positive soil moisture anomaly, there is more evaporative fraction anomaly, and then it is negatively correlated with the temperature, which is basically shown in other observation studies, and the models were simulating it pretty well. But when it comes to nowcasting or using it as a nowcasting tool to give warnings whether we can use these models, we looked into the frequency distribution, and we could see that basically all these both models are aligned towards it is more skewed towards the negative evaporative fraction anomaly. But then when it comes to the possibility of simulating convective events in the afternoon, this orange pixels shows convection permitting models and the blue one shows the global models. And this shows 2 millimeters of rain in the afternoon at 2 o'clock and this 5 millimeters of, and any value more than 1 shows that there is more probability of rain. So basically we could see that the convection permitting models are giving a better estimate about the probability of rain compared to the parameterized convection models. So basically, when you come to talk about whether we can use these models, we are not still very optimistic about that one because of different reasons that the land use is not represented properly in the model. But still, there is a chance that we can still use the convection permitting models to talk about the afternoon rainfall initiation and to use as a nowcasting tool. At the moment, we haven't used it as a tool. Instead, the project that we are working for Africa, the Science for Weather Information and Technology, we could clearly see that we can use land surface temperature as a proxy to predict the afternoon precipitation. So as part of our project, we have developed a nowcasting system based on the LSD that I have shown before from the Severi Meteosat data, Severi data, using the near real time. So we get the LSD updated at every 15 minutes and we calculate the anomalies and we calculate the land state at that time, and then we can predict whether there is going to be an extreme event in the afternoon. That's what we have done, and we have submitted that paper to ERL now. So basically, we concluded that there is a huge impact on land surface in the initiation of extreme events over West Africa. What we can do that apart from global warming issues, there is land use also, which is affecting a lot of extreme events. Then when we talk about whether we can do anything about that, yes, we are sure that we both are in our hands. You know that changes in land use is caused by humans, anthropogenic emissions, everything is in our hand. So we can definitely go for mitigation measures. And I'm not a fan of adaptation or acclimatization, but I would really prefer to go for mitigation. So there are a lot of things that we can do, and I will be very happy to discuss about that. Thank you very much.
Thank you, Dr. Samina. Now, the lecture is open for discussion. Any quick question from the viewers? There is something available in the chat box. Okay, that's not a question. Is there any query or comment or compliment?
Suresh, can I ask?
Yeah, please. I was waiting for you.
Yes. Yeah. Dr. Samina, actually you spoke on extreme events. So what is this impact on total rainfall? Is it also, there is any impact on the rainfall, total rainfall, or only extreme events?
No, there is a huge impact on total rainfall events. Let me see if I have a slide on that. Yeah, So I will just share that plot actually. I went through that one quickly actually in the interest of time. Can you see that, this one?
Yes.
Yeah. So basically this plot, the plot A, it shows annual rainfall in millimeters. So this shows a trend that there is increase in precipitation. The amount has gone from 85 to 2015. This is a 5-year running mean. Yeah. This one shows the increase in extreme rainfall events over the period. So it's not only that extreme events, the number of extreme events have increased, but the total rainfall also have increased over the period of. And this is basically over this region that shown in the red box. It comes under Sahel. Sahel, if you are familiar with the African region, it's over the Sahel region.
So this is after a long drought type of situation earlier. Now that you say that the rainfall is increasing. So
Yeah.
it was mainly people are contributing towards the forestation that time.
Yeah.
Okay.
It is.
So,
Deforestation is a big issue over West African region. I'm so sorry. Everything is at risk. So deforestation is a big issue in Western Africa, unlike in Amazon region, which is basically for business, mafia, log, that kind. Basically, what is happening in Western Africa is due to increase in population. That they need to expand their agriculture. That is one reason that they are converting the forest area into agricultural land. And on top of that, the weather in Southwest African region is extremely identical for cocoa plantation. So most of the chocolate industries in Europe, also in US, are investing in Africa to convert the forest land into cocoa plantation. So there is a large increase in that agricultural area plus the cocoa plantation area in that region. So when you cut down the data that I showed in the Hansen forest, which is where they classify the forest cover as any greenery, which is more than 5 meter height. Everything that comes under 5 meter is considered as grassland or savanna or the shrubs and C3, C4 grasses and all. So basically all these plantations and agricultural land comes under that. It doesn't show in the forest cover data. But then USGS has a classification of all these different type of vegetation. And you can clearly see that how that is the one of our studies in the deforestation that is accepted in PNAS, how much forest is converted into agriculture. And when we do a correlation studies, that increase in agricultural land correlates very well with the population increase also. Though the problem is a lot of wildlife, it's not only human, all the extreme events or the increase in precipitation is aligned over those areas where deforestation happened or increase in agricultural regions happened. It's not only humans, it's a lot of wildlife is affected. Because many people would say that I'm not concerned about gorilla, but I am. It's their land, and it's just getting reduced. And the gorilla population is going into, people say that it's kind of, in 50 years time, we can tell our children or kids that once upon a time, there was a species called gorilla like dinosaurs, and and I'm not in favor of that, honestly. And we have to leave their habitat for them. And I know that increase in population, we also have to live, but we need to identify solutions to coexist. And it is possible. It's not that difficult, to be honest.
Thank you for your concern about wildlife and nice explanation. Okay, thank you.
Thank you.
Yes.
I think, Suresh, we can go for next.
Yeah, please contact. Next are two invited. You can invite.
Okay. Thank you, Shamsina and Simina. Thank you. So we will go to now next invited lecture by Dr. Kanhu Charan Patnaik from University of Leeds, UK. Dr. Patnaik?
Yeah. Hello.
13
Good
minutes.
afternoon.
13 minutes, please.
Yeah, 13 minutes.
Yeah. Good afternoon to you and to everyone. So I am Kanhu Patnaik. So I was working in University of Leeds when I did this work. I think, am I audible clearly? Is it?
Yeah, sure.
Okay, good. So currently I moved to Singapore. I'm working as a senior research scientist. So this study, what we did in Leeds was we actually tried to find how the industrial deforestation has impacted the moisture recycling over Indian subcontinent. So using some kind of stable water isotope fractionation and how the contribution of the land and the ocean, the moisture contribution from both has affected. So this kind of study we did in this. So basically, I will speak about the background of the study, then what simulation we carried out, and we'll discuss about the result and summarize the results. So since we know that the Earth's surface has changed rapidly, and therefore the coupling between the land and atmosphere that also changed. And with recent studies that suggest that the Amazon deforestation at tipping point the tipping point of the deforestation is if 30% of the forest will be cut, then the climate will lead to a much less precipitation what it is currently occurring at the Amazon forest, and the Amazon forest will turn into savanna. So India is one of the reasons where the substantial change in the deforestation, the land cover has occurred. So since India is mostly dependent on the monsoon, therefore the monsoon also has changed, especially in the long-term perspective since the industrial period. So it is very crucial to understand the moisture sources and associated mechanism for a monsoon, crucial for the climate change adaptation. Okay. So what brings me to this study is how the vegetation type has changed from the pre-industrial age to present era. So which is compared the broadleaf trees and C3 type grass and the shrubs. These are the main categories. What we see that if you see the top panel, it is the pre-industrial about 1870s, and the middle panel is somewhat present about 2010s. So you can see that the broadleaf trees has drastically reduced in the recent era. So recent era, presently, so about more than 50%, 40 to 50% broadleaf trees have been reduced. So the tropical deforestation during the industrial, mainly it happened during the industrial period, whether it impaired some way to the Indian monsoon and how the monsoon dynamics have changed. So for this, we actually conducted few simulations focus on whether the moisture sources because of the deforestation has changed or it remains same or some other sources has come up after this. Okay. Another thing is that the delta 18O. So delta 18O is the ratio between, well, as you know that water has two isotopes. One is delta H216O and H218O. So delta 18O is the ratio between that the H216O, H218O and H216O. So this is a good proxy for the precipitation and to study the convective parameters and the hydrological cycle. On training studies, where my collaborator, Professor Emmanuel Glo, who goes to the Amazon forest. And from their study, they found that the prairies that have the information about the last 100 years or 150 years or 200 years, how the land cover has changed over that period. So it is really important if we can incorporate that information into the model, then we can use that information to interpret the land use change in the last 150 years. So this is schematic diagram how the precipitation delta 18O migrate from the ocean into the land. And what we found is that along the coast, towards the near to the coast, the more delta 18O is getting depleted. And as we go into the inland, the delta 18O gradually decreases. So this is with the increasing distance from the coast, the decrease in the delta 18O happens. So this is called the continental effect. And evapotranspiration works as a positive feedback to the atmosphere. So it reinserts back the delta 18O into the atmosphere. So there is a net east-west gradient which reflect the control of these two parameters. So next, we carried out 3 different simulations to find out how the land cover changes affected the rainfall and the moisture, and how whether the greenhouse gas has to do something. So we carried out 3 different simulations, one with fixed land cover and fixed greenhouse gases. We call that a control simulation. And we fixed the greenhouse gases to 280 ppm to pre-industrial level, and land cover also fixed to the pre-industrial level 1870. And then we just changed the land cover to the observed one, but then fixed the greenhouse gases to pre-industrial, and third one with both observed land and observed greenhouse gases. So another interesting thing we did, this model we used had CM3 model. So we incorporate 2 different tracers, 2 hydrological tracers. So one tracer will tag the water. Tag the water means the rainfall occur because of which moisture, whether it is evaporated from the land or if it is evaporated from the ocean. So both has different tracers. So typically we can quantify how the precipitation occurred because of the locally evaporated moisture has affected or not. So basically that is the. So what happened? So this plot is from the land cover only simulation minus the control simulation. So this simulation only we change the land cover, not the greenhouse gases. So to see how only the land cover change affected the rainfall. So what we see that the land cover actually the rainfall has decreased over the central India, but if you can see that temperature with the rainfall in the winter season, it is along the east coast and the peninsular India that rainfall has increased. But if the second panel is the regional recycling precipitation recycling ratio, that means what percent of the rainfall is because of the locally evaporated moisture. Okay. So in this case, about 30% of the rainfall has decreased from the regional recycling ratio, the regional locally evaporation. So, but it has increased. Overall, it has increased, but the contribution from the local evaporation has decreased. Okay. And this is in delta 18O because of the more rain out during the winter season along this east coast and the peninsular India, more rain out had happened. Now coming to the second simulation, the second one. So this one is the more observed one, like with this one having the land is land cover plus greenhouse gas simulation change minus the control simulation. So when we actually involve the greenhouse gas to increase, allow the greenhouse gas to increase, the rainfall has increased over the Indian subcontinent. But during the winter season, this is more or like similar to the only land is land cover change simulation one. So this is the main difference between the two. Only the over this land is in summer monsoon because of the greenhouse gases, so it's allowed to heat the heat more. So it actually allows more moisture in moisture advection from the ocean. That is the reason why we got the more rainfall in the summer season. So then we also did that moisture, how the moisture convergence is, and we found is that along this east coast in both the simulation, the most moisture converges during the winter season. So this increase in rainfall has been attributed to the moisture convergence over eastern coast of India and peninsular India. So that's all for so to summarize my study. So we quantified the signal from delta 18 and the continental water recycling as a land derivative, the tracer of the Indian subcontinent. So removing the forest reduces the precipitation, but not in the wet season or affect the mostly dry season only. Delta itinerary reflection primarily rain out process during the summer season and the land derived precipitation during the dry season. So that's all. If there is a question, I would be happy to answer. Thank you.
Thank you, Dr. Patnaik. Before the question is open for discussion and then comment, and I have a small comment to make.
Yes.
See, the season as such, the classification you are making winter inclusive of December.
December, yeah.
But unfortunately, December is not the winter season as far as India is concerned. And then moreover, during which period, the way in which you have plotted all, so that is a spillover of northeast monsoon, or northeast monsoon was quite active during December. So that causes, so whatever value you probably now you have to look into and then exclude the December, then probably your study will be having vital impact. And especially, I am happy that you are using delta 18O. That's a good study, really. I appreciate you. So my suggestion is that probably you can exclude December and then do some more good work. Thank you.
Yeah, thank you very much. I will do that then. I will do that based on the IMD definition, not the development definition.
Yeah.
I think we will thank Dr. Patnaik ji. Actually, he kept his time within time. Okay, so there is a time only for 1 or 2 questions. So we will move to the next lecture, because there is, we have to keep the time. Thank you, Dr. Patnaik.
Thank you very much.
So we will invite now Dr. Kiran Hunt, University of Reading, UK. And he will be giving a lecture on Western disturbances and climate change, past, present, and future. To Dr. Kiran.
Hiya. Just give me a second here. Sort this out. So hopefully you can see those the lead slide now. Yeah, good. Great. Okay, good afternoon. So I'm Kieran Hunt, and I'm going to talk to you today about the work that I've been carrying out at the University of Reading over the last 5 or so years, largely since I finished my PhD. This is work mostly done with Andy Turner and Len Shaffrey, but there are plenty of other international collaborators as well. We've done a lot of work with Professor Dimri, for example, at JNU. So today I'm going to attempt a sweeping overview of Western disturbances. We're going to look at the evidence for their behavior in paleoclimate. And we'll look at how we use modern observations and reanalyses to look at their structure and impacts in the present epoch. And then hopefully we'll have time at the end to combine these lines of evidence with climate model output and quantify their response to future climate scenarios. There we go, good. So we'll start with an overview of what Western disturbances are. In contrast to much of the weather that affects the Indian subcontinent, they're extratropical on origins. Obviously, the monsoon is a very tropical weather system, but we set outside of that. These systems often spin up over Europe or the Mediterranean, and then they're brought to North India by the subtropical westerly jet. And as a result of that, they're very baroclinic in nature. We can see that by looking at their vertical structure on the right. I guess you probably can't see my cursor, so I'll just tell you where the plots are as I get to them. So this plot on the right is a composite vertical structure as seen in reanalysis, the era interim reanalysis. And what we did there was apply a tracking algorithm to era interim reanalysis that identify Western disturbances. And then we take storm-centered composites and look at those in the vertical. And these are 8 different variables. So you can see in the top left here, this is zonal wind. So this is the jet. You then have a PV anomaly. So panel 4 here on the top right shows the potential vorticity anomaly. Sorry, not anomaly, just potential vorticity. And the response of the potential vorticity maximum is in deep shear flow is to produce ascent ahead of it. That's to the east, and you can see that in panel 3 here. That's showing omega, and descent behind or to the west. Sorry, so ascent to the east, descent to the west. Now, when you combine that ascent with the circulation that we get, so the circulation is shown in panel 2 here, and you can see that there's a lot of southerly flow even in the lower levels, and that brings a lot of moisture up from the Arabian Sea. So combine that southerly moisture flux comes up from the Arabian Sea. It ascends both due to the circulation of the Western disturbance and because it hits the Himalayas and is forced to ascend by the orography. So that brings very heavy precipitation as a result, both liquid in the lower altitudes and solid precipitation at higher altitudes. And because this happens in the winter when the monsoon is not so active, these systems basically bring most of the winter precipitation to North India and Pakistan. And they're also associated with a lot of extreme precipitation events as well, particularly when you can imagine high moisture flux hitting the mountains, releases a lot of moisture very quickly. They have a seasonal dependence as well. Like I said, they come predominantly in winter. That's because they come in the subtropical jet, which is much further south during the winter months, December through March, than it is during the summer months, June through September. During those months, the Western disturbances usually pass over the Tibetan Plateau or to the north of the Tibetan Plateau. But they can occur during the monsoon months as well. They're just a lot rarer. So in bringing a lot of precipitation during the winter, these systems essentially have an agriculture that's dependent on them. The rabi crops are dependent on the moisture that's brought in by Western disturbances. Rabi crops are things such as wheat and barley and mustard. So let's start on a timeline now that I've given you an overview of what they are. So let's look at paleoclimate, start right at the beginning. So this plot on the right here is a plot from Livio Jossen's paper. It's a very good sweeping paper looking at the paleoclimate of northern Indian winters over the last 6,000 years. So they've used the collection of proxies to explore winter precipitation over the subcontinent, and particularly focused on and just after the mid-Holocene. So the mid-Holocene is about 6,000 to 4,000 years ago, and so it ends just as this orange bar begins. And time on this plot, by the way, starts on the right-hand side and moves to the left-hand side. You can see at the bottom of the plot that as the mid-Holocene ends and you come out of that period, the Western disturbance activity increases significantly. Now, this is because during the mid-Holocene, there was a lot less insolation in the northern hemisphere. The meridional temperature gradient was weaker, and therefore the subtropical jet was weaker, and so it was bringing in fewer of these systems. We can see that. I would also add at this point that this is contemporaneous with additional activity in the North Atlantic Oscillation and increased European flooding. We'll get onto that a little bit later. To move beyond proxies and into model space, we can explore these in a little bit more detail. So it could, as part of CMIP-5, 6 modeling agencies took part in the PMIP-5 experiment, and that was basically they're using mid-Holocene solar forcing to drive models, so we can explore what's going on during the mid-Holocene and compare it to the present day. Now on the far left, so what I did was track Western disturbances both in historical, that's present day style CMIP-5 experiments, and also their PMIP counterparts. And you can see on this far left plot, these violin plots show the difference in Western disturbance frequency and in Western disturbance intensity. Now the frequency, the models don't necessarily, they're not all significant, the changes, but where they are, you can see that the present day Western disturbances are more frequent by about 10%. And they're all significantly more intense as well by about 5 to 10%, depending on the model. And the result, the implications of that are that winter rainfall decreased over the Indus Basin. These are the plots along the top. Sorry, the winter rainfall increased after the mid-Holocene. As the mid-Holocene comes to an end, winter rainfall increases. And what that means is that we went from what was a summer growing season to a winter growing season over the Indus Basin. So the Indus Basin is marked in black in the figure in the top right. And where the season was once a winter growing season and is now a where it was once a summer winter growing season, where it was once a summer growing season is now a winter growing season. That's marked in this dark yellow, and you can see that that boundary occurs much over the Indus Basin. And so it's possible that this is one of the many factors that contributed to the end of the Harappans. If they were the Indus Valley civilization, if they were dependent on summer crops and they had to move to winter cropping, they may not have been able to adjust quickly enough, because this seems to have been quite an abrupt change. Anyway, that's enough paleoclimate. We can now move to the present day. I'll move the slide on. Good. So let's look at the last 70 years. And there are loads of different ways that we can count Western disturbances up over that period. So in the top right is a figure that looks at 5 papers that have counted Western disturbances using different methods, most of them using observations. So they've counted them up in things like IMD weather bulletins and that sort of thing. Apart from the red line, which is my paper where we track them in reanalysis. So I'll get onto that in a minute. But of the remaining 4 papers, they generally show a slight decline, but because these are quite short periods and generally attached to specific locations, just look at a particular city that's impacted or something, these declines are not necessarily statistically significant. Indeed, if we move to a broader way of doing it, we go to the bottom plot, and this is just tracking Western disturbances in 3 different reanalyses using 2 different techniques, which I won't go into now. You can see that actually there's a lot of interdecadal variability, a lot of interannual variability as well. And that swamps really any significant trends that brought about from greenhouse gas forcing. When we get onto future climate in a bit, we'll see that that's not going to hold forever. But for the time being, it seems that there's no real trend one way or another, and different methods of counting give you different answers. So briefly, we'll look at a little bit of what's causing this relationship with interdecadal variability, and it doesn't take a great deal of exploration to link this to the NAO. So we can look at years in the top right here, we can look at years where Western disturbances are much more frequent and compare them with years where they're a lot less frequent. And what I've done there is use a metric of jet strength and jet location. And you can see that generally on years where the Western disturbances are less frequent, the jet is either weaker or further north. And if we do the same thing, but with looking at NAO positive years and NAO negative years, the projection of jet behavior is very, very similar. So it's reasonable to link differences in NAO differences in the NAO sign and strength over subsequent years to differences in Western disturbance frequency. And if we do that calculation directly, as I've done at the bottom here, you can see that when you have a positive NAO, you have up to about 20% more Western disturbances in there. They're also stronger in those years as well. And as a result of that, we bring fractionally a lot more precipitation to the region, a lot more winter precipitation, particularly to northwest India and southern Pakistan. Western disturbances come with impacts as well, and I'll just talk about this very briefly, but these are two such impacts. So at the top here, we show that we're exploring very heavy rainfall. So in that big black box that covers much of Pakistan and northwest India and some of Afghanistan, I took the strongest winter and summer precipitation events that occurred and located the nearest Western disturbance and or tropical depression or tropical storm or tropical cyclone, and then mark them accordingly. So where the green dots are show that winter heavy precipitation events occur almost always under a Western disturbance. Over 95% of winter extreme precipitation events are caused by a nearby Western disturbance. And we can't make such a strong connection in any other season or with any other type of weather system. As a result of that, because heavy precipitation falling on mountains is going to cause landslides, we can link it to landslide activity as well. And that's what we've done at the bottom. This is work carried out with Professor Dimri. And we showed that landslides occur much more frequently when a Western disturbance is present because they bring more heavy southwesterly moisture flux into the region. So let's have a look at how they're likely to respond in the future. This is how Western disturbances look in climate models. And what I've done here is track Western disturbances in lots and lots of different climate model outputs over different scenarios. Now, this historical period is marked in grey here, and you can see again a lot of that interdecadal variability. It's a little smoothed out when we average all of the models together, but you can still see it there. But as we move into GHG dominating eras, the GHG dominated era, you can see that a decline sets in. It's a significant decline in frequency, in Western disturbance frequency, and it comes with a significant decrease in their intensity as well, which you can see in the bottom middle plot. Now, the reason for that is the jet, as it is when we ask most questions about Western disturbances. Why does something happen? Because there's a change to the jet. The jet changes in such a way that that horizontal wind shear weakens in the vicinity of Western disturbances. So center of Western disturbance is marked with this magenta cross, and the shear across the Western disturbance decreases. That means that they have less baroclinic instability on which to feed, and as a result of that, you can see down here, there's the baroclinic angle falls, Western disturbances weaken and become less frequent, and as a result, we expect that precipitation, winter precipitation. Oh, sorry, I was getting a notification on the computer there. We expect that seasonal precipitation, seasonal winter precipitation is going to decrease. However, extreme precipitation, the signal of extreme precipitation is not easy to deduce from CMIT-5 models because they can't resolve convective processes. So we don't know whether extreme precipitation events are going to increase or decrease just looking at CMIT-5 models. And you can see, so the top two plots here show mean precipitation and maximum precipitation. You can see a coherent change in the mean precipitation, coherent decrease in winter precipitation, but there's a mixed signal for the maxima. And if we look at the histogram of precipitation intensity over the different models, you can see that generally over the lower values, there's a decrease. But as we move to the extreme right tail, the models can't decide. Some of them predict a decrease and some of them predict an increase over the Indus Basin. So to overcome that, we have to use a method called pseudo-global warming.
Dr. Hunt, your time is up. Dr. Hunt, your time is up.
I've got 5 minutes on the timer, Dr. Suresh.
Yeah, actually for invited talk, it's 13 minutes. So anyway, that has already been told. Can you please rush up? That is my
Yeah. Well, don't worry, it's the last slide. Sorry, the timer was confusing me. I was working onto that. Maybe you should fix that for future speakers. Okay, yeah. So we use a pseudo global warming method. What you do there is basically you force a very high resolution model. We've used WRF here, and at the boundaries you force it with reanalysis, but you perturb the reanalysis according to future climate scenarios. And basically, if you do that, you find that extreme precipitation is likely to increase, which we do with this accounting method here. We can look at that using moisture flux arguments and show that that's because moisture flux is increased into the region. So even though western disturbances are weakening, the dynamical weakening, the effect of the dynamical weakening is less than the effect of the increased moisture. Okay, I'll finish there. And thanks for the person managing the timer for confusing me horribly.
So actually, Dr. Hunt, I have got a small question.
Okay, sure.
In the projection that you had shown that earlier we had some kind of multi-decadal variation in the WD frequency, but in the projection it is just showing just a decreasing trend. Do you think that that multi-decadal variation is missed in the projection?
Here. In this slide, you mean?
Yes.
Yeah. So yes, if you look at individual models, you see that they do capture the interdecadal variability, but because the phase is not controlled very strongly, they're not in phase, and as a result, when you take the multi-model mean, you're not capturing the interdecadal variability because it's all smeared out between the models. If you were to plot this for a single model, you would see both interannual and interdecadal variability that is a relatively good approximation of what we see in observations, even if the timing of the peaks and troughs is not matched in reality, because the forcing of the models is not constrained to observations.
And another comment is that that as per the projections about monsoon rainfall, it is generally said it is going to become more wet. That is being projected, and if I'm to believe to your presentation that winter is going to become more dry, so we are going to have a annual cycle to be more extreme, that highly wet during the summer and very dry during the winter, and that will have a significant impact on agriculture activity. So what is your comment?
My comment is I agree. I guess I'm not sure that was necessarily a question so much as an observation. Yeah, I think that's a fair observation to make. The fact that winters are going to dry is not a discovery that I've made. It's merely one that I've been able to explain using Western disturbances. That has been known, I think, for a little while now. Yeah, it's going to have a significant impact because the band where the drying is occurring most strongly is where most of the rabi crop is grown. So irrigation is going to need to improve in that region. And as I understand it, it is. There is a lot more irrigation infrastructure that's being put in to adapt to these changes. Of course, the problem is with increased extreme events, you risk flooding your crop. So you need to mitigate against that as well.
Thank you. Dr. Suresh?
Yeah. Yeah, thank you. You can contact, that's not a problem. Yeah, the remaining 4, probably ask them to stick to time. That's all. Okay, you can connect.
Thank you, Dr. Han.
Thank you. Thank you very much.
Nice presentation. Now we will move to the next presentation by Dr. Alok K. Mishra, Aisar Gopal. And Dr. Mishra, you will have a time of 9 minutes and 1 minute for question answer. You can start.
Okay, thank you very much. Is my screen visible?
Yeah, you can. Yeah.
Okay, thank you. Myself, Dr. Alok Mishra. from ISER Bhopal. Today I am going to present on atmospheric water budget on precipitation response over agroclimatic zone in India under high warming conditions. This is the result which has obtained from the regional earth system model. This work has been done in the collaboration of the ISER Bhopal and Institute of Oceanology Russian Academy under the Indo-Russian project. Just 1 minute slide. So outline for our talk is the first is the background of the study and the configuration of the regional earth system model over the Cardex South Asia, and the demonstration of the skill of the simulated result of the model, and investigation of the changes of precipitation over the agroclimatic zones, basically on the fine scales regional over the regional studies. And finally, we will discuss. I will discuss about the examination of the change in water budget component as a constant for the precipitations. So this significant we have already seen in the literature as well, or the lead talk and the invited talk. The climate is changing, and due to that changing, precipitation has altered very much, especially on the local scale. So that have the very tremendous impact on the regional society as well ecosystem. For the reliable projection of these changes is very important for the effective mitigation and adaptation strategy. So improving how this reliable projection can be obtained. In this regards, improving the processes associated with precipitation changes is highly demandable. Various modeling studies have been shown the absence of air-sea interaction was the one of the key source of the precipitation uncertainties. Further, the coupling has been done and found that the is very success in the improving the performance, and despite the good amount of success, the couple model still shows the huge amount of the bias, particularly in terms of the dry bias over the India. So how these uncertainties come from? So one source of this uncertainty might be the coarser resolution. So the increasing of the resolution is the demand. So in this, we have used the regional earth system model over the Cardex South Asia domain, and these are the agroclimatic zone over the which model performance as well as changes has been demonstrated.
Can you please put on the full screen mode, please? Can you please put on the full screen mode, because your presentation is not viewable by some of the viewers.
Okay.
You can put it on the full screen mode by clicking Shift F5 or otherwise icon within
Thank you. Yes, this is the experimental design. In this model, we have used the regional atmospheric model REMO as an atmospheric component. Within that, the land model is also coupled, and the oceanic model MPI-OM within that the biogeochemical model as well as sea ice model has been already coupled, and in addition to this, we have also included in this a hydrological discharge model, and these are the coupling has been done with the help of the OSC's coupler. For the exchanging the information between the ocean to atmosphere and the atmosphere to ocean is done with the coupling frequency of 3 hours, and for the hydrological model the coupling frequency is for the 1 day. These are the CMIP 5 and CMIP 6 model. With respect to that, we have demonstrated the added value of our simulated results. This is the JJS mean precipitation obtained from our simulation, which is Rome, and CMIP 5 and CMIP 6, and this one is observation. With this, we can see that the model is very good to capturing the spatial variability of the precipitation, high precipitation over the Western Ghat, Northeast region, and to some extent over the Central India. This is better than the CMIP 5 as well as CMIP 6. There we can see here the large dry bias over the central region. So improving the performance of our regional Earth system model adds the reliable for the projection. So further we demonstrated the model skill in terms of the quantitative estimates, some statistical metrics by the Taylor sticks. Here we can see this one is the the model which have been used here. The performance of this model is very good and high in comparison to the CMIP 5, CMIP 6, as well as the some Cardex simulation, regional Cardex experiment also. So this is the projection of the precipitation. So we can see here we have demonstrated computed the projection in two time parts. So one is for the middle future and one is for the far future, and this is the demonstrated with respect to historical period of the 1915 to 2014. Here we can see the large alteration of the precipitation, large response of the climate change, and the dual response we can see here. So over the some regions precipitation is going to increase, as well as some regions are going to increase. So very large heterogeneity over the some regions. Northern region we can see the change response is very little, but heterogeneity is more. Further in the far future we can see here that the regions of either increase enhanced precipitation or suppressed precipitation region is widening is occurring. So the regions of the extreme increased precipitation is going towards the eastern coast of the India, and this is zonal extension towards the western coast. Further we make the quantification for the all the agroclimatic zones. Here also we can see the large variations in the trend for the all regions. Some regions shows the significant amount of the increasing trend, and some regions shows the insignificant nearly zero trend, as well as in addition to this we also can see here some regions are having the decreasing trend. So one important message is in this is the one must be very careful averaging the when we are increasing the time series of the trend. One must be very careful in the selection of the region for the averaging. For example, if we take this one region, this contains the region of the increased precipitation as well as suppressed precipitation. This might be compensate both response and maybe not project the actual which is going to occur. So this must be very careful in the selection of this. Can be taken care by the taking very small areas for this.
You conclude only 1 minute.
Yes. So for the remaining the biases over the risk, one of the content is the water budget. So here we can see here the evaporation is going to change, and wind is also going to change, but for the wind this is a large scale phenomena. This is not much of a heterogeneous as like the precipitation. So in conclusion, a high resolution regional Earth system model is implemented over the Cardex South Asia. Performance is evaluated and found to be good with respect to previously global climate models, and intensity as well as spatial variability of precipitation is found to be substantially modulated in the warming climate. Component of water budget alter the contribution of precipitation change. Thank you.
Thank you, Dr. Alap Mishra. So I think time is over, so we don't have much time for next question. So therefore we will move to the next topic. Thank you, Dr. Mishra. We will now invite Dr. C.D. Jain from NARL for his lecture.
Yeah.
Dr. Jain?
Yes, hello. Can you hear me? Is that okay?
Yes.
Yeah, okay. So I'll just share my screen.
Dr. Jain, you have only 9 minutes, so please.
Okay. Is it visible, my screen?
Yes. So you can.
Is it okay? Is it full screen now?
Great.
Okay, thank you. So I'll be talking in next 9 minutes. I'll be talking about the local emission and long range transport impacts on the CO, CO2 and methane concentrations measured at a tropical rural site. This study is slightly different than the other studies, what we have seen till now. So this is a pure observational study where we have done the measurements and then we tried to understand the local emission and long range transport impacts. And this is the outline of my talk. A brief importance about the GHG measurements and then observational site and measurement details, results and summary and conclusions. Coming to the importance of GHG measurements, we know that what are the physical drivers of climate change, mainly carbon dioxide, other greenhouse gases like methane, nitrous oxide, halogenated species, and so on. And then we know that what is happening with them post-industrial revolution. We see that there's a continuous increase in the CO2 as well as in methane. There was a little bit plateau in between, but again, it started increasing post 2005 or so. So there is a continuous increase and that gives the continuous burden on the climate change issue. When we separate out the natural drivers and human drivers, we can see that the natural drivers are almost stable during these years. However, the human drivers or the anthropogenic emission problems are increasing as well as the temperature we have observed. So there is a one-to-one correlation between the human drivers and the observed temperature change. When coming to the anthropogenic sources for the greenhouse gases, we see that there are different sectors here. Industries, power stations, waste disposal management, residential emissions, transport. So many other things are in total. There are something like the total GHG emissions, around 72% is carbon dioxide, around 20% is methane, and then rest is other gases which are included here. So and then when it comes to CO, it is not a greenhouse gas as such directly, but it has close interlink with the CH4 and CO2. For example, CO and methane are the main main sinks for the OH radical in the atmosphere, which eventually lead to the formation of CO2. So there is a close interlink in cyclic tropospheric reactions here. And when it comes to the global carbon emission scenario, if we see India comes among the top contributor towards the carbon emissions. This is the latest one we have seen in up to 2021. Some part of the 2021 is still the projected mode, is not this one. So it is important for us to understand what is the scenario of these emissions in India. For that, one of the requirement is the field measurements, which is very, very sparse all over India. Hardly few stations are there which are monitoring the greenhouse gases. And also that the measurements comes with another challenge where we see that there will be local emission impacts as well as long range driven background concentrations. Local emission impacts needs to be taken care while looking for the long-term increase or decrease in the emissions. Now coming to the observational site and measurement details, the observational site is at NARL Gadanki, which is in the southern peninsula of India. You can see that here. So this is a rural site, but however there is a highway which is in the proximity around 500 meters from the measurement site and also a small village. So it's a typical ideal tropical village environment where we can see that some anthropogenic influence is there because of the highway going through. Other than that, there are not any major anthropogenic source problems. Now coming to the measurement details, the measurements are done with the Picaro G2401 CRDS instrument, which has been calibrated using the NOAA cylinders, 6 NOAA cylinders according to the WMO calibration guidelines. And then the CRDS, the instrument works under the CRDS principle, where we have 3 highly reflective mirrors, and the light is sent into the cavity comprising of these 3 mirrors. And then we can see that the lifetime of the light inside the cavity with and without a particular absorbing species like CO, CO2 or methane is measured, and the difference we will get into the concentration of the species. Coming to the results, so the panel here, left panel here, you can see that the time series, there is a strong day-to-day variations and seasonal variations, and also the diurnal variations, what we have seen already. So the thick black line in this panel shows the background variations, without the local emission impact. The background variations background is calculated Either you can measure it in a pristine site, or you can use the 50th percentile method, or minimum diurnal value method. Both the methods are accepted in the recent scientific literature. So in this method, we have in this study we have used the 5th percentile method. The black thick line represents the background concentration. Wherever above that is the local emission impact, where you can see that a significant amount of local emission impact is there on all the 3 species. And then this shows the seasonal variation and also the diurnal variations here. We can see that most of the things, except the CO, all other species are daytime minimum and nighttime maximum, except CO. During the summer period, you can see that there is a daytime maximum for CO. That I will come back to it later. And then this panel here shows the trends during these measurement periods. 2016 to 2019 is the measurement period what we have considered. You can see that there is a significant decreasing trend for CO, whereas CO2 and methane have the significant increasing trend, and the CO2 and methane trends are marginally higher than the global trends, where we have used the NOAA data, GML data for calculating the global trends here. Even though this is a short period, 3 years is not a huge period for climate, for calculating the trends and all. However, this gives a rough idea what is happening in the site. And then now coming to the local emission impacts, as I said, the local emission is the concentration excess above the background concentrations. We have calculated by subtracting the variations from the 5th percentile of the daily mean values. And then we see that CO has the highest excess concentration compared to the CO2 and methane. CO being a short-lived species, which has the highest local emission impacts, whereas the methane and CO2 are being the long-lived species, they have the lowest local emission impacts. And then this panel here, which shows the MODIS fire data for the site around 100 kilometers of the site, and then which is used. This is in a qualitative measure again, because of the cloud screening. The spots what we see here in this panel may not be true representation of the fire events occurred during the period. However, it shows the hot spots. We can see that in this direction, the center cross point is the site, and where you can see that northwest and southeast direction, there are hot spots of the fires in the site. And then we can see that when there are higher fire occurrences, we have seen more CO. So CO is used as a marker for the combustion here. So this gives that there are a significant local emission impact on the CO, whereas the impact on the CO2 and methane is mostly towards the long range transport. Now coming to that, this shows a correlation between the two species like CO, CO2, or CO2 methane, or CO methane. This exercise gives us whether there are common sources for both the species, or the sources are different. Normally, CO is not correlating well with any of those species like CO or CO2 or CO methane, showing that CO sources are completely different. However, in the winter, there is a slight correlation for CO and methane, which may show that biomass burning during and around the site here, because biomass burning also gives some sort of methane.
Only one, not more than 1 minute. Please conclude.
Sorry?
Time is only 1 minute. Please conclude.
Okay, fine. So this only one slide is there. Okay. So this shows the bivariate plots, which gives the correlation with the winds occurred at the site along with the excess concentration what we have seen. We see that the winds at the site are correlating well with the concentration observed. So that means that there is significant local emission impact as well as long range transport also. This exercise gives the CWT, that is the concentrated weighted trajectory during the summer period, mostly the local sources in this one, wherever in the winter and this one, you can see that long range transport is prevailing. Similar results from the flex part, where you can see the switchover from southwest monsoon to northeast monsoon, where both the winds are prevailing at the site. So that has got the highest impact over the concentration observed. And the last part is that we have also compared with the satellite data because Gadanki is a boundary layer site, wherever Mauna Loa is a above boundary layer site. So we wanted to take this opportunity to study the sensitivity of the satellite observations for the boundary layer and above boundary layer. We can see that there is significant bias in the Gadanki values, wherever the Mauna Loa has the lower bias. So we have done the corrections, and then we concluded that boundary layer measurements of the satellites for these species need to be interpreted with care, where there will be a lot of biases. And then to summarize, local emission and long range transport impacts have been investigated. CO found to be the most locally impacted species. Forest fires, agriculture, residue burning are the dominant local sources which contributed for the local emissions. A trend analysis shows significant decreasing trend in CO and increasing trends for CO2 and methane. Comparison with the satellite data with surface measurement showed the significant biases. So we need to be careful while using the satellite data for boundary layer studies of these species. For more details, you can go through this paper. Thank you very much.
Thank you, Dr. Jain, for an excellent presentation. But I was, slightly worried that, you have data only up to April 2019. Otherwise,
Correct.
we could have seen, during lockdown,
Correct,
what
sir.
really happened. So
Yeah.
it would have been
Yeah,
very
yeah.
interesting if that data was there.
No, sir. Actually, we have the data. We have omitted that because that is not a general year. So for this one, we cannot take with this study because all the preceding years are business as usual years, wherever 2020 was a unusual year. So that has to be treated separately. So that is why we have omitted that in this study. But we are coming up with that also. We can see that here. Just I will go through quickly this introduction part what I have shown. Okay, here you can see that in this projection, this slight decrease here, right? All these things here. Are you seeing this, sir?
No.
So you can see here, right? All other countries. There is a slight kink in at the end of the 2020. This is because of that lockdown.
You are not sharing.
I'm sorry. Just one second.
Okay.
Yeah,
Okay,
I'm sorry.
okay.
Yeah.
No issues.
No issues.
You are in full screen mode.
Yeah, I understand. So yeah.
Nice.
Is that okay now?
Yeah.
Yes.
Yeah, so here, sir, you can see at the end of this here, so there is a slight decrease, kink or something is there. So this is because of the 2020 changes. Definitely, that is an interesting study. Thank you for bringing me, reminding me that.
Yeah.
Definitely, we will take up that study, sir, in near future.
I agree. So this is more of global. So I would have seen that Gatangi, what was the,
Yes, sir, sure. We will look into that because when we were preparing this manuscript, the 2020 year was not complete. So we just omitted that actually.
Okay. My suggestion is that you ensure the quality check of the data.
Yes,
so
sir.
that it will go for the future climate use or something like that. Right now,
Yes.
also you are comparing with the Mauna Loa and other thing. You're doing some correction, etc. You said.
Yes,
so
sir.
Go further and then make a quality check. Then use it as a
we
data
have,
bank.
Yeah, we have already done that, sir. The data is WMO standard data, and then we are also doing an inversion modeling study with this data.
Okay, please go ahead.
Sir. Okay, sir. Thank you very much. Yeah.
Thank you, Dr. Jain. So
you.
now we will invite Dr. K. Koteshwar Rao.
No, I think it is not there. Now, probably, instead of that, in the recent schedule, they have given Rahul and Vijay Kumar. You can invite Rahul.
Okay, Rahul. Mr. Rahul from Goa, MC Goa, I think.
Yes, sir. Good afternoon, sir. I'm sharing my screen. I hope it's visible.
Yeah,
yes.
Visible. Go ahead. You have 9 minutes and then try to complete in 9 minutes and then avoid unnecessarily introduction stages, etc. And then straight away you can go to mere observation or experiment and then result, etc. Okay.
Right, sir. Right. So this presentation is all about the operationalization of district level impact based weather forecast for heavy rainfall that was implemented by Meteorological Center Goa, which is the nodal agency of India Meteorological Department for the coastal state of Goa. And we will.
Can you please put it on the full screen mode?
It's already on the full screen mode, sir.
No, I don't think.
I have put it on the full screen mode. Maybe it's taking a while for you to reflect.
Okay, fine.
I hope it's visible. Okay, so we will go to we will discuss about the outcomes and the scope of this impact-based forecast that IMD Goa has been issuing. So we will have the contents, like we will have an introduction about what is the impact-based forecast, and we will we will see how India Meteorological Department Goa did the classification of these impacts, identification of these impacts, then how it was implemented. We'll take a case study of July 2021, and then we will discuss a little bit about identifying the thresholds, how we determine the thresholds for each and every impact. Then finally, the lessons and challenges. So this WMO guidelines number 1150, which stresses to the fact that now in coming days, weather forecast will not be about what the weather will be, rather it will be about what impact the weather could make. And it's underlined again and again that people are now demanding information about what to do to ensure their safety and protect their properties while severe weather activities are taking place. So to come to that level, to have this impact-based forecast realized, we need to have a bit of information on our hand in the beginning itself, like what could be the possible hazards that could impact a particular place and where these impacts could be, and when or what is the threshold for these impacts to take place. Now we are discussing about this WMO guidelines. It defines about 3 paradigms of impact.
For a slideshow, you can show slideshow so that it will be bigger. No?
It's already on slide, so sure. I'm just changing it back to other mode.
Anyway, continue.
Okay. So the thing is that WMO guidelines defines 3 paradigms. The first paradigm is forecast is about the severe weather, what the severe weather is going to be. And the second paradigm is about the impact, what the impact that severe weather can make. And third, and the most important part is like pinpointing to the locations and telling that it is on this place the impact is going to take place. So these are the 3 paradigms that the WMO has defined for impact-based forecast. So to go along with that, IMD Goa or Meteorological Center Goa has collected information from Directorate of Fire and Emergency Services in Goa, who are the first responders for any of such impacts that are recorded. So we collected data from them for the past 4 years and plus 2021. And we try to identify what all are the possible impacts that Goa was facing in these past 3 to 4 years. And we try to correlate it with the actual rainfall that was recorded over these 4 years. And we try to correlate, or we try to figure out some relation between these events as well as the continuity of rainfall or the quantum of rainfall which led to these events. So this is in 2017. And this is in 2018. These red dots or the orange dots, what we find here are the dates when some impacts were reported. Now, what we find in 2019 is there's a significant number of events that were reported compared to the past 2 years, and similar scenario repeats even in 2020 also. Why? Because these 2 years were the excess monsoon years. Goa recorded 33% and 41% of excess monsoon rainfall in these 2 years, which obviously led to more number of incidents and more number of heavy rainfall related impacts. Now, from that information, we collected the possible impacts and we categorized them into minimal, minor, significant, and severe. Then we arrived into a conclusion like what should be the criteria, what should be the existing situations based on which these scenarios should be given the ultimate priority, and on what basis these should be issued to different regions. For that, we compared, like it was mentioned previously, we compared it with the rainfall situations, and then concluded that this much of rainfall or this quantity or this intensity of rainfall may lead to these impacts which are of this severity. Now let's take an example of this July 2021 for the period from 10th July to 23rd of July. Why this period is important is because in these 14 days, Goa received a rainfall amount which was more than double its actual normal value of rainfall for that particular period. And it led to a flood-like situation in Goa, which the media and administration stated as the worst flood in 40 years. And like we were mentioning in previous slides, apart from this forecast, it's as important as the forecast it is to disseminate this information to the public as well as to the administration so that the precautionary measures can be taken. So on the right hand side here, what we find is the number of bulletins that Meteorological Center Goa issued during these periods. And when again going back to those paradigms the WMO has defined, we IMD follow a certain set of procedures, like in what frequency we have to issue bulletins and what all information should be there in bulletins whenever the forecasting station is expecting some intense rainfall activity. So this is the first paradigm, or rather something we can call a second paradigm, where we are forecasting impacts the possible impacts we can very well see here what all were forecasted for that particular period. And this is something we will term it as a press release or special bulletin which were issued for this.
Rahul, sorry to disturb you. Actually, your slide is not moving, and can you also show full slide? Actually, you are your slide also not moving.
I have my own apprehension because he is the fourth slide out of 23 slides. Already 6 minutes are over. Maybe explaining more and then not advancing the slides.
Yes.
It's better. You are having hardly 3 minutes now.
Yeah. Continue.
I am actually at my 12th slide, sir.
Yes.
Due to some issues, I don't know. Maybe the slides are not changed.
Can you full slide show? No, it is not.
It's on the full slide as well, sir.
Yeah. Anyway, not anyway.
Should I take my time little bit and try to share it again?
Right now you are in 12th slide. You advance.
Okay, sir. Fine then. And then okay. So these press releases were issued every third or fourth day, and we gave an indication like what could be the possible impacts on those particular days. And then we are slowly shifting to the second paradigm, more closer to the third paradigm, where we are issuing these bulletins every day, and we can see the impacts which were issued. They were on daily basis, and we were specifically mentioning the regions on a larger scale which could be impacted with these events, and we were giving the color coded warnings like to indicate the severity of these situations. So that is the second paradigm of impact based forecast. Now in the third paradigm, if you can see this slide, we were actually going to each and every taluka, which is the lowest administrative level boundaries as far as the region is concerned. So we were specifically mentioning the taluka names, and we were specifically describing what could be the possible impacts. And these were issued every 6 hourly when the event was taking place. And we can see gradually how India Meteorological Department has shifted from the paradigm second to paradigm third while we are discussing about impact-based forecast. And this slide here is all about how the information was being disseminated through the website, through the WhatsApp accounts, Facebook, Twitter, social media, and all the possible means. Along with that, one-on-one discussions with the State Disaster Management Authority as well. Now, this slide here describes about the actual impacts that those were realized, and almost all the kind of impacts, whether it be about falling of trees, collapsing of weak structures, or flooding near the river areas, or water flowing over small bridges and culverts. All these statements, most of these statements that India Meteorological Department issued as an impact-based forecast were realized, and we can see there are some newspaper cuttings here where it is very clearly mentioning that India Meteorological Department had, in fact, very well given information in advance. It was given information that there are regions which are vulnerable for flooding. Now, in this slide, I've described about the impacts that were recorded for a period of 14 days. And the whole purpose of showing this slide is that the impacts were not actually of a single day or a particular day in this 14 days. It was actually all along these 14 days. And that's why IMD had to be on its toes and keep on issuing the forecast, impact-based forecast and everything. Now, this slide is actually about arriving to a threshold. This is like the impacts reported on a particular day and the 5-day cumulative rainfall over that particular station, which led to that impact. So we can see a lot of variation in that, spatial as well as temporal. And now about the challenges and lessons that we have faced and learned in this particular period, we can see that the number of events are actually increasing, and the area of impact also keeps on changing. And the impact-based forecast requires frequent update and frequent mapping of vulnerable areas. And the state disaster management authorities have to be kept in confidence and good belief of IMD so that we can properly issue these warnings and get the better result. And finally, this slide is a number of paper cuttings which mentions that India Meteorological Department could issue this forecast or foresee these impacts well in advance, and that has actually helped administration to take the necessary steps. So that concludes my presentation here. I'm sorry, sir, due to some network issue, I believe you could not see most part of it.
Okay, thank you, Dr. Rahul. Probably, I appreciate the paradigm shift, what you are mentioning, probably IMD reaching to the districts. Continue the good work.
Thank you, sir. Thank
you. Is there any question from the audience side? Viewers?
Thank you, Rahul. Actually, you have done excellent presentation. So Suresh ji, we can call the final.
Yeah, yeah, I'll call him. Dr. P. Vijay Kumar.
Yeah.
Okay, sir. Thank you. Can you hear me, sir?
Yeah, you are audible, and then you can put it in the full screen mode. Probably you can try to complete in 9 minutes.
Okay, sir.
Keep the presentation in full screen mode. Yeah.
Is it visible, sir?
Fine. Go ahead,
Okay.
please.
Okay. My topic: mini cloudburst events in Kerala and the structural changes in monsoon clouds is a work recently published in Weather and Climate Extremes and contributed by these authors. We know that Kerala has been creating headlines for the bad weather it has been experiencing for the last many years. Among them, the 2019 and 2021 mini mesoscale cloudburst events that are very much worrying because it has more signature of changing pattern of climate and or something related to climate change that is visibly observing here. We know if we consider the entire Indian region, we have two pockets, Indian region as well as the surrounding region. We have two major places where maximum rainfall is obtained. One is in the Myanmar coast and another is the Western Ghats region. These two regions have somewhat similar geographical features also. There are mountainous regions near to the coast and the wind is flowing across it, so that but one difference is that along the west coast most of the rain is produced by shallow to medium clouds, whereas in the Arakan Mountains, Myanmar coast, where it is mostly very deep clouds. And if we define extreme kind of rainfall, more than 1 centimeter in 1 hour, we can see that maximum of that concentration of that or maximum frequency of such events occurs in the northeastern states, and we have almost half of the rainfall received in that region from such high intense rainfall. Even though total amount of rainfall received in the Rajasthan region is low, almost half of it is received in high intensity. Whereas even though only frequency of occurrence of rainfall intensity exceeding 1 centimeter in 1 hour is low over the west coast region. Whatever little that is obtained from medium to shallow clouds, not deep clouds. This color indicates depth of clouds. Blue indicates higher cloud tops. Most of the clouds in the west in the Bay of Bengal are very deep, whereas the clouds that is cloud top temperature actually. That temperature is warmer. Warmer means it's the top of the cloud is at a lower height. And the data source is INSAT, Kalpana 1 IRBT and TRM GPM rainfall data. If we have on the in this right panel, we have deep frequency of clouds and extreme rain frequency plotted together. And what it gives is that over the Mumbai latitudes near to 18 to 19 degree north, the x-axis is the latitude, where we have deep clouds accompanied by high intensity rainfall, whereas in the west southwest region we have high intensity rainfall obtaining from shallow clouds. Konkan region is also have been identified as a major hotspot of heavy rainfall, and in a study by Francis and Cadgill, it shows that that study period was 1974 to 1998. They show that the rainfall is concentrated mostly in the 15 to 16 degree north latitude in the Konkan region. But in our present analysis that is pertaining to 5 years, and it's 2013 to 2017, we find that high intensity region has shifted more southward, and a peak is observed in the 11 degree north and 13 degree north latitude. And if we compare the 2018 and 19 rainfall events and the flood that followed, we know that 2018 was above normal and consistent from the beginning, but a little rapid on 15th August. But that rain was distributed almost equally throughout the day. But in 2019, rainfall was below normal up to the first week of August, and on August 8th, sudden downpour occurred, and it was almost 10 times higher than the climatological daily mean, and that happened just in a few hours. That made such intensity of rainfall and flash floods and landslides that followed it. And such intensity of rainfalls comes under the classification of mini cloudburst according to Deshpande et al. 2018. And we have seen that this synoptic conditions in these 2 years were they had some similarities as well as differences. Major similarity was that this is 850 hectopascal wind obtained from ERA 5, and we had the presence of a monsoon depression in the Bay of Bengal as well as a typhoon in the South China Sea. Also, LLJ was strong and about around 20 meters per second at 850 hectopascal during both the years close to Kerala and the offshore near to it. But the one difference was there. In 2018, the surface temperature in Arabian Sea and most regions of the North Indian Ocean, it was nearly normal. Whereas in 2019, SST was 1 to 2 degree higher near to the Kerala coast. And this would have created a situation where the Cape values could have gone high. And the study that Kumar et al. 2014, they say that in Myanmar coast, it was a comparison between why the rain that occurs in the high intensity rain that occurs in the west coast is having only shallow clouds, but that in the Myanmar region grows very high. They say, observed that the Cape values near to the eastern boundary of Bay of Bengal was high. That would be generating allowing the clouds to grow to higher levels. Whereas we have previous studies also, Rao et al. 1976, etc., which shows that west coast region we have clouds growing up to a top of the clouds up to 8 kilometers. Most of the clouds that are formed in this region are from orographic origin, and they do not have a tendency to grow high, because of the low Cape values. But high Cape values can support and make structural changes in clouds, and clouds can become more cumulonimbus type and lightning and thunder, which is unusual during the monsoon period in this west coast region, especially south of 14° north latitude that Kerala is belonging to. And this region has been continuously observing some kind of changes in the structure of the clouds as well as the nature of the rainfall that is being received in this region. And we have a comparison of 2-hour cumulative rainfall obtained from GPM I-merger that is 0.1 degree resolution and half-hour resolution, temporal resolution. And we can see that it's in 2018, this distribution, even though total rainfall was 8 times higher than the daily mean on August 15th. The 2-hour rainfall distribution was almost equal. Throughout the 24-hour period on 15th of August 2018, it rained. That was the peak rainfall day, which produced that flood event in 2018. And the distribution was equal, so that no signature of mesoscale mini cloud or any kind of cloudburst event was not there in 2018. But in 2019, if we see, there are many pockets where rain exceeded more than 5 centimeters in 2-hour period, and such a classification is comes under the mini cloudburst event. And the distribution, if we see, that is mesoscale. That means more than roughly 50 pixels of 121 square kilometers have recorded rainfall between 40 and 50 millimeter, and a few 10 or 20 pixels have recorded rainfall between 50 and 60 millimeter per 2 hours. That means intense rain crossing magnitude 4 centimeters per 2 hours was absent in 2018, even though 2018 has been considered as a major flood event in terms of the number of casualties and the losses it suffered. And it was not on a single day's rainfall, but accumulated rainfall from so many days from the start of the season that created that havoc situation in 2018, whereas in 2019 it was a single day's rainfall, that is August 8 to 2019, that made all the differences and produced all the problems here. And it overtook the normal curve on that particular day in 1 or 2 days, and after that rainfall consistently became normal, but remained on the top above the normal line. Yes, sir. I'm coming to my last slide. Actually, we have in 2019 also. If we are wondering if 2019 was a beginning. This year, last month, on 16th of October, we observed a similar kind of situation here, and this is a daily total rainfall in which we have 1 pixel, which is showing a value for 28 to 32, around 28 centimeters of rainfall in a single day. That occurred almost in 4 hours. That means in some hours, rainfall of around 8 centimeters have occurred. And such events, even if we are considering 2019 as a starting point, such events have occurred once more, and we conclude that such events may recur in Kerala, especially when dynamic and thermodynamic factors come in mutually supportive way. And this may be one of the ways this climate in this region is changing in future. It is a worrying situation. Thank you.
That is a nice study, Dr. Vijay Kumar.
Thank you, sir.
And I have 2 observations. One is that you were talking about CAP, convective available potential energy, and then you were just corresponding with the study elsewhere also. As far as the Indian weather condition, especially southern peninsular India is concerned, CAP is considered only as a necessary condition, but not a sufficient one. Even 2000 joule per kg or 4000 joule per kg will not give that amount of rain which is supposed to be given in US or elsewhere. Okay, we have to be very careful, and then the CAP study you can again relook into. The second one is that most of the talk concentrate only on the structural change over the monsoon clouds and then monsoon related rainfall. Just before the onset of monsoon or during the monsoon period itself, I don't recollect the date exactly. There was the windstorm as well as the rainstorm, which caused a lot of havoc north of Cochin radar, which is exactly north of Cochin radar, and then some 30 to 50 kilometers, so much amount of damages were there. So that also you can include and then make it as a corroborative paper and then do a good job. That is my suggestion.
Thank you, sir. Yes, thank you, sir.
Is there any question or compliment from viewers? If there is none, let us thank Dr. Vijay Kumar.
Thank you, sir.
And with this, we have come to the conclusion of the first technical section in INTROMET 2001. In this particular session, we had a variety of papers, lead as well as invited, as well as the contributed papers, which had a variety right from model projection, model simulation, land ocean coupling, and observational studies, and a thermodynamic part as well as a statistical modeling part. Let me thank on behalf of the organizers and on behalf of my co-chair as well, all the speakers and all the viewers for an effective contribution for this session to be live. Thank you all. Is there anything you want to say, Dr. Pai, or we will be passing over to organizers?
Yeah, I agree with you, Dr. Suresh. It was, very, all the 8 lectures very excellent, covering various aspects, starting from global level climate projection, change projections, and then impact of land cover, land use, and then also moisture, impact of moisture on extreme rainfall, and also ultimately discussion about how impact-based forecast can be developed actually to adapt to extreme events related to climate change. So overall, this was a very excellent session. So I thank all the lectures, and let us go back to the organizers. Thank you. Thank you.
Organizers, would you have any announcement?
Yes, so thank you all the Thank you, the chairs and speakers of the section. That was a wonderful technical session, and it's end of that. So we will now disperse and for a short break, and we will join back at 4:40. Okay. So that is the end of first technical session 1A. We thank the chairs and speakers of the session. We will now disperse for a short break, and we will rejoin back at 4:40 for the releasing of special postal covers. Thank you.
Thank you all.
Thank you.
Hello, hello. Hello, hello. Hello. Hello, hello, hello.
Hello, hello. നേരത്തെ മാസ്ക് മാറ്റിട്ട് ചേർത്ത് വെച്ച് സംസാരിക്കും. ഓക്കെ മാസ്ക് മാറ്റിട്ട് ചേർത്ത് വെച്ച് സംസാരിക്കും. കേൾക്കുന്നില്ല.
also excelled well in various positions, and she has got the recognition, international recognitions. She also become the fellow of the Academy of Sciences, got the even World Meteorological Organization award, and that she is her talk also. She has trained many people in like Dr. Sriya Sridharan and many other excellent people here. So I think she died in the age of 93 in Trivandrum. So she is the second person we want to remember, and a lot of contribution in the field of atmospheric sciences and the instrumentation and solar radiation measurements. The third person is well known to most of the recently, Professor P.R. Pishardi. Professor P.R. Pishardi is also belong to Kerala, that is Kollangodu, in the Palakkad district of Kerala. And he also, after graduation, he went to Professor Sir C.V. Raman. All three people are belong to Sir C.V. Raman. Then he showed a lot of about the spectroscopy, his mainly work. Then later he joined with the India Metro Department. He worked in various positions. He is considered as the father of remote sensing, father of Indian remote sensing. Even Cochrane built that disease. He's through the remote sensing. He is the person who has done all things, and then we tried to find out this main. Professor Pishardi is also involved in many activities. He visited Cochin University on several times. He is I think he selected me in the Cochin University as a faculty here. He was also earlier when my PhD examiner, and his memory is so excellent. So when I was doing in IIT Kanpur, and I met him there. When I met him some other meeting in Bangalore or somebody, he asked, "When did you come from Kanpur?" I surprised because I was earlier one of the student at that time. He still remember each and every person very nicely. And Professor Pishardi is also got in the Padma Shri. And later he was in I think 1996 we conducted, the Department of Atmospherics conducted a symposium on the climate variability and predictability. And I think he came here the previous day, Hartal has declared unexpectedly at 6 o'clock. So tomorrow, then we in the whole night, I think we shifted all the delegates from staying in different places to the Cochin University guest house. And Professor Pishardi is also shifted to hear our guest house room number 1. He was staying in the room number 1. And he has given the talk, inaugural talk, and evening he left. On the way, he had been an accident. On the way back to airport, somebody had pulled a trolley and he in his leg and some fracture. After that, I think he could not move further. That is something we can never forget. And he is also involved in many activities in Cochin University. I think even he was our member of Board of Studies. Professor Anandarshan is also a member of Board of Studies. Ms. Annamani is also a Board of Studies member. So here they have also contributed a lot. I think this is a right occasion we can commemorate in releasing the special cover. So that is the thing which we would like to. So I'm happy to my duty of welcoming the members. The professional address, that is the presiding Professor P.G. Shankaran. He is the Vice Chancellor of Cochin University of Science and Technology. He is with us on all our activities, and he used to come some of the activities here and encourage it. Even before that, I think in the Vice Chancellor, even before that also he comes and encourages. So on this occasion, I'm very happy to welcome on all behalf of Indian Meteorological Society. Srimati Mariamma Thomas, I think Postmaster General of Central Circle, Kerala. Madam, I think now we are seen here in the Cochin University campus and our activities. Definitely, before going out, we will show the what are the radar facility, and we will explain how the work is going on. Actually, this for your information, this is an international facility. This facility, this type of radar is not available in the earlier. So far, it was designed in a different way in many other places. In India, I think we have got the National Atmospheric Research Laboratory in Tirupati. The ISRO has developed a system long back in 25 years back. But that radar is entirely different.
that radar is in a very big area, 4 acres of land full of antennas, very, very expensive. And no other, I think that is very expensive at the time. But this radar we designed is a frequency of 200 megahertz frequency. Nowhere in the world it is not there. So in the Department of Science and Technology, Government of India had a plan to install this type of radars for improving the weather forecasting system. So they suggested whether we can opt the older one or the new one. New one is a risk because it is not proven. So we took the risk and then we want to install it in a building top because it is very, very economic. And it is very much cheaper than comparing to the power is less. So we tried because we had a lot of problems in the initial. We don't know how it can be designed, even from the design, development, and installation, everything done in India, or in our Indian scientists and engineers, especially from the, because not for, I think we have got many experts from ISRO and many others, DRDO and many other institutions. They came here, they given training and all things, and these people have done this. And within 3.5 years or 4 years, we could achieve this. Nowhere, I think, it is possible. Even Department of Science and Technology, their own radar system in Nainital, it took 12 years. It took only in the university system, it took only 4 years because of a very good cooperation between all the factors, university and DST and our expert committee members. So we will explain that. So this is only for introduction about the radar system. So we, on behalf of our whole community in Cochin University of Science and Technology and our Indian Medical Society, we are happy to welcome you. Dr. Ramesh Kumar, I think there is no introduction gathering. He speaks more and more. Not now. He is just 2 years junior to me. So I know him very well from the last several years. So he has given the idea of starting the special issue at that time. So anyway, I'm welcoming my Dr. Ramesh Kumar. Of course, Abhilash is the Secretary of the conferences. It is international conference going on here. So the formality, I'm also welcoming Professor Abhilash for this function. So again, our team, our colleagues, friends, and students. The students are our strength, and research scholars, all people are here. So we are very happy that it is a rare occasion that we can introduce the eminent scientists working in the field to the youngsters, Professor R. Anandakrishnan, Ms. Anna Mani, and Professor Pishardi through this. And also, the other thing is we are also conducting a public lecture series by experts. From today, Professor R. Anandakrishnan, tomorrow, Ms. Anna Mani, and next day, and this Professor P.R. Pishardi. This can be viewed. Anybody interested, we will the link we are providing to all. This is the viewers. Thank you for.
Thank you, sir. Now I would like to invite Professor P.G. Shankran, Pro Vice Chancellor, QSLAB, for the presidential address.
Chief guest of the Navy, Srimati Mariamma Thomas, Indian Postal Service, Postmaster General, Central Office, Kerala Region, Professor K. Mohan Kumar, Chairman of this international conference, Dr. Ramesh Kumar, Chairman, Scientific and Technical Committee of the conference, Dr. Abhilash, my dear colleagues, faculty members, research scholars, and students, and my dear friends. It gives me immense pleasure to be here on the occasion of the special cover release as part of the International Conference Symposium on Tropical Meteorology. As you know, the Cochin University of Science and Technology is celebrating 50th year, and during the last 50 years since its establishment, it has grown in its stature making a mark for itself among the leading institutions in the world. So the university assumed its present shape as CUSAT in 1986. It is the reorganized form of the University of Cochin, established in 1971. It is an occasion that calls for befitting the celebration, or this is a time to appreciate the past, celebrate the future, celebrate the present, and inspire the future. We are celebrating the occasion with increased strength and pride derived from our achievements. As you know, we have climbed 80 places in the recent national ranking process, NARF ranking process in the year 2021, and have been honored with the Chancellor's Award for the best university in the state. We are also preparing for the NAC accreditation, and we will be submitting the report next month beginning. Our faculty members are getting various multidisciplinary and multi-institutional projects from different national and international agencies. This is achieved through filling up the vacant positions which we have done during the past 4 years. We are providing various schemes and support for research improvement in the university. We also have rolled out a vision plan, keeping in mind the developments in the next 10 years. As part of the Golden Jubilee celebration, we have planned a number of events and have taken up some new ventures. Due to Corona situation, we could not start many of the activities, but we have started one activity, which is the National Science Lecture Series, with the aim of sharing knowledge of eminent scientists with our faculty members and research colleagues. We have planned to conduct conferences and workshops in different theme areas. This is one of the such conference in association with Indian Meteorological Society. I congratulate Dr. Mohan Kumar, Dr. Abhilash, and the team for organizing this conference, which is very relevant in the current scenario. I'm not going to explain the theme of the conference or describe the theme of the conference. As part of the Golden Jubilee celebration, we already have released a special cover in association with Indian Postal Service last month in October. This is the second one, and this is to commemorate the 3 pioneers in the field of atmospheric science, and congratulate the Department of Atmospheric Science and Radar Center for arranging this function, which is very useful in the sense that it will increase the visibility of the CUSAT. I wish a very best to the program. I hope that we will cooperate with this Indian Postal Service in many ways, and we have already discussed some of the ideas with Srimati Mariamma earlier. I wish a very best to the program. I wish a very best to the conference. I wish a very best to the Atmospheric Science Department and this center. Thank you.
Thank you, sir. Now I would like to invite our guest of honor, Srimati Mariamma Thomas, IPOS Postmaster General, Central Circle, Kerala Region, to address the gathering.
President, Professor P.G. Shankaran, Professor K. Mohan Kumar, Dr. M.R. Ramesh Kumar, Dr. S. Abhilash, and members of the scientific community of the Cochin University of Science and Technology. For the Department of Post Central Region, today is a very proud moment because we are celebrating so many special things. We are celebrating the Golden Jubilee of the Cochin University of Science and Technology. We are celebrating the Cochin chapter of the Indian Meteorological Society. We are celebrating the International Symposium on Tropical Meteorology, INTROMET-2021. We are celebrating Dr. C.V. Raman, who I understand is the guru of all the three scientists we are honoring today through the special cover. We are honoring his students, that Guru Shishya Parampara, in that two scientists who were actually trained and guided by Dr. C.V. Raman have handed over that Paramparya to Dr. Anandakrishnan, Dr. Pishardi, and Dr. Annamani. And their students are present today honoring this Parampara of Gurus through special covers. It's a wonderful occasion. And they are bringing this tradition, starting from Dr. C.V. Raman, to a new generation of young scientists I find here today. The Department of Post is very proud to be part of this occasion. I understand that we are also celebrating through the location itself an indigenously built radar. That is a concept very apt for Atmanirbhar Bharat, which is a catchword of the government of India today. An indigenously built radar. And this special covers are being released in that same location. Also this year, the government of India is celebrating Azadi Ka Amrit Mahotsav, the 75th anniversary of Indian independence. And as part of that celebration, we need to remember all those who have brought honor and glory to the name of India. And from the introduction, we understand that these three scientists that we are honoring today through special covers are very much part of the pride of being Indian, of what India has to offer the world. I congratulate all those who have taken the initiative to celebrate this occasion through special covers, and we hope that the Department of Post will be able to join hands with QSAT and with the scientific community of Kerala in celebrating many more scientific achievements of this state and this country. Thank you.
Thank you, ma'am. Now I would like to invite Dr. M.R. Ramesh Kumar, Chairman, Scientific and Technical Committee, LOC Intromet 2021, to address the gathering.
Most respected President P.G. Shankaran, guest of honor Srimati Mariama Thomas, Professor Mohan Kumar, Dr. Abhilash. First of all, let me thank. In fact, the making of this special cover was a crazy idea. In fact, I wanted to have actually a stamp, as we were just discussing. By the way, I am the president of Goa Philately and Numismatic Society. So I have a craze of actually having stamp. In fact, very few stamps in India have been done on scientists. Maybe we have a P.C. Ray, we have Homi Bhabha, we have a Vikram Sarabhai. The most recent one was actually on APJ Abdul Kalam. And Ramanujam also is there. So this has been my passion. Maybe just like my meteorology, this has been my passion. And in fact, Sir C.V. Raman has actually a postal. He was actually worked for post and telegraphs long back. Okay, so it is very appropriate that his cancellation also has come. So we had an idea, and in fact, we wanted to have actually a C.V. Raman stamp on this special covers. Unfortunately, only we have actually a 10 rupee definitive stamp, which was not available, or maybe this one, or maybe some scientists. So we had ultimately put the Earth, which is actually now under the current topic of actually the changing climate is directly affecting the Earth. So we thought that at least the Earth or maybe the Sun. These are the two things which we are thinking actually for putting on the stamp. Because for a philatelist, there are several things which comes into picture. One is actually the caricature, which was very well made by one Rejoy, who has actually done a wonderful job. Plus, we have the radar center also in the part of Cache. Plus, we wanted actually a stamp for a philatelist, that is very important, and the cancellation. So, as Professor Mohan Kumar has correctly mentioned, all the three people, Professor Anandakrishnan, Mrs. Annamani, and Professor Pishardi, all were actually his students, and all of them studied at the Indian Institute of Science, Bangalore. In fact, Professor Anandakrishnan was my guide also. Unfortunately, I couldn't continue. My topic of that time was actually vagaries in monsoon, long back, which we see this year. In fact, this year we had actually a non-stop rain starting from April till today. Just now only we had actually rain. So whether people are asking whether it's a extended monsoon or a continued monsoon, or whether it's a southwest monsoon or northeast monsoon, or is it because of these low pressure systems, etc. So a number of questions are there, which I think Dr. Abhilash and Manoj are doing every day through the social media, public, maybe to their publications, or maybe whatever print media also they are doing. So this stamp collection has been my passion from a very childhood days onwards. In fact, some of the things which Cochin University can do now, maybe they can have some maxi cards, which I think the Department of Post should do. Because Cochin University has several facilities, especially our foreshore road, maybe the lakeside campus, we have n number of things. One of the earlier VCs of actually Kufos, Dr. Madhusudanan Purpa, he has almost done so many fishes actually in this, which are actually in the Webanad Lake. So the fishes in Kerala, the radar center itself, the various activities which the Cochin University does is actually worth publishing in a maximum card, this one, or maybe any other things also like. So there are n number of things which Department of Post can actually do. Maybe, and stamp collection is actually a very good, let us say, outreach activity. In fact, this cover which is made now will go to almost remote parts of the world, okay, which is actually worth this one, so that we are honoring the 3 eminent scientists from Kerala and who have actually contributed, as Professor Mohan Kumar correctly mentioned. Anandakrishnan has almost touched all the aspects, and his student, Professor P.B. Joseph, who unfortunately couldn't be here, was actually a student of Sir C.V. Raman, Professor Anandakrishnan, and we have another scientist called C.K. Rajan. Unfortunately, he also couldn't turn up. So there are a number of people who actually worked with Professor Anandakrishnan, and he is a very, very hard-working person. And I am also fortunate to have Professor P.R. Pishardi Memorial Award, which was earlier called the National Remote Sensing Award, which is given by the Indian Institute of Remote Sensing, Dehradun. So I am really happy to also have that. And Miss Annamani, as Professor Mohan Kumar has correctly mentioned, mind you, not now. In those days, girls' education was next to impossible. And she was coming from an elite family from Pyramid. She worked really hard, went to Trichy, this one, and unfortunately, she couldn't get actually a PhD because you needed an MSc at those days. But she overcame that and went to Imperial College London and did a wonderful job. In fact, what people have not thought now about the ozone and all these things, she has fostered actually in 1970s. Because Professor K.R. Ramanathan at that time told her that you should study and work on ozone. And she was also instrumental in a new thing called autonomous weather stations, which we hear quite often. Which was actually totally unknown at that point of time. And radiation is another field which she has actually done. Because even though we say we know a lot of about solar radiation in different parts of India, I think she was the first person to look at it. So I thank Professor Mohan Kumar and Abhilash for agreeing to my crazy idea. And Professor Mohan Kumar went one step ahead. I only thought of special covers. Professor Mohan Kumar said that we should have a memorial lecture. I said that will be icing on the cake. So because I only thought actually a small thing, he had far more further vision or whatever. So he instituted actually, and we got some 3 brilliant people. Professor J. Srinivasan will be giving a talk, Professor Anandakrishnan Memorial talk. Tomorrow, Dr. C.R. Sridhar, who is actually ex-Deputy Director of Meteorology from IMD, will be giving a talk on Annamani Memorial lecture. And on the last day, Professor B.N. Goswami, who is actually a brilliant scientist. Earlier he was from IAC, Bangalore, then he went to IITM as a director. Currently he is in Cotton University in Guwahati. He was also a very visionary who changed the whole idea of actually IITM, what is present today. In fact, he only recruited, I think, Abhilash to IITM, and from there he came here. So he recruited people from all over India and all over the world and brought the best minds actually to the IITM and changed. And he had a fantastic project called National Monsoon Mission, which got actually about 400 crores, thanks to the Ministry of Earth Sciences. So he changed the whole idea of actually the IITM. So he will be giving a talk on Professor Pishardi Memorial Lecture. So I once again thank Cochin University as well as Professor Mohan Kumar and Dr. Abhilash for agreeing to my crazy idea and making this happen. Thank you.
Thank you, sir. Now I I would like to request the dignitaries to release the 3 special covers.
മാഡത്തിന്റെ എടുത്തോളൂ. മാഡത്തിനോട് ഒരു മാഡം മാഡം ചീഫ് ഗസ്റ്റിനോട് മാസ്ക് ഒരുക്കോളൂ സാർ. ഫോട്ടോ കാണിട്ടല്ലോ. വർഷം കഴിയുമ്പോൾ now you can give out. Sir, വെച്ചല്ലോ സാർ. എല്ലാവർക്കും കൊടുത്തു. അനന്തകൃഷ്ണൻ തന്നെയല്ലേ? രണ്ട് സ്റ്റുഡൻസും ഉണ്ട്. അനന്തകൃഷ്ണ സാറിന്റെ മോഹൻകുമാർ സാറും ഞാൻ. അടുത്ത കവർ എടുത്തു. എനിക്കതിന് മുമ്പ് സാറേ നിങ്ങളുടെ സിഗ്നേച്ചർ വേണം. ഒരുമിച്ച് ചെയ്താൽ മൂന്നിനെ ഒരുമിച്ച് ചെയ്താൽ മതി. പുള്ളി എപ്പോഴും ഒരു സംസ്കൃത ശ്ലോകം ചൊല്ലിയിട്ടാണ് സ്റ്റാർട്ട് ചെയ്യുന്നത്. സംസ്കൃത ശ്ലോകം ചൊല്ലിയിട്ട് സ്റ്റാർട്ട് ചെയ്യും. Meteorology and oceanography.
In all seminars, after dinner, he gives a fantastic art, funny
jokes. മാഡം കർണാടകയിൽ 10 കവറൊക്കെ ഉണ്ട് ജിയോഗ്രഫിക്കൽ ഇൻഡിക്കേഷൻസ്. ഡിപ്പാർട്ട്മെന്റ് ഓഫ് കോഴ്സ് ഒട്ടും മോശമല്ല മാഡം. തിരൂർ വെറ്റില, മറയൂർ ശർക്കര, പിന്നെ ആറന്മുള കണ്ണാടി, ചെങ്ങാലിക്കോടൻ പഴം, നേന്ത്ര സയന്റിസ്റ്റ് ഒട്ടുമില്ല സാറേ. സാറേ ഇനി എല്ലാവരും ഓരോന്നോരോ സിഗ്നേച്ചർ ഇടണം. സാധാരണ തന്നെ സ്റ്റാർട്ട് ചെയ്യാം. ഇവിടെ ഒരു സിഗ്നേച്ചർ റെക്കോർഡാണ് നമ്മൾ. പ്രൂഫ് നാളെ ഡിപ്പാർട്ട്മെന്റ് ഓഫ് കോഴ്സ് ഡേറ്റ് ഇട്ടോളൂ. സാറിന്റെ പേരിട്ടോളൂ. ഡേറ്റ് സാറിന്റെ പേരിട്ടോളൂ.
Now I would like to invite Dr. S. Abhilash, Secretary LOC INTROMET-2021 for the vote of thanks.
This is a great occasion as far as INTROMET is concerned and the entire atmospheric science family, especially the KISAT family is concerned. And I am fortunate to have been honored to propose this vote of thanks during this important event. And I am fortunate that being the third generation scientist from the tradition, we are the third generation scientists after the great eminent scientists like Professor Anandakrishnan, Professor Pisharidi, and Professor Annamani. So it is my great privilege to propose this vote of thanks to all dignitaries who are present in this on the dais. I most humbly thank our Pro Vice Chancellor who is presiding today's function, and he is providing constant support, encouragement, and all other facilities required for the Department of Atmospheric Science and Radar Center. Thank you, sir, for coming us and supporting us. I would like to propose or express our deep sense of gratitude to Srimati Mariama Thomas IPOS, who had, though it is a service from Postal Department, she served, actually, Postal Department really served us in making this postal cover possible. In that sense, I would like to thank both Amala from Postal Department and our Vijoy is also present. And I am also fortunate to tell that these 3 cartoons have been prepared by my daughter. And so it's a 4th generation. And so I would like to propose on behalf of IMS Cochin Chapter, Cochin University, Radar Center, to the entire Postal Department, especially Mariama Thomas Madam, for making this happen. Now, I would like to express our sense of love, affection to our professors, my guru, Professor Mohan Kumar sir, who had been a motivation for all of us, like Anandakrishnan sir he was fortunate to having a great eminent scientist like Anandakrishnan sir as his guru. Like that tradition is continuing. We are fortunate to have the 3rd generation scientist and guided from Professor Mohan Kumar sir. And we are thankful to you, sir, for constantly providing your guidance and eminence and the vision for all of us. Thank you, sir. And I would like to express the real man behind this idea, our Ramesh Kumar sir. Actually, this entire idea was proposed by Ramesh Kumar sir. And in fact, I would like to tell that there was no fun for this. so in that, even if there was some issues with that, but we could manage to have this function. Here, and he is the main brain behind this function. And we would like to, on behalf of the local organizing committee, I would like to thank Ramesh Kumar sir for making this happen. Now, I would like to thank all those who have gathered here, both in offline and online mode also. Many have already joined for this function. On behalf of this IMS Cochin Chapter and INTROMET Organizing Committee, I express my sincere gratitude to all of the students, faculties, and all the participants who have joined both online and offline and viewing this function through YouTube channel. I express all thanks to all of them. Thank you very much.
Thank you, sir. Now please stand up for the national anthem.
Bharat Bhati Mata, पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मागे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
This concludes the session. There is a small announcement. Memorial lecture will start around 6:30 p.m. in Hall 1, Pampa Hall. All are requested to join the web portal or patch the program to YouTube channel from 6:25 p.m. All submitted posters will be displayed in the virtual room during all the remaining activities. All registered participants can enter the virtual conference platform and view the posters and lyrics to the
Sir was talking about a program for the students and faculty. ഒരു എൻ്റെ ഒരു ലേഡി വിളിച്ചിരുന്നു. ഇവിടുന്ന് ഇവര് പറഞ്ഞിട്ട് നമ്മുടെ നാട്ടിലുള്ള ഒരു ലേഡി ഒരു പോസ്റ്റൽ ഡിപ്പാർട്ട്മെന്റിൽ വർക്ക് ചെയ്യാം. അവര് വിളിച്ചതാ. എറണാകുളത്ത് പറഞ്ഞിട്ടാണ് പറഞ്ഞ് വിളിച്ചതാ. ഈ പറയുന്ന സർവീസസിനെ കുറിച്ച്
ഒന്നും വിടരുത്. Just go to the class. You can also join. Welcome to Ragesh.
Am I audible? Excuse me.
Discussed about the observation impact on or range. Range.
See, video also. This one.
Hello?
Yeah, that's okay.
My face
So
is
why is the blood?
What?
Blood, okay. Little blood.
No.
Hmm?
Your face is a little blurry.
Okay.
Your specs.
No, not spectacle. Even the face is blood. Compared to the background. That's all right. That's okay.
You unclick mirror the video.
Huh?
Unclick this because of the light glare.
That I can block while switch off the light. No, put on the light.
No, if this light works, you may not have that much glare.
No, that work.
You can actually try shifting the bulb if necessary.
No, not now. Okay, now close it or?
Yes, close.
Oh. Okay.
You can stop video.
Unmute here. It's muted, is it?
No, it's not on mute. Click on top of it.
Okay. But how come I'm not having any connection to anyone?
Hello? Can
you Okay,
my audio and video quality?
Open my. I'll open my.
Hello? Hello?
No, go to you. Go to you. Make it stop. Just no, let me just open my. I should open it. Here.
This one.
No. Already. Okay, now let's what happens. I have to upload it. That's a tricky point.
So try it.
No. Tell me. Let's see. Upload. What is next?
No.
Share screen.
But you haven't started the presentation. Start the presentation.
No, only after upload. I have upload it.
No, you don't have to.
Then I cannot. I'll keep it and I cannot see them. I'll keep doing this. Okay, let's leave it. No, it doesn't. Okay, go back.
On the screen and go back to this one.
Huh?
No, Zoom is here. No.
Okay. Then I can go to full screen now, right?
You are in full screen already.
Oh.
You can go to participants. Click here. Click on that. You want to chat and say you can start, or you're not on mute. You can ask if you have to start now.
No, nobody is talking. That's not fun. Somebody was talking, but
Your tea is here. Perfect. Yeah, Memorial. You're not on the screen.
Oh.
Video is off. You don't have to share Mama.
that's yours, right?
Yeah. Should I keep mine on the bed so you don't have confusion?
We have direct. That will be.
You're more likely to kick it off while you
No. This is my favorite version.
Should I mute your phone?
Yeah. Put in airplane mode.
Yeah.
I don't want to. Any.
I put it on airplane mode.
They would ring. Somebody else take this phone. If it rings.
I'll keep the phone off.
Yeah.
Your audio is going through. You're not on mute.
I thought they're doing the rehearsal. They're not doing the rehearsal.
Hello. Hello. Am I audible, sir?
Yes, ma'am. This is
Yeah.
the audible, ma'am.
Yeah, this is Srinivasan. You're audible.
Okay, sir. Hello, this is Rapita from Cochin University. Please check Joseph sir's audio and video, please.
You also you open.
Hello, Joseph sir.
Can you please switch on the
Hello, Joseph sir. Can you please unmute your audio and can you switch on your video? Hello, Joseph sir. Please unmute your audio.
Can you speak something?
Hello, sir. Can you speak something? Hello. Hello, Joseph sir. Can you say some words?
എന്റെ പേര് വിളിക്കുന്നുണ്ടല്ലോ.
Okay, you can talk, sir.
ഞാൻ പറയണോ?
Start with the
Sir, you're muted, sir. Yes. Yes.
You can unmute him also.
Kindly speak something, sir, so that we can check the quality of audio.
You're asking Joseph or me?
For Joseph,
Joseph,
sir.
sir.
Okay.
You're okay, sir. You're okay.
Thank you.
Thank you, sir. Joseph, sir. Yes. Hello, sir. സാറിനോട് സംസാരിക്കാൻ പറഞ്ഞാൽ മതി. ഓഡിയോ ക്ലിയർ അല്ലേ നോക്കാൻ വേണ്ടി.
Sir, just sound check ചെയ്യാനാണ്. അവർക്ക് sound check ചെയ്യാനാണ്. Hello, am I audible? Hello?
Yes, Joseph sir, can you hear?
Can you hear now?
കേൾക്കാമോ?
എനിക്ക് കേൾക്കാൻ പറ്റുന്നുണ്ട്. അവിടെ കേൾക്കാൻ പറ്റുന്നുണ്ടോ?
ഇവിടെ കേൾക്കാം. കുറച്ചുകൂടി ഞങ്ങൾ ലൗഡ് ആക്കാം. നിങ്ങളുടെ വോളിയം കുറച്ചുകൂടി ലൗഡ് ആക്കാം.
ഓക്കെ.
അവിടെ നിന്ന് സൗണ്ട് വോളിയം. ഹലോ.
ഇപ്പൊ കേൾക്കാമോ?
ഇപ്പൊ ക്ലിയർ ആയിട്ട് കേൾക്കാം. ക്ലിയർ ആയിട്ട് കേൾക്കാം. ജോസഫ് സാർ, സാറിനൊന്ന് പറഞ്ഞ് വിളിക്കാം.
ഓക്കെ. ടെസ്റ്റിംഗ് സൗണ്ട്. ചെക്കിംഗ് സൗണ്ട്.
ചെക്കിംഗ് സൗണ്ട്.
ചെക്ക് ചെയ്യാണ്.
സാർ, അതിന്റെ വീഡിയോ ആണോ?
എപ്പോഴും വീഡിയോ.
Sir, can you see me? Sir?
Yes, I am here.
Okay, sir.
Are you able to hear me?
Yeah, sure. Now, very clearly I can hear you. Tomorrow, today, hello, sir. Hello, sir.
Brother Joseph, can you see me?
Yeah, we can hear you and we can see. Yeah. Yesterday I had some problem with the audio. That is why I could not talk.
Yeah.
Okay, sir. Okay. Professor Joseph is here. I think you can also see him.
Yeah.
You will call my name when it is time.
Yeah, you are sharing the session. You are yourself and the Professor Sen. Professor Sen, sir. Professor Sen.
Yeah.
Okay. Yeah, I think you can, Professor Joseph start, then you will continue. I can continue. Sen sir can continue that. Okay. In the inaugural function, I think rapporteur will introduce the chairs and as well as the speaker. Then you can take over the chair. Another one minute. Okay, we will start the. Yeah, you can do that. Yeah, sir.
Welcome to the day one of INTROMET-2021 Professor R. Narendra Memorial Public Lecture. Professor J. Srinivasan is going to deliver a talk in this session. He is a distinguished scientist and the former director of Diveta Center for Climate Change and the honorary professor, Center for Atmospheric and Oceanic Sciences, Indian Institute of Science, Bangalore. Chairpersons to this lecture are Professor P.V. Joseph and Professor P.N. Sen. Professor P.V. Joseph, former director of India Meteorological Department and the emeritus professor at the Department of Atmospheric Science of the Cochin University. His important research contributions included the discovery of a low-level jet stream in Indian monsoon, role of North Indian Ocean on monsoon onset and active break phases, SST convection relationship, development of a model for dust storm, etc. Professor P.N. Sen is a former director of India Meteorological Department and emeritus professor, University of Pune. Now I request the chairs to kindly take over the session.
Sir Joseph, sir, please. Professor Joseph,
Yes,
Krishna Mohan, yeah, please tell Joseph sir to.
I am happy to be associated with this program. Professor Ananda Krishnan has been my teacher. He has been a forecaster for long, and he has been associated with IITM for a long time. And but as a teacher, he has spent most of his time. So he is my PhD guide. And it was so very nice to work with him as a PhD guide. While after getting my PhD, and I was working in Pune in the training division of the Indian Meteorological Department, and he had started the meteorology course in Cochin University in the early 1980s, and he was going every month to Cochin to take the classes. And after 4 or 5 years, he asked me, "Will you take over from me?" And at that time, my wife was working in Pune, I was working in Pune, and I could not take that job immediately. So after I retired, I joined Cochin University as a visiting professor and an emeritus professor, and did 17 years of teaching to honor him. And Dr. Ananda Krishnan is such a nice person, and I could teach MSc and MTech programs. I could guide the work of 10 PhDs in CUSAT. This is a tribute to Dr. Ananda Krishnan from his student. And I am greeting Dr. Sen, and thank you for making me chairman of this thing. Thank you.
Professor Sen, can you add something about Professor Ananda Krishnan experience? Yeah, please.
First of all, I feel honored that I have been given this opportunity to talk to you and share the screen with so many people. Professor Ananda Krishnan, as Professor Joseph has told, he was a distinguished scientist. Not only that, I will just, he was humble in his nature, always. I remember one time when I was delivering some lecture in some refresher course for the India Meteorological Department officers, and he was attending the course and taking notes. Then after the lecture, I asked him, "Sir, why are you doing all these things? You know all these things." No, I can always learn something from everybody. That was his characteristics, because I was a very junior fellow and he was such a eminent scientist, but that was the quality, his humility and all these things. And till the last day, he was busy in doing research. His contribution in the Indian meteorology, particularly in monsoon, is tremendous. So it's a great thing that we have arranged a lecture in his memory. So Professor Joseph, and myself, we feel proud that we are here today. Thank you all.
Okay, I think now, with your permission, I think you can invite Professor Srinivasan to deliver the talk. Now we are leaving to the chairman, two chairpersons. Now we can proceed your program. So J. Srinivasan will talk about the deliver the public lecture. Hello, can you hear? Hello. Hello, can you hear, sir? Professor Sen, can you hear?
I'm able to hear.
Okay. Sir, please, Professor Srinivasan, can you hear?
Yes.
Sir, you can start then. I think Professor Joseph has some problem. I think he can.
Okay. Is my screen shared?
Yeah, I think you now. Yeah, it is shared. You can make it a presentation mode.
Is it visible now?
Yeah, it's full. Now it's okay. Fine.
Okay. Is the slide moving?
Yeah, it is audible.
Okay. Let me first thank the organizers for inviting me to give the Professor Ananthakrishnan Memorial Lecture. Professor Ananthakrishnan is a pioneer in Indian meteorology, and it's a great honor to give a lecture in his name. I'm going to talk about the simulation of the monsoon during the past 20,000 years using climate models. This is possible today only because of the amazing increase in the power of computing that we have today, that we are able to run a model continuously for 20,000 years to understand what happened in the past. And we want to understand the past monsoon in order to predict the monsoon in the next few years to next 100 years. Now, why should we worry about past monsoons? Monsoon is a complex nonlinear system. Hence, although we have done a lot of people have done work, Professor Ananthakrishnan and many others, Professor Joseph, looking at 150 years of rain gauge data. But 150 years is not enough to tell the full complexity of the monsoon system and the various modes in which the monsoon varies. Today, we are lucky that we have access to powerful computers, and also we have proxy rainfall data from speleotherms and oceans from the last ice age to the present. So we get a qualitative idea of how rainfall could have varied in the past, and then we can run models during this period and use this model to understand monsoon better. Now, monsoon responses to climate occurs in various time scales. The past is what I'm going to talk about. Of course, there's the present and the future. They're all connected. And so I'm going to use the energetic frameworks to interpret the monsoon changes. Now, one of the interesting things about the past monsoon interest came in the African monsoon, because during the period from 1970 to 2000, there was a long drought in the Sahel region of Africa. And this led to a lot of discussion about whether this was a man-made drought or is it due to natural causes. You see below that in India, we have not seen such long periods of drought. Our droughts occur for a few years and then we get back normal rainfall. But Africa went through a very bad period for 30 years. And the question has always been whether this is natural or man-made. Now, in a paper published about 10 years ago, Shanahan and others said that we find that intervals of severe drought lasting for periods ranging from decades to centuries are characteristics of the African monsoon, and therefore the droughts of the recent decade are not anomalous in the context of the last 3,000 years. So what we are saying is that if you look at the long period of the African monsoon, there have been many long periods of droughts. So this should be a warning to all of us that we have to look at the long period monsoon and see whether there are possibilities that Indian monsoon may also go through a long period of low rainfall. Now, the proxy data for the past rainfall comes from many sources. The most common is on land is the speleotherm, which is derived from stalagmites in caves. A lot of work has been done in India, led by Dr. late Ramesh from PRL. And by looking at the oxygen isotope in these speleotherms, we can infer the amount of rainfall. Okay? So this work, Dr. Ramesh and his students have done very well. But these records last only maybe 5,000 years or 7,000 years. In India, we're not had a very long record. So if you want a longer record from last glacial maximum, we need to go to ocean proxies, and that's what I'm going to use for my discussion. Now, the land record paleotherm shows a linear relationship between rainfall and the oxen 18 isotope variability. Okay, so from the variation in oxen 18 isotope, we can infer the past rainfall. And the same thing can be done with ocean proxies, foraminiferas, from whose oxen 18 isotope also you can infer similar rainfall. Now, what people have generally said in the past is that if you look at the data over the last 250,000 years from the Chinese cave, Donghehulu cave, they showed that the variation in delta O18, and that is variation in monsoon rainfall, in those caves coincides exactly with the variation in incoming radiation from solar at that latitude, 30 north. So it was generally believed till recently that variation in solar radiation incident in that latitude is sufficient to explain the variation in the monsoon in the past. Okay, although this is quite impressive result, but this is not the whole story. Now, for example, Kushbach, a pioneer in monsoon research from United States, has shown that variation in incoming radiation and variation in rainfall are linearly correlated. Okay, this is over a long time scale, average over 10,000 years. But I'm going to talk about a period from last ice age to the present, and this had two episodes. One for the last ice age, but the temperature was 3 to 4 degrees below today, to the Holocene 10,000 years ago, when we reached the present temperature. And then the temperature remained reasonably constant for almost 10,000 years. And then in the last 100 years, it has increased rapidly. So the idea is, can we understand how monsoon varies from 20,000 years ago to the Holocene, and then from Holocene to the present, in order to understand what will happen in the future. Now, during this period, there were short periods of rapid climate variation called the Bowling Aneroid in Younger Dryas. So there were fluctuations, and monsoon also responded to changes during this period. Now, we looked at an ocean proxy near Andaman, and this proxy showed that the oxen 18 in seawater, its variation with incoming radiation at that latitude had two different slopes, one in the Holocene, the last 2,000 years, and one during the glacial from 15,000 to 10,000, 18,000 to 15,000. So you can see that the slope is different. That means the response of the monsoon to solar radiation was not the same during the deglacial when compared to Holocene. So this was the issue, puzzle we wanted to solve. So for that, we used a simulation done by the National Center for Atmospheric Research in Boulder, Colorado. They used a fully coupled atmosphere, ocean, sea ice, and land surface simulation with CCSM3 at a fairly low resolution because the model is run for 22,000 years. And in that model, they allowed for variation in Earth orbit around the sun, greenhouse gases, ice sheets, and meltwater fluxes from melting ice in the Arctic. They also had separate simulation in which they varied each of these things separately. So this enables us to understand the role played by variation in Earth orbit, greenhouse gases, ice sheets, and meltwater separation. Now, here I've shown in black the simulation by the TRACE 21,000 simulation from the NCAR model. And in red is the proxy data from a location core called KL126 in the Bay of Bengal at 20 north and 90 east. Now, note that although the agreement is not perfect, there is a fairly good agreement about the variation increase in rainfall from around 3 millimeters per day at the last glacial maximum to around 7 millimeters per day around 12,000 years ago, and a gradual decline to 6 millimeter per day in this model. Okay, this model simulation is not perfect. It is slightly drier than the present observed rainfall. Okay, but still it captures very well the rapid increase in the deglacial and the gradual decrease in the Holocene. Now the question is, what caused this? To understand this model simulation, you need a diagnostic model. The model is too complicated. You cannot get into all the details of the model. So we need a diagnostic model which reproduces this variation that the model simulates and use that model to understand the monsoon. Now, I talked about the ocean proxy that actually measures salinity. The salinity is measured through barium calcium ratio and other examples. So this proxy for foraminifera was used to detect the amount of discharge from both Brahmaputra and Ganges. Now, if you compare what I showed with the proxy with the model simulation, here I compare in the y-axis of model simulation rainfall and the incoming radiation, which is prescribed in the model. You see that the model shows the exact difference between the Holocene and the deglacial. Very similar, not identical, very similar. That shows that this model is good to understand why the slope of this curve is different in the Holocene compared to deglacial. So again, showing both together, the proxy on the left and the model on the right. And you can see that they are very similar, not identical. Both show a large difference in slope. And our aim is to understand why the slope is different. Now, I've put the model simulated rainfall in blue and the solar radiation variation in red with reference to the present day. And you can see that during the last 22,000 years, the solar radiation varied only by 7%. It reached a maximum around 10,000 years ago. But the rainfall has almost doubled from LGM to Holocene and then gradually decreased toward the present day. So the question is, although the radiation only increased 1%, why did the rainfall increase by 100%? So it is amplification of 13 times. So that demands some explanation. For that, we use what is called the energetics perspective. This has become quite common now in the last 10 years. And this depends upon looking at the energy budget and the moisture budget of the monsoon region. And so this is different from the traditional land-sea contrast theory, which has many flaws, which has been pointed out recently. Now, the energy theory essentially says that monsoon requires energy to drive it and to let the air passes rise all the way to tropopause and simulate the Hadley circulation. So this energy comes from the sun, and some of the radiation, of course, is radiated back to space. So the net radiation at the top of the atmosphere is a critical parameter, and also the flux at the surface. But over land, this bottom flux is close to zero because land has very little heat capacity. So over land, what is important only is the net radiation at the top of the atmosphere. And during the last 40 years, we have excellent data on this quantity from satellites. So that enables us to really quantify this quantity, the net radiation at the top of the atmosphere. Now, about 30 years ago, Neil and Held from Princeton proposed a very simple model for the monsoon based on the concept of ITCZ, intertropical convergence zone. They said this zone air converges at the bottom and diverges above, and this whole phenomena can occur only because radiation comes from the top and enables this heat engine to continue to run for the entire season. So to quantify that, they had the mass static energy budget, vertical integral from surface to the top of the atmosphere, consisting of horizontal advection, both zonal and meridional, vertical advection, and the total energy divergence on the right-hand side, and the moisture budget involving horizontal advection of moisture, vertical transport of moisture, evaporation and precipitation. And so these two equations are the cornerstone of this model. Now, what is amazing about this model is they just divided one with the other and got a very simple expression for diagnostic purposes. So this is what I call a diagnostic model. In this model, all I've done is divided one equation by the other. And so I get the result, rainfall and evaporation is equal to divergence of the energy in the column divided by what is called the total gross moist stability, which is given below here as a ratio of the vertical moist static energy integral and the vertical moisture humidity integral. Okay, so this is a quantity which encapsulates all the important things happening in the vertical in the atmosphere. Now, this equation can be further written in a more convenient way as rainfall equals evaporation time, incoming radiation S at the top of the atmosphere, 1 minus albedo, the reflectivity, which is influenced by clouds and ice, minus outgoing longer radiation, which is influenced by clouds, carbon dioxide, water vapor. Okay? And the denominator is that quantity TGMS. Now, note that if we somehow assume that evaporation, albedo, over latitude do not vary, then S and P are proportional. So this is the idea that Kurzbach suggested, that P is proportional to S if all the other quantities are not varying much. Now, this is true if you look at an average over 10,000 years. But if you look at an average of 100 years, then these quantities do vary. And so rainfall is not only dependent on S, it also depends on other factors. Now, what are the other factors? That's what important issue. Now, before I do that, I want to show how powerful this model is. This model says that the numerator in this equation is the net radius top of the atmosphere. This I have plotted here over Africa and India in July, averaged over 30 years. You see that over India, the net radiation is about 60 to 80 watts per meter squared, but in Africa and Saudi Arabia, it is close to zero or negative. Now, so in the same latitude band around 25 north, India gets much more input radiation than either the Sahara or Saudi Arabia. And that explains why India has a monsoon at this latitude, but Sahara does not. So what they say is that if the radiation top of the atmosphere is small or negative, the numerator is negative, then P cannot be greater than E, because TGMS is normally positive. So this is a very powerful result, which was actually proposed by Jules Charny a long time back, but at that time, he did not have the satellite data to support this idea of how Sahara Desert formed. But today, we can clearly see Sahara Desert is a net radiative sink, and that means rainfall cannot exceed evaporation. Now, to highlight that more, I plotted the rainfall in Africa along with net radiation. You can see that net radiation is there only in the region where rainfall is positive, only in where radiation is at least 30 to 40 watts per meter square. When it goes to zero or negative, there is no rainfall. So this is a very powerful result of the Neal-Held hypothesis. Now I come back to the simulation. Behind the simulation, we calculated TGMS. First, we plotted it with column water vapor, and we plotted it 1 over column water vapor. When you look at yearly data, it is quite noisy. There's lots of variation due to the role of dynamics changes, surface changes. But if you average over 10 years, 50 years, and 100 years, things become simpler. So I'll focus on 100 years. In the 100-year time scale, the relation between TGMS and 1 over water vapor is almost linear. So this will enable us to explain the simulation of the trace in terms of simple parameters. So here we have put a linear fit to the TGMS with 1 over water vapor. It's not a perfect fit near the high water vapor, high water vapor is slightly nonlinear, but it is quite useful because this equation fit I given. I'm going to compare now with the model output. Model output is black. The simple model is red. And notice that although there are problems around the period 12 to 16,000, otherwise the agreement between the diagnostic model and the GCM is amazingly good. So we are going to use this diagnostic model to understand what controls the monsoon over a long period. And you can see that there are only two parameters now. One is net radiated top of the atmosphere, and another is water vapor. And you can see the very simple expression which tells you the 100-year average rainfall, not yearly, 100-year average. And it tells you why that increased from 1 millimeter to 3 this is P minus E, not rainfall. Moisture converges from 1 to 3 millimeter 3 times, and then it declined to about 2.2. Okay. Now, to explain this, we need to understand that during the period from last glacial maximum to Holocene, solar radiation increased and ice melted. So ice became water, so it absorbed more solar radiation. Temperature went up. And as the temperature went up, carbon dioxide, methane, whatever, all increased because they all depend on temperature. So greenhouse effect increased dramatically. So both these led to an increase in water vapor, and water vapor plays a crucial role in controlling the vertical stability of the phosphoric column. Okay. So in the deglacial to Holocene period, both melting of ice and increase in CO2, methane, water both played a role in increasing water vapor by a large amount. So water vapor plays a very important role in monsoon. One, because it is a powerful greenhouse gas, more powerful than carbon dioxide. And when it condenses, it releases a lot of latent heat. And finally, water vapor is lighter than air. So it affects the buoyancy of the air parcel. So the TGMS, which is indirect measure of the vertical stability, is affected by the presence of water vapor. Now let's go back and look at the radiation coming in at the top of the atmosphere at 30 knots between deglacial and Holocene. You can see that radiation gradually increased to a large amount and then declined. So in the deglacial, because of ice melting and increase in CO2 and so on, the water vapor went up dramatically. But in the Holocene, as the radiation went down, the water vapor did not decrease, but because there were no further ice formation, and CO2 did not increase much in this period, last 1,000 years, till the last 100 years. So in this period, the water vapor did not change much. So the behavior of water vapor between deglacial and Holocene was very different from the symmetric behavior of the radiation. Radiation is symmetric, but the response of monsoon is asymmetric. Now this is shown again in the next graph, where P minus E is shown for the full model in red, and in the model where only water vapor is varying in blue, where only the net radiation varying in black. So what I wanted to notice is that the variation net radiation agrees with the total P minus E during the last 8,000 years. But in the period from 22,000 to 10,000, the variation in the P minus E is following more the blue line, okay, which is the water vapor variation. So this model clearly shows if you want to explain the variation in the deglacial, you have to include water vapor. If you want to include the variation in the Holocene, you must include the net radiation. If you want a complete agreement, you include both. You include both, you get the red line, okay? Now, what happened in this period, in addition to the change in solar radiation, the ice area gradually declined from deglacial to Holocene, and then after that didn't change much. And carbon dioxide increased rapidly and then remained almost constant except for the last 100 years. Now, the people who did trace simulation were very nice. They not only did the full simulation, they also did simulation having only orbital changes, only greenhouse gases like CO2, only melt water forcing at the polar region, and only ice changes. So this individual simulation helps us understand the role played by each one of these parameters on the monsoon. So first example is only change in CO2. So here we keep the ice at the LGM level. We keep the orbit fixed. So we see that if only CO2 increase, then the luminosity increases rapidly during the deglacial, along with water vapor, and then it remains constant. Notice that net radiation, CO2 doesn't change because orbit isn't fixed. So sun's input is constant, and the increase in luminosity is completely controlled by increase in water vapor. So this shows beautifully the role of water vapor, which was triggered by an increase in CO2. Then the next one was where the ice was varied, but not carbon dioxide and orbit. And again, because orbit does not change, the radiation input was constant. But the ice melting caused the temperature to increase, and hence water vapor went up. And again, the rainfall increased by not as much as the CO2 case, greenhouse gas case. Now, if you do only the orbit case, keep CO2 constant and ice constant, then you see that the radiation goes up and comes down, CO2, and the water vapor follows exactly the radiation. And ultimately, the rainfall luminosity also follows that. So this clearly shows the role played by each of these actors in the total change that occurred in the last 22,000 years. And all of them are reproduced by this simple model, which is remarkable. Okay, this model is able to explain each one of the individual forcing as well as the total. And what happened in these individual forcing? In the case of the total, where everything was changed, the temperature of the Indian region, Arabian Sea really, went up from 297 all the way to 300. While if we only change greenhouse gases, it was slightly smaller because solar radiation didn't change. If you only change ice, the change was even smaller. And if you change orbit, it came back to the ice age stage. So this clearly shows that the temperature increase induced by greenhouse gases and ice a little bit was most important for the full simulation. Now, I'm told here the PMNSE convergence by the incoming radiation divergence as a function of water vapor. And I want you to see that all the simulations fall on one line. This is remarkable, saying that whether you look at the full simulation or only orbit, greenhouse gas, ice, or meltwater forcing, all of them fall on a single line. This clearly shows the value of the diagnostic model. But if you look at water vapor with surface temperature, the greenhouse gas and orbit show a different path. And this is because during the greenhouse gas increase, the forcing was equal in both hemispheres. But when orbit changed, there was much more heating of the northern hemisphere than southern hemisphere, and that caused the IDCC to move more northward, and that increased water vapor more in the Indian region than southern hemisphere, and that caused much higher increase in water vapor for the same temperature in the Arabian Sea. Okay. So once more, I want to highlight the relative role of variation in divergence of energy coming from sun and the variation due to water vapor. So divergence alone cannot explain this remarkable increase in rainfall and convergence. So you need water vapor, and water vapor plays a role in a complicated way that is encapsulated in the TGM. Okay. Now let's look at the Holocene. In the Holocene, the last 10,000 years, the radiation went down from 482 to around 452 today, and the rainfall has declined almost in a similar fashion. Okay? Not perfectly, but almost. So the decline in Indian rainfall from 10,000 ago to present can be explained by a decrease in solar radiation. Okay, so there are three phases in this period: the melting of the ice, which and the increase in CO2, which caused a rapid increase in water vapor. Then some fluctuation occurred around 12,000 years ago called the boiling Elrod, which I will briefly mention a little later. And finally, the very smooth decline in the Holocene where water vapor did not change. Now, this again highlighting the same issue about role of water vapor and QD. This has already been explained. Now, let's get the full understanding of this model. The incoming radiation, insolation, controls surface temperature as well as the amount of energy available to the monsoon. But this also affects the greenhouse gases and ice sheets. When they melt, they also increase surface temperature, and both put together increase the water vapor. So during the declacials, this part plays an important role. During the Holocene, this change is not much, so this part plays a role. So that is the full theory of monsoon variation in the last 22,000 years. Now, I want to also talk about a very interesting difference between Indian monsoon and the Bay of Bengal monsoon. In the past, we always thought of monsoon as a land phenomena, but today, monsoon is thought of as occurring in regions where there's a seasonal cycle in rainfall. So if you look at that, Bay of Bengal also is a monsoon region with a strong seasonal cycle. And we want to know, based on the diagnostic model, how does the Indian monsoon and the Bay of Bengal monsoon respond to these changes. Now, this gave us a great surprise. If we look at the rainfall in the Indian region, which is what we saw so far, the red line, it follows the solar radiation in the Holocene. But the Bay of Bengal monsoon, which follows the Indian monsoon during the deglacial, completely changes its character and rapidly comes down during the boiling alert period and then rapidly increases in the Holocene, okay? Increases. All the radiation is decreasing, the rainfall is increasing. This is completely counterintuitive, that India and Bay of Bengal are in phase during the deglacial, but totally out of phase in the last 8,000 years. This was a puzzle which we wanted to understand. So we looked at the divergence of the flux, which over India follows essentially the solar radiation change, while in the Bay of Bengal, it goes in the opposite direction. Now, Bay of Bengal is different from India because it's an ocean. Ocean gets energy both from the top and the bottom. At the bottom, latent heat flux provides energy to the column. In India, although latent heat evaporation occurs at the bottom, but that comes from the radiation that is coming from the top, because the land does not have an additional heat source to cause evaporation. It causes evaporation only due to the radiation of the sun. But Bay of Bengal, with a fairly thick mixed layer, stores the heat that was coming in the pre-monsoon period, and that heat is released during the monsoon because of high surface wind. So Bay of Bengal, the Q day goes up rapidly between 10,000 to the present, and that increase is what caused the rainfall to go up. And in both cases, the TTMS, the vertical stability parameter, decline due to increase in water vapor, remain constant. So that is not an important issue. And water vapor were in a similar way, although it was a little higher over ocean, which is not surprising. Now, again, I want to replot this to highlight the difference. So in the Holocene, rainfall declined in India and increased in Bay of Bengal. Okay. Now, why is that? Now, that's not only it is because of the difference in QDIV, there's also some difference in the vertical structure in the Bay of Bengal in India. We found that the vertical integral of the moist static energy, which is considered an important parameter by Neil Head, happened to be close to zero over India, which was a great surprise. We didn't expect it. But over Bay of Bengal, it was dominant. So the hypothesis Neil Head proposed more than 30 years ago is perfectly valid for Bay of Bengal monsoon, but not for the Indian monsoon. Indian monsoon, you have to take into account horizontal advection, A here, which is more than the vertical advection. But in the Bay of Bengal, it's opposite. So this is the main difference which we discovered in this model. This is also true of reanalysis data. Why is this happening? This is happening because the vertical structure of the vertical velocity is very different in Bay of Bengal as compared to India. In India, the vertical velocity maximizes at around 7 millibars, a little higher. In Bay of Bengal, it maximizes at a much higher level. This came as a great surprise to me. I didn't expect this. I thought India would also show a higher maxima at a higher level, but it does not. The analysis does not show that. Okay, but as far as the mass static energy is concerned, they behave similarly. So the main difference in the vertical variation of the vertical velocity. So because of that, the convergence m d omega dp is much higher in the Bay of Bengal here than below, and the net is positive. But over India, the two are almost comparable. Okay. So in India, the two are comparable. In Bay of Bengal, they are not comparable. So because of the level of zero divergence is much higher. And in addition, of course, the flux of the Q diff is different in India and Bay of Bengal. Because at the surface, there is no flux coming in at India because land has got very rich capacity. Or ocean, there's a large value. This one is negative because of the Sand convention for fluxes. Okay, so Bay of Bengal behaves differently mainly because of two reasons. One, the vertical structure of vertical velocity and the Q diff. Now, when you try to fit the TGMS of Bay of Bengal with water vapor, it did not follow a simple linear line. Okay, it showed a lot of complex behavior, and because of that, if you try to fit linear lines, we don't get good agreement in this region between 8,000 and 12,000 years ago. So we had to slightly modify the model or model for Bay of Bengal, the diagnostic model, and we found that for Bay of Bengal, we had to worry about the vertical mass static energy differences, which we have not done for India. When you account for that, then we get a perfectly linear fit with vertical mass static energy difference between upper troposphere and lower troposphere, and with water vapor in the denominator. And then we get a perfect fit between the diagnostic model and the GCM. So we have been able to improve the model for Bay of Bengal, and this also improves the model when you look at time scales below 100 years. Okay. So for India, it was not required. India also, you can see that around 8 to 12,000, there is a discrepancy that can be improved by including the vertical mass static energy difference. Okay, now I want to end with a few remarks about the African monsoon, which we didn't study in great detail, but it's worth thinking about. Now, in the African monsoon, the P-E ratio over land is much stronger than that over India. Okay, and that partly related to the way the PGMS varies in the African region compared to India, and that is related to the vertical structure of both mass static energy and vertical velocity. Q diff variation is somewhat similar. Okay, here I'm showing both land and ocean. Now, all of us know from whatever papers we have seen in the last 10 years that IT season in Africa at present is at around 15 knots compared to India, which goes further north. But about 10,000 years ago, during the African humid period, it was much more northward, around 25 knots. And this led to what is known as the Green Sahara. And a lot of interesting paleo proxy data has come, which says Sahara was very, very green and a lot of rainfall occurred there. And so the land in Sahara was not a desert 7,000 years ago, but actually a savanna. And that has been from the proxies which measure the discharge in the Atlantic Sea, and the discharge of dust. Atlantic Sea was much lower in this period than the present day. So we know that Sahara was not a desert 7,000 years ago. And this has been recently analyzed by a group led by Pasata and his colleagues, and they showed how the IT season, which doesn't move beyond about 20 north in the present climate, moved much more north during the African humid period, but you cannot reproduce that in traditional models. Okay, you can only reproduce when you make Sahara green, that is change the albedo, and also reduce the dust in Sahara. Both, if you do in the model, then you're able to show the shift in the ITCZ by about 15 degrees. Otherwise, it shifts by only 5 degrees or 3 degrees. Now, the other simulation which I found very interesting was one that done by Zheng et al. In the Neelam group. They showed that if you want to reproduce the last 60 years of Sahel rainfall, there is observations right here. If you have only a quadratic Gaussian model, you don't get it. You have to include land, soil moisture also, and also include vegetation. Once you include vegetation, look at the lowest and the highest, they are almost identical. The middle two are not that good. So it shows that for Africa, you need to include the role of land and vegetation much more to get the variation in rainfall. In India, it is not that much because in India, the desert part is very small. It is Rajasthan alone. So when you do all India monsoon rainfall, that region does not contribute as much. And so I've not seen any paper showing that vegetation changes play an important role in the Indian monsoon. But I may not have read all papers. So anybody knows something, I'm willing to be corrected. Okay, I want to end this point. I have only looked at how the monsoon changed from ice age to the present climate, okay, through changes in water vapor and radiation. Now, the question now today we are facing in the 20th century is due to human-induced increase in carbon dioxide. There's a very good chance our temperature may go up by 1.2 or more centigrade, and we may reach a new climate state very different from the ice age or the present climate. So based on the model we have got, we can see that as the temperature goes up beyond 2 degrees from present, the water vapor will increase a lot more than before, and that will increase rainfall a lot, and that will increase also the extreme rainfall. So that's what we have learned from whatever we have studied in the past, okay? And that comes out nicely in the model, one of the models I looked at in the MF simulation. The blue is the present climate, variation of rainfall over India with water vapor, and the red is the future at 2100, okay, where water vapor goes up. You can see the entire relation between rainfall and water vapor shift by about 20 kg per square meter. So because there is more water vapor in the future, there will be more rainfall, but because the vertical stability also changes, you require more water vapor in the future to get the same rainfall as now. For example, at 50, suppose you get 7 millimeters rainfall. The same value you will get at 60 in the future. So that's why some parts of India may actually have a decrease in rainfall because the water vapor may not go up as high in Rajasthan as it will in South India. So that is the point worth thinking about for the future climate. Okay. Now, this relationship between water vapor and rainfall, which is I looked at over a long time scale of 100 years and 1,000 years, it's also reproduced an hourly rainfall. This is the work from Neelam based on data from the West Pacific. Very nice data. He shows the average precipitation in the y-axis and column water vapor 3 hours earlier. That's all, just 3 hours earlier, and it varies exponentially. Okay, and all the heavy rainfall we saw in Kerala and in South India in the last 2 years is related to this behavior. That as the temperature goes up, whatever goes up, the rainfall goes up exponentially. And that's where we are going to get more and more extreme events as the globe becomes warmer. And I want to reintroduce this graph. In the past, the changes in the last ideas were triggered by solar radiation. Today it's triggered by human beings. Human beings increase CO2, that cause temperature to go up, and that increases water vapor, that increases greenhouse effect and stability. Ice melted in the last 100 years, and all these contributed to positive feedback. Similar to from LGM to Holocene, same thing happening from today to the future. Now let me summarize. So what was said earlier by Pushpa was that in the past, rainfall is proportional only to solar radiation. We have shown that in the 100 to 1,000 year time scale, rainfall differs on both solar radiation and water vapor. And we go to even smaller time scale, decadal scale, depends on solar radiation, water vapor, and the vertical moist static energy difference. And if you go to intermediate scale, when you introduce more circulation parameters, which we have not done at present. Okay, let me conclude. We have shown the new diagnostic model reveals how Indian monsoon varies on a centennial scale. The mechanism that causes increase in rainfall from LGM to Holocene is different from Holocene to present day. The monsoon in the Bay of Bengal is influenced more by surface heat flux than the incident solar radiation. The vertical structure or vertical velocity is different in Bay of Bengal compared to India. And based on this work, you can argue that monsoon rainfall will increase in the 20th century rapidly on account of increase in water vapor, and this will lead to more extreme events. Thank you. And I want to thank my student, Dr. Chetan Kumar Jalial, whose thesis was based on this, this work. And we have published 3 papers. And if you want to know more details, you can look at these papers. Thank you.
Sir, we are handing over to Professor P.N. Sir. Sir, please.
I'd like to ask a question because Professor Srinivasan, you have compared the Bay of Bengal monsoon with the Indian monsoon. Did you have similar study for the Arabian Sea monsoon and Indian monsoon?
No, we have not gone into detail. We have looked a little bit, not much. Arabian Sea monsoon is not that interesting because Arabian Sea cools during the monsoon. So the rainfall changes are not that much. But I will send you whatever figures we have in the thesis, but we're not gone into great depth. Bay of Bengal surprised us. We didn't expect that a large increase. So we spend more time on the Bay of Bengal. But you're right. I should look at the Arabian Sea and figure out what happens in Arabian Sea. You're right. I'll send you the results very soon.
The Western coast mostly get the Arabian Sea branch of monsoon. So
yes, but the oriented range is mainly different from what I was saying. See, the rain over Kerala and Karnataka coastline is orographic range. And I don't think the model we have used here, which is very coarse resolution, only 3.7, 3.75, I don't think it reproduces orographic range well. So we can only talk about all India. We cannot talk about coastal features. We can't talk about that.
Okay, thank you so much.
Professor Joseph, Professor Joseph, want to add anything? Yeah. Professor Joseph.
I think there is some problem with this.
Yeah, I think it's something. Okay, you can ask. You can.
Yes, sir. I am Manoj. I have a question. Regarding the position of the ITZ or the African region, you had shown it was much more north in the past time scale. So, what about the location of the major deserts? Was it also affected, or is it not evolution?
Let me explain to you. 7,000 years ago, there was almost no desert in Sahara. Sahara was green. So the ITZ moved so far north that the desert almost disappeared. Okay, so the key point is that the desert is there in Africa only because there is advection of cold, dry air from Europe, because there is no Himalaya. In India, we are lucky. We have the Himalayas all the way from 70 east to 100 east. And we have shown with the work of Professor Arindam that if you remove the Himalayas between 80 east and 70 east, Indian monsoon declines dramatically. We were told 40 years ago that Tibet plays an important role. We showed it is not true. It is the Himalayas to the west of Tibet. That's because that is the part of Himalaya which prevents cold air advection, which is happening in Africa. So Africa is strongly influenced by cold air advection. As a matter of fact, that Sahel decline in the 70s, many people show is due to aerosols being advected from Europe to Africa. That is one hypothesis.
Yeah, there is another question by Professor Aditya Agi. He asking about how about changes in Indus Valley climate?
We are not looked that detail. I'll tell you why. This model has a resolution of 3.75, 3.75. Because if you want to run a model for 22,000 years, you cannot run a high resolution. If you want to understand the Indus Valley, I think we require a 1 degree model. and I hope somebody will do it in the next 10 years. But this model cannot be used to understand small scales because there is no orography. Himalayas are not well reproduced, so I would not stretch it that far.
And what about the Hartley circulation at that time? It would have very long distance covers up to the 45-degree latitude?
No, I don't think it changed. It changed by maybe 5 degrees, not 45 degrees. No, did not. Because over the Indian region, Himalaya is one barrier. Over Africa, I have to check. For Africa, I have to say how far it went during the, I think it went to 30 knots. It didn't go to 45. But I'll check. But the data is there. I will let you know what the Hadley over Africa is.
Yeah. Okay.
And also India. I will. Those plots are there in the thesis.
And Professor Joseph, I think again. Okay. Professor Piensen, I think whether. Yeah, you can continue, or Professor Tyagi is here.
Yeah. Just, is it possible to run a sub-regional high-resolution model for, say, past 10,000 to simulate Indian climate in a better way?
Dr. Tyagi is a good question. I wish somebody would do it because today both IITM and IMD have powerful computers. I request them to take it up as a national task. I think we should, here we depended on NCAR, but it is high time we don't depend on outsiders. We should do our own simulation. And I request IITM and IMD to think about it. It can be done fairly easily. It requires some resource, but it is worthwhile for us to do a regional model simulation, at least for 10,000 years, to understand what happened in Rajasthan, where Rajasthan had high rainfall 4,000 years ago, and during the Indus Valley simulation. And it will benefit all of us to understand how well we simulate the past monsoon.
Thank you, Professor Srinivasan. May I request Professor Mohan Kumar to include this as one of the recommendations of the symposium?
Sure, sir. We are taking down all the details.
Yeah,
thank you.
I'll be very happy if because we can do it in IISc because we share our computer with 50 other departments. But both IITM, IMD, etc. are the people who are to devote some time for basic research on monsoon.
Thank you.
Okay.
So I have one question.
Yeah. You type your name.
Okay. My name is Midun. I'm an assistant professor at Department of Atmospheric Science, CUSAT. So my question is, the process you explained here, whether it can happen on a centennial timescale? Because
I'm explaining only centennial. So let me explain. On a centennial timescale, thermodynamics becomes the dominant factor. Water vapor. Now you go to a decadal or internal timescale, the dynamics become more important. So we are now looking at the yearly data. It's very noisy. So we have to do a lot more work to bring in the role of dynamics. We have seen some impact of horizontal advection of Mars static energy from Arabian Sea to Bay Bengal, but it is not as simple as this. We did centennial scan only because we were able to come up with an analytical solution. I like simple analytical solution. That is not possible for interannual or decadal scale, but we are working on it. We hope to get some results in the next few years.
So one more question. In the case of global warming, maybe consider RCP 8.5 scenario when we have a warm climate.
Yeah.
So after that, is there a chance of reduction in precipitation after that due to this feedback?
No, all the feedback I see are only increase in rainfall. But only one problem we have when you look at the whole globe. If by chance, for example, the rainfall in East Asia increases more than over India, because East Asia has more vegetation than India, has much more. India is mostly agriculture. If East Asian monsoon increases more than Indian monsoon, then there may be descent over India and Indian rainfall may go down. So there is a connection between African monsoon, Indian monsoon, and Asian monsoon due to changes in Walker cell. So I don't know whether our models are reproducing that correctly. See, remember that when you look at the CMIP 6 models, they all don't agree on the amount of rainfall increase. which means there are more things to be looked at regionally. Okay, this is all right for a settlement scale. One cannot get carried away. When you want to look at interannual and decadal scale, what is happening in East Asia and Africa can also influence India. So that part is still not clear. That requires further analysis.
Okay, thank you.
Professor Sen, I think okay. And it is an excellent presented talk. I think it is very useful for our students and research scholars for the to continue their work on the monsoon variability research. So anyway, it is excellent work. I think we have presented here. So we just on the commemorating Professor R. Anandakrishnan. This is really a good, nice to hear from you, sir. Thank you very much for your nice presentation and very, very informative for us. Thank you, sir, for accepting our invitation and giving this talk.
I thank you for inviting me.
Yeah, we also express our sincere thanks to Professor P.V. Joseph and Professor P. N. Sen for accepting our invitation to chair the session. Thank you, sir. You are spending your time and valuable time for the Professor R. Anandakrishnan's sake. I think it is excellent talk. I think thank you, sir. Both of you. Thank you.
Okay, thank you.
Thank you.
Thank you.
Yeah.
Today's sessions are over, and tomorrow's plenary session will begin in hall number 1, Pampa, at 9:20 in the morning. Thank you.